delegates and resource persons, invited speakers, welcome to the second day of the International Conference on Recent Advances in Nonlinear Functional Analysis and its Applications 2022, ICRANFA 2022. Today, we are going to start our invited talks by Professor P.S. Avadhan Garu, and the title of the talk is Concept of Fixed Points in Various Scientific Applications. It's very interesting talk, and the title itself presents the real life situations where fixed points arise. That is very interesting, and how to reach that fixed points also. I hope that I don't know. I hope that we can get the information, and accordingly we can maintain, or we can pose some iteration procedures to reach that fixed point. So let us see and let us wait to get the information. And this session says Professor K.K.M. Sarma, Department of Mathematics. Now over to Professor K.K.M. Sarma. Thank you.
Good morning, all of you. Once again, we welcome you all to the second day of ICRAN FPIA 2022. I take pleasure in introducing Professor P.S. Avadhani Garu for today's session. Professor P.S. Avadhani did his M.Tech Computer Science and PhD from IIT Kanpur. He is also Fellow of Institute of Engineers, Fellow of AP Academy of Sciences, Fellow of Computer Society of India. He was a professor in Department of Computer Science and Systems Engineering, and Principal, College of Engineering, Autonomous, former Director of IIIT Agartala. Presently, Professor Avadhani Garu is a member of Board of Governors of IIES and T West Bengal and IIPE Visakhapatnam. He has several awards to his credit, including Best Researcher Award by Andhra University and Best Teacher Award by AP State Government, and he held several positions in various conferences, and he is member Board of Studies and etc. Professor's areas of research interest are computer algorithms, cryptographic algorithms, data and network security. Professor Avadhani Garu was editor-in-chief for CSI Vizag. Professor Avadhani Garu visited Southern Polytechnic State University, Atlanta, USA, Turkey, Malaysia, and Tehran by invitation to deliver lectures and share his ideas towards the development of computer science. Professor Avadhani Garu guided 34 PhDs and now guiding 9 more students for PhD. And he has completed 2 research projects and conducted 6 symposia. Also, he published 1 textbook published by Tata McGraw-Hill and wrote study material to several universities for schools of distance education. Professor Avadhani Garu is life member for several societies like Cryptographic Society of India, etc. He has delivered numerous invited talks across India. Professor Avadhani Garu published more than 110 research papers, both in international, national journals, including several conference proceedings. He has 2 IPRs and 11 articles to his credit. Now, I request Professor Avadhan Garu to present his talk on concept of fixed points in various scientific applications. I welcome you, sir. Thank you.
Thank you all. First of all, let me thank Professor KKM Sharma for presenting me in a nice way. I think I'm audible, right?
Yes.
Okay. And also, I am thankful to Professor Ravindra Babu Garu for accepting my request for talk. In fact, he contacted me. Then I said I would give. It's not a fixed point theory of more mathematically. Conceptually, I said I would give them give the concepts because which I faced in general. So whenever I happened to be there in a board of selections as a government nominee for some institution, where one of the mathematics students appeared. Though I am a member to observe only, the proceedings and all, not asking mathematics questions also. So their mathematics selections were there, computer science selections were there, and so on. So I was sitting there. One student, he was asked, when do you say that a set is compact? He said, every open cover is a finite subcover. Okay, fine. Then they asked him, what is open cover, what is finite subcover, and so on. But that fellow did not explain because, and not only that, they said that, okay, then what about it is in the Euclidean space? It is closed and bounded, he said. But the point is, what is, give an example, how do you find out a finite subcover? These things he was unable to explain. Then I thought, okay, maybe the conceptually, when Professor Babu asked me, I thought conceptually, let us think about fixed points, which over the years we have been thinking about it. Right from my IIT Kanpur days, there were some examples and so on. Fixed point theory, mathematically, I'm not talking about mathematics or so. So fixed point theory in general, the concept of fixed point theorem, fixed points in scientific applications, how they are. And before going further, my pranams to all our gurus. So to name Professor N.V. Subramanian Garu, from whom we have learned talking fearlessly in a way. That means you can we can put the things what we think right in the right perspective. And next one is Professor J. Gopal Krishna Garu. Professor J. Gopal Krishna Garu is a stalwart in many ways. Because he is very nearer to my house. I used to interact with him many times. And then he used to tell us many things, including Mahabharata, Ramayana, and everything. And also how the time measurements and things like that. So P.V. Krishna Garu is the only man who is called Guruji in the department. Even Professor P. Henry Subramanian Garu, one day he said, so call Guruji. He said, who is that Guruji, sir? We asked him when we were students. He said, there is only one Guruji, who is P.V. Krishna Garu. That's it. And KPR Sastry is a source of guidance, source of inspiration. So, in fact, I was the only student under whom, for functional analysis, we used to call him God, Devudu, and Professor U.M. Swami. And he's a man whom we used to emulate for his teaching skills. So, whenever we wanted to teach, we wanted to remember Professor U.M. Swami Garu, Madan Swami Garu. Madan Swami Garu laga paadam cheppali anukunevaadu. And Professor P.V. Raudamurthy Garu for his meticulous way of writing and then putting things in order. So everything meticulous way, that is the thing. And S.V. Krishna Garu for his encouragement and then for his wit and wisdom. So these are the teachers who made us. It is not that we studied. They made us to study, they made us to work hard, they made us what we are now. I'm sure everybody will accept. So now going to the concept of fixed point theorem. Normally, what is a fixed point? Any function fx is equal to x is a fixed point. Okay. Of course, that is invariant point with respect to a function fx is equal to x. And the conditions will depend on particular application. For example, continuity, whatever you call it, the condition, mathematical conditions are so they depend on. But the basic idea is fx is equal to x. That is the concept of fixed point. So let us see where, how, and these are useful. So somebody, hello? So I'm sure I'm audible, right? వినిపిస్తుందా?
Audible, sir.
Okay. So then the simplest form of fixed point theorem, just for the sake of it, I put it. If f from 0 to 0, 1 to 0, 1 is a continuous function, then there exists a point x in open interval 0, 1 such that fx is equal to x. So this, I just wanted to put it only mathematically. See, for example, you can prove it using the intermediate value theorem. For example, f is a continuous function from a, b, and s is a value between fa and fb. See, why I said s is between fa and fb, because fa or fb, which is bigger, we don't know. So that's why you can't say fa to fb. Then there is a point x belonging to open interval ab. I'm sorry, it is not a closed interval. Open interval ab such that fx is equal to s. So you can take a is equal to 0 and b is equal to 1, s is equal to x. We get the simplest form which we have said. This, of course, I just put it for the sake of the completeness to start with. Now you see the concept. What is the main concept? Fx is equal to x. So that x can be called a fixed point. All other conditions for existence, uniqueness, etc., and depend on applications also. Now, what are the application areas? See, cartography. What is cartography? Cartography is map preparation. Cartography is a very big subject which normally MSc mathematics people are very good at it. The greatest cartographists in the world are basically pure mathematics people, because of the fixed point theory and many other analytical tools. So cartography is map pointing and map preparation, because whenever you want to prepare a map, there must be some fixed point with which you have to start with. So you have to identify where India is, where something is, somewhere you have to start, maybe the equator where it is, and then only you can map it. Otherwise, how do you do it? Similarly, GIS. After all, everybody in our car these days have GPS, Global Positioning System. And how do you know whether you are going in the right direction or not? The GPS would tell you. So for the basis of GPS, you require GIS, Geographic Information System. The information on the geography, that is, geo means earth, the earth information system. And also space science and cyber security, and which is my area of work. And cyber forensics. Cyber security and cyber forensics are my area of work. So these applications I just want to touch upon, because after all, half an hour, I don't think I can do much better. I just want to give some ideas about it, so that people who want to work further, they can take the pointer from this. Some illustrations, just ideas, you can say. solar system. The first one is solar system. Giant wheel, Rubik's cube, traveling from one place to another in a city, travel in space, travel in sea, time measurement. So what are the fixed points in these areas? And also some more are there, which are surveying, for example. I told you cartography, surveying, for example, in the civil engineering sense. Fixed points in humans and authentication. These are all the things which I thought I would put it in that order. First of all, solar system, you see. So solar system, when you identify what is the fixed point, everything keeps moving. In fact, remember, in the total space, even sun keeps moving. But in this galaxy, it is a fixed point. Sun is a fixed point here in the solar system because everything moves around the sun. Therefore, we can calculate all the other speeds and all with relative to this fixed point. Remember, every system, so which, for example, here we normally we take fx is equal to x. That doesn't move. That is the idea here. Okay. Next, a Jade wheel, for example. I'm sure in the early childhood of ours, everybody must have climbed a giant wheel or a Rangul Ratnam, what we call. So in the giant wheel, when you keep moving, I'm sure everybody's blood pressure will be high. It grows up because there will be some fear. We are going and then rounding and so on. So the giant wheel fixed point is its center that is axis, which doesn't move. So whenever you wanted to get out of that fear complex, look at the center point, which doesn't move. So to some extent, to large extent, your what is that, anxiety or the blood pressure will be reduced. So because it is a fixed point, so that it doesn't move around, so our feeling of movement gets reduced. This is another example. And third is more interesting. Rubik's cube. I'm sure all of you must have seen Rubik's cube. Rubik's cube has 6 faces. It's a cube, 6 faces. Each face has a different color. You can see that the diagram which I have put it next to that. Remember, there are 9 3x3 cubes in each side. For example, the top side of this diagram, we have yellow, and on the left side we have red, and then on the front side we have green, and we have the other 3 sides of the back which have different colors. So what is that we have to do? The problem, this is a puzzle, Rubik's cube puzzle, and rotation in all 3 directions are possible. The Rubik's cube, for example, you can see, you can rotate like this, and so on. And what is the problem here? The problem is the puzzle is to bring a jumbled cube to its original position using rotations. See, I put the jumbled the cube. That is, the colors are different in each of the faces, and you have to put colors, each color of that one side same color. Here the problem is you have to rotate it. You can rotate and then bring it, but the point is, how do we calculate the year in which a past incident occurred? Naturally, we need a reference point. For example, how to find the exact date of Mahabharata war? It is an accepted fact by historians that it has happened. How to find out? This is done using a fixed point in space called Ursa Major or Big Bear constellation. That is called Big Bear constellation. In Sanskrit or Telugu, Saptarshi Mandal. It is called Saptarshi Mandal. You can see that. This is what it is. Ursa Major or Saptarshi Mandal. I put 2 diagrams because one is in Sanskrit, they call it, and the other one is our English version. So it is called Saptarshi Mandal. How do they measure Saptarshi Mandal? It is observed astronomically that Saptarshi Mandal stays there in each nakshatra for 100 years. So Ursa Major or Big Bear constellations, Saptarshi Mandal will be for 100 years in each nakshatra or star. There are 27 nakshatras. You can say Ashwini, Bharani, Kurtika, Rohini, Mrgashira, Arudra, Punarvasu, Pushami, Aslesha, and so on. So, and this 100 years is a fixed point in that. So that, and also it moves in the anti-clockwise direction. So it is researched that Mahabharata, when it has happened, this constellation, that Ursa Major constellation, is Magha Nakshatra during war period. So using which it is estimated that the war happened in 139 BCE. So this time measurement is also done through fixed points. Fixed point, Ursa Major is a fixed point for 100 years in a nakshatra. So that through that, it is done. There are TFR calculations are also there. Tata Institute of Fundamental Research Physics Department. I've seen 2 or 3 papers on this. It's a very interesting study. Now surveying. Obviously, when you want to, suppose you have a, there is a big layout of house plot. How do we identify our plots in that layout? We need a reference point, obviously. If there is a huge ground, where is your plot? So it's a reference point or a fixed point to start with. And now, fixed points in humans. See, what is that here? Fx is equal to Fx is the time or the age, let us say age factor. So what is that which do not change with our age? How do you identify? Though face changes, fingerprints, iris, DNA, let us see that. So why do you require that? For example, Restart or Restart G, Babu Garu wanted to identify a student, he will immediately ask the identity card. So why do you ask identity card? Identity card is an identity that he is a student of Andhra University, where his photo will be there. So we identify with a photo. But in advanced way, we use now fingerprints. Fingerprinting already we have been using in the university. And for Aadhaar card also we have fingerprints. Passport we have fingerprints. So this is for authentication of a person. The idea is that fingerprint is a fixed point for a human body. And similarly, face is a way to identify. It is a fixed point. So these are all the issues. How do we identify human beings? What are the fixed points of human beings? That is, what are the points or parts in humans which do not change with time? So fingerprints, for example. See, how do you identify fingerprints? Fingerprints issue, I mean, it is proved that fingerprints will not change. And also, but it is the problem is that once 1 in 20,000, the fingerprints will be same. That is, if you take 20,000 people, the probability of 2 people having the same fingerprints will be there. It's much higher. Therefore, so, but here also the fixed point is they see the minutia points. That means Sudulu and down. Any Sudulu a distance and these are all the identifications. So, but this is not safe because for 2 reasons. One is 1 in 20,000 is a probability. The second one is somebody's fingerprint is lost. Then how do you recover the data? How do you identify him? That is the problem. Purposefully, somebody will cut his fingerprint also if there is an enemy. It's possible. Hand geometry, same thing. If hand geometry is also same way, it is assumed that it doesn't change for the next 50 years. But what if the hand is cut? The face recognition. Face recognition, though we may not be able to recognize. For example, I happen to meet my classmate in US. Presently, I'm now talking from US. So recently, I met my classmate. None of us recognize each other. So I was so smart at that time, and then, but unfortunately now I'm bald-headed and so on. So my smartness, he was expecting me to be as smart as I was like that. And similarly, I was expecting him in that way. But when I see him, he was fat and so on. He could not recognize me, neither I could. So, but computers can do that because there is an algorithm of face recognition of the features. But still, the threats of face mask and plastic surgery made things difficult. The fixed points are changed now. So this is the recognition process. I don't think I can do that. Now, iris. Iris recognition is a biometric identification that uses mathematical pattern recognition techniques on one or both irises of an individual iris. Iris recognition is possible as the eyes have a complex pattern that are unique, stable. So iris is a fixed point of human body. Iris means kanti papa. So you can do that. But the point is the radiation effect will be there. So that is another disadvantage here. So this is the recognition of iris process, wherein every day if you look at the camera or the iris catching device, then well, it's possible that eyesight may be affected. Next one is DNA. People suggested some DNA, but DNA is useful for finding relationships. It's not a fixed point for an individual. That is the problem. In fact, ATGC, they are called nucleotides. These 4 nucleotides are there for a genome sequence also. Everybody genome sequence is also through ATGC. That bioinformatics or bio engineering people or bio mathematical people, they will be able to do it. Tell us better. Genome sequence, people are saying that this is ultimate. So people say that every human being has a genome sequence. ATGC, GC80, only four nucleotides, but millions of it in a specific sequence. the sequence is fixed. Almost the people say that 3 million to 10 million will be there. So it is a unique fixed sequence. If the sequence can be identified for each person, let us say, I will have a unique sequence and Professor Kanak Sharma will have a unique sequence. And so everybody will have a unique sequence. That sequence defines a human being so that authentication can be done, identification can be done uniquely, number one. Number two, any ailment can be rectified by because everybody will have a fixed sequence. So if there is a change in the sequence, then that creates a ailment, it seems. So you can fix it up. So finally, people say that if genome sequence can be identified, then authentication issues will be solved. But however, there are other problems which we are not now discussing. These are the fixed points I thought I would put down to you all in various applications, because half an hour is that my time. It is closing now. So discussed about the concept of fixed points in various areas and applications, in particular in authentication, in computers and authentication, and the issues being faced in authentication also presented. These are my conclusions. And then if the chairman, Professor Kanak Sharma permits me, I thank everyone with this. Thank you. Over to. Sharma garu?
Excuse me, sir.
Please. Tell me.
Avadani, sir.
Chapandi.
Can you please tell about DNA? I mean, again.
Okay. You can see that slide.
Yes, sir.
DNA is there for everybody. Okay. It is the structure. It's called helical structure. Because of DNA, we get everything. You must have heard about a DNA test. For example, somebody claimed, let us say one politician, somebody claimed that I am the son of so and so, and he abandoned me when I was childhood. That was the case. Then how do you identify? They do the DNA test. So even in the hair also, human hair also, the DNA is there. It is so. What it contains is it contains 4 nucleotides. They are called actinine, thymine, guanine, and cytosine. So they are popularly known as ATGC. Instead of calling them, we call them ATGC. They are called nucleotides. So each DNA structure will have these nucleotides. So what happens is this ATGC, millions of them will be there with us. I mean, DNA also millions of them will be there. So normally it is expected or it is assumed that DNA, DNA maps, for example, hierarchy or hereditary, for example. Hereditary will be through DNA structure. So using DNA, one can identify what is the whether they belong to that hierarchy or not. For example, people claim that they have conducted DNA tests all over the world with various tribes, and they claim that most of the tribes are originated from India. People say Aryans have come from somewhere and somewhere, but the DNA test suggests that people have migrated from India to other countries. So that is because of more scientific things as per the DNA testing. Now, so those type of relationships we can identify. Now the point is nucleotides. I told you, you can see the things written there, T, C, A, T, C, T, G, C, and so on. So those are called genome sequence. Genome sequence means nucleotides. These genome sequence, people say that it is fixed for an individual. That is, it is unique for an individual. My point is, it is fixed point for our loop, who ultimately at that time they have introduced the fingerprint concept. We are identifying with fingerprints. Now we are identifying with hand geometry, fingerprints, and so on. Maybe Aadhaar card. What do we have on Aadhaar card? How do you identify? Through Aadhaar card. It is only fingerprint. So likewise, now ultimately it is going to be genome sequence. That is the idea. So those, if you still are interested, you can refer to any bioinformatics or biomathematical books. They will give you more information about it. Okay.
Are there any questions from audience? So
Thank you, sir. No, sir.
thank you, Professor Avadhan Garu, for giving us an inspiring talk in real life time applications and using concepts of fixed points in various scientific applications. Thank you, Masharu.
Thanks,
Sure,
Professor.
thank you.
Thanks, Professor Avadhan Garu, for giving us a with fixed points with full descriptions, examples you have given to us. It is very interesting to us, sir. Thank you very much, sir.
Thank
Thanks
you. Thank
accepting our invitation and presenting your talk, sir. Thank you
Thank
once again. Namaste, sir.
Namaste. I'll
Please send that your talk to my email address, sir.
sure, I'll do that. Okay, right.
We share.
Right, thank you.
Thanks.
Thank you so much, sir. You given very important information for us. Thank you, sir.
Okay.
Now, the next talk is of Professor Anita Thomar. She's from Professor Anita Thomar. She is from. Namaste, madam. Namaste, madam. She is from Sri Dev Suman Uttarakhand University, Paint LMS campus, Rishikesh, Uttarakhand, India. She delivers her talk on fixed point iterations and Mandelbrot sets, and the session is, the chair of the session is Professor KKM Sarma. Over to Professor KKM Sarma. Please go ahead.
Good morning, madam. I take pride in introducing Dr. Anita Thomar. My voice is audible? Hello?
Yes, sir. Audible, sir. Audible.
Okay. Professor Anita Garu, she is Professor of Mathematics in the Department of Mathematics at Sri Dev Suman, Uttarakhand University, Uttarakhand. Professor Amita Garu published more than 60 research papers and some chapters in 6 textbooks. She's area of interest is fixed point theory and their applications. Professor Anita Tomar visited Senegal, Africa, Taiwan, Turkey, Thailand, Nepal, and Serbia for presenting her research works and delivering invited talks and lectures. She also attended more than 80 national and international conferences. Madam Anita Tomar received Teacher of the Year Award in 2020 and Leading Woman Scientist Award in 2021. And Professor Amita Garu guided 2 PhD students, and she co-authored 3 books for undergraduate students and has held several academic and administrative positions in 23 years of academic career and organized several activities for the overall development of students, successfully completed entrepreneurship faculty educated program for orientation courses, attended workshops like latex, empowerment of women, safety and other things, organized international e-conference on fixed point theory and its applications to real world problems, organized international seminar on academic writings to things to know, organized online national level quiz programs, organized online faculty development e-workshops, and several. Madam is also a life member of Indian Society for History of Mathematics and Indian Mathematical Society, professional member Institute of Engineering Research and Publications, and she participated in several blood donation camps and several. Now, I request Madam Anita Tomar to deliver her lecture. Thank you, Madam.
Madam, you start, madam. Your talk. Please start your madam. Your talk, madam.
Professor Anita Tomar
please
is presenting her talk on fixed point iterations and Mandelbrot sets. Madam, you can continue your lecture.
Madam, you start your lecture, madam.
Can you hear me, Madam? Seems that my voice is not audible. Madam, you can start presenting.
Yeah, no problem. That is not an issue. My voice is clear. But how to share the screen? Can anyone share? That's why I said to, because it's, yeah, it's there. It's there, but I don't know. I have never used the Cisco WebEx. I have opened the PPT. No, I have opened my PPT. Then it's coming, open system preference.
No, ma'am.
I don't know what is the problem. I'm clicking on the share button. It is coming open system preference. MacBook. Now I have downloaded the app also. Earlier I had joined from the browser only. Yes. Can't you share on my behalf? I have sent the PPT. I have sent a mail. Because I'm trying continuously trying. It's showing open system preference. No, I have downloaded the app also. Okay. Okay. So I'm exiting it. So good morning, everyone. Am I audible to everyone? Am I audible?
Yes, ma'am. Yes, ma'am. Audible, ma'am.
Okay.
Yes, madam. It is audible, madam.
Okay.
Okay. Please,
Maxi-
now you start your madam. Your talk.
Okay.
Very fine, madam.
So thank you so much. First of all, I'm thankful to Professor Babu for giving me this opportunity and to attend this conference. I also want to congratulate him for getting the extension of next 5 years due to his nice work in the area of fixed point theory and its applications. Congratulations, sir. Am I audible?
Madam, audible.
Yeah, congratulations, sir. So today I'm going to speak on fixed point iterations and Mandelbrot sets. So fixed point is nothing but it is a point which remains invariant under a given transformation. Or in a graphical terms, we can say that a fixed point is the point of intersection of the line y equal to x and the given curve. Please, next slide. So, what is fractal? Next. Next. Next slide. A shape does not have to be exactly identical to be classified as a fractal. Instead of shapes that display, there are so many fractals which are found in different aspects of life. For example, we can see fractals in nature. Please keep moving the slides also. There are many different fractals which we see in different aspects of life, like fractals in nature. Uh, in, in nature, we have different types of fractals, like branches of tree. animal circulatory system, snowflakes, lightning and electricity, plants and leaves, geographic terrain, river system, clouds, crystals, and so on. These are some of the factors which we can see in the figure. Besides this, we have also factors in computers. Computers have unlocked our ability to explore fractals, and because fractals are derived from the mathematical equations, we can explore these shapes at a finite deep level. The computer's capability of calculating incredible numbers gives us the ability to use complex fractals for real world applications like 3D modeling, terrain modeling, where incorporating fractal equations adds to the inaccuracy of the project. Besides this, we have fractals in shapes, mathematics, 3D modeling, information and data management, computer system architecture, other areas of technology. Physical structure, human psychology, mental work in fractal geometry, which became famous as a computer graphic program as soon as computers became famous as a computer graphic program of complex sine functions. Paper is published in Fractal and Fractional. This is our recent work. So today we will explore some novel variants of Mandelbrot set for transcendental complex function plus C, and this is a greater than or equal to NCR complex number, and Z is a complex variable. And we will utilize 4 distinct fixed point iterations for the generation of these Mandelbrot cells. First, we develop escape criteria for the selected cells for this via these distinct algorithms. Here I want to mention one thing, that an essential singularity and the collection of escaping points is not empty for each transcendental function. Concern is to utilize the less number of iterations necessary point of transcendental function. And then we examine the impact of variables on the derivation of dynamics, color, and appearance of factors. The Mandelbrot set is nothing but the collection of C, so that the function, if we take PC z equal to z square plus C, that function diverge iterative point 0. Which is stress getting some common C and then examining the sequence PC 0 approaches to it. It is on the next slide. I'm on preliminaries. If we vary the initial point of Z, considering C to be constant, we obtain Julia set. The connectedness locus of family of polynomials may also be described as the Mandelbrot set, which was thought to be disconnected at first. Disconnect. Mandelbrot set. Mathematically, the Mandelbrot set, it is in these. Mathematically, the Mandelbrot M is defined at point C, where C is a complex number, in case FPC is connected. It is the complex value parameter, so the filled Julia set is connected. Equivalently, we can say that it is the set of all the points C belonging to C, such that PCZK does not diverge to infinity as K diverge to infinity. If we define a complex value self map from the set of complex numbers to the set of it is definition 1. Next slide. Next slide.
2 days, so many scholars, professors, all this from everywhere. ఇప్పుడు ఉత్తరాఖండ్ నుంచి మాట్లాడుతుంది. ఇందాక ఆయనేమో
It is on the next slide. I am on definition.
యుఎస్ లో ఉన్నాడంట, ఆయన మాట్లాడాడు.
So the pika
ఇప్పటికి ముందు
is ZK plus 1 PZK. It is clear that one step feedback procedure. If we define Zk plus 1 equal to 1 minus alpha Zk, alpha PZK, then it is a Mann iteration, and Mann iteration is also a once feedback define Zk plus 1 equal to 1 minus alpha Zk, fine. Zk plus 1 equal to 1 minus alpha Zk, alpha P is Yk, where Yk is nothing but 1 minus beta Zk plus beta P xk xk is 1 minus gamma Zk. And new iteration is the three-step feedback procedure. In the new iteration, we take gamma equal to 0. We obtain the Ishikawa iteration. If we take beta and gamma to be 0, then we obtain Mann iteration. If we obtain alpha equal to 1 and beta and gamma to be 0, then we obtain Picard order. So, particular we have used sign function mathematicians and astronomers. However, Jaya is it is on the previous slide. However, Jaya function of arcs of the circle instead of angles. The modern trigonometric function of sine is a function of rectangle whose only fixed point is 0. The more improved version of sine is an finite series allowing their arbitrary negative and positive and complex numbers. We know that modulus sine Zn is always less than equal to 0. And we can write modulus of sine Z, it is in the previous slide. Modulus of sine Zn is equal to modulus of Zn minus Z3n upon factorial 3 plus Z5n upon factorial 5 and so on. If we take mod Zn to be common, then it will be 1 minus Z raised to 2n upon factorial 3 plus 1 upon Z raised to 4n upon factorial 5 and so on. Similarly, we can expand sine by n and sine xn. So, if we take modulus of 1 2 and Z upon factorial minus to be equal to 5 terms given equal to and x terms to be greater than 3, we have to make it like to and it would just for all the values of x, y, z, for which omega 1 is equal to omega 2, in which estimation is done for points x and y in the plotting region. I'm on the previous slide. Depending on the computation behavior of the color of the pixel is selected, the parameters are in every iteration to check if it is a critical escape, stays in the range or not. If this stays the color of every point demonstrates the rate of reaching the escape point. The black color generally demonstrates the parameters which do not succeed to escape prior to the iteration. On the other hand, the brighter shade demonstrates the escaping points. This provides a visual description of the number of cycles necessary to attain the escape stage for this. And the complex region is partitioned into specific number of pixels. If C is the center of the pixel, we iterate the critical point 0 under PC and every stage if the orbit has modulus greater than 2 or not. Whenever this is attained, C is not contained in the Mandelbrot set. Initiate the pixel in accordance with the number. Keep iterating the number whether the reading in the Mandelbrot initial side we have a complex sine function in corollary 2, which is on your this corollary scheme. Note, and in theorem 2, we have developed the escape criteria for iteration corollary in this algorithm in the iteration. Theorem 3, we have developed the minor for iteration and corollary is the escape criteria for monoid. So I have skipped the book in the theory we have developed. So the selection of the parameters in these terms is new and has not been studied till now. For some k, then the orbit escape, meaning thereby that Z is not inside the Mandelbrot set. However, if Zk does not exceed, then due to definition of the set, we utilize this algorithm to generate the fractal in this section. So these are some of the fractals which we have generated. Please keep this slide. We have used the different parameters for the generation. The first one is first figure is for Noor orbit. Second is for Ishikawa orbit. Third is for Mann orbit or Picard orbit. You will observe that all these are symmetric about symmetric x-axis as well as y-axis, and one who are almost identical, and the size keep decreasing as we move from Noor to Ishikawa, Ishikawa to Mann, and Mann to Picard. Next slide, please. So these are some of the figures. In this, we have utilized different parameters. If you will notice that the shape of first fractal is like a shaveling, which is worship, which is a god of Hindus. Next slide, please. And in this, you will observe that for in figure 3, you have entirely different type of fractal in the Mann orbit. In Ishikawa and Noor orbit, we have similar fractals, but for Mann orbit, we have entirely different fractal, and this fractal contains a ring structure in between. Next slide, please. So in this, the ring of Mann orbit becomes larger in size, although the fractals in Noor orbit and Ishikawa orbit are almost similar. Next slide, please. Here, the fractals in Mandelbrot set and Noor orbit are same, and their shape is like a flower. And in Mann orbit, the size of a ring in between is larger as compared to the earlier fractal. And shape in the Picard orbit is always different to the please. These are the entirely different versions. You will notice that the shape in the Picard orbit is entirely different, and these fractals are similar to some glass paintings. Next slide, please. Next slide. And here also you will notice that in Picard orbit, the shape is entirely different. In Ishikawa and Noor, the fractals are similar. In Mann also, the fractal is different, but Picard is entirely different. Next slide, please. So this is the case. This is again our beautiful fractals. These are some of the fractals which are similar to some flowers, or we can say rangoli. Next slide, please. So this fractal is similar to the S alphabet of English. This is like a star. Next slide, please. This is like a spinning wheel which children use in Deepavali. This fractal resembles a swastika. As the value of n increases, the fractal becomes circular in shape. This is again like a spinning wheel. Next slide, please. So this is again like a spinning wheel. These fractals are circular in shape. Next slide, please. This is like a Milky Way in Picard orbit. Next slide, please. So we have obtained beautiful fractals. This is again like a spinning wheel which the children use in Deepavali festival. Next slide, please. So we have explored very interesting fractals using our sine function in all the 4 orbits: Ishikawa, Mann, Noor, and Picard. Next slide, please. Next slide, please. So I want to mention here that you must please keep this. So you must notice that when alpha is less than equal to beta is less than equal to gamma, then we see that Mandelbrot we obtain beautiful Mandelbrot sets for the Noor process. If alpha is less than equal to beta, then beautiful fractals for Ishikawa iterative process we obtain. And One more thing I want to mention here, the Picard method is proved to be very weak in getting Mandelbrot set with desired accuracy, shape, size, color, and resolution. This is again a topic of research that why the Picard method failed to give a fractal as obtained by other methods in this paper. Because in Ishikawa and Noor orbit, the fractals are entirely different, and in Picard orbit, the fractals are weak as compared to other orbits. One more thing, you have noticed that some of the fractals resemble spiders, starfish, shivling, carrying a trishul on the top, which is an abstract representation of Hindu god Shiva. Or you have seen the fractals of spinning wheel, which the children use during Deepavali. Some of the fractals resemble Rangoli, and so on. See, surprisingly, cubic, quintic, and sapling Mandelbrot set in Mano orbit are entirely different and stunning, having a ring in the outer center, which is increasing in size with increase in the values of n. So, this was all about the fractal. So, in the end, I want to say that science and everyday life cannot and should not be separated. So, thank you very much for your kind attention, and sorry for the inconvenience caused because my laptop was not supporting the sharing of the screen. Thank you so much.
Thank you, madam, for your inspirational talk. Because of some technical problems, we were unable to follow you, but it's a wonderful talk. It involves a lot of hard work put by you to present this talk. Thank you once again, madam, for giving us a talk on fixed point iterations and Mandelbrot sets. Thank you very much, madam. Thank you.
Thank you, sir.
Professor Anita Tomar, madam.
Yes,
Initially, the transmission is not good, but we got the information, correct information from the middle onwards. We followed fully, and please, it is interesting, madam. You did varieties of Mandelbrot sets. It is very difficult task to get that information. To do research also, it is very difficult. In one conference I attended in New Delhi, there they told that Mandelbrot sets work in research is very difficult, they said, but you are working in that field, it is very interesting, and so many diagrams you obtained and presented also, that differences also you are explaining. So very thank you very much, madam, for your presentation and for your accepting our invitation to present your talk in my on my superannuation. This is arranged, and thank you very much. And please send your that talk to my email, madam. Copy. Share.
Yes, sir.
I have. It is already with us. It is already with us.
Yes, okay, sir. I have sent on your email.
Very nice.
Yes, sir. And thank you so much. Congratulations to you also again for getting the extension of the next 5 years. And I hope you will again continue the work in fixed point theory and its applications as you were doing for such a long time.
Thank you, madam. Thank you, Professor Sarmagar. Thank you for chairing this session.
Thank you.
Oh, no. నేను పెడతావు నాకు నేను స్టార్ట్ చేసి ఇచ్చా నౌ today's next invited talk, we welcome Dr. Jade Wheel, Department of Mathematics, Illinois Wells Wellyan University, Bloomington, IL, USA, and F.A. McRae, Department of Mathematics, Catholic University of America, Washington, D.C., USA, and Professor J. Vasundhara Devi, Department of Mathematics and Gayatri Vidya Parishad, Professor V. Lakshmikantam, Institute for Advanced Studies, Gayatri Vidya Parishad College of Engineering, Visakhapatnam, India. It is a combined talk of all these three professors, and the title of this invited talk is A Brief Overview of Qualitative Theory of Various Mathematical Models. And the chair of this session is Professor P.D.N. Srinivasu, Department of Mathematics. I welcome all the invited speakers and Professor P.D.N. Srinivasu to chair the session. Welcome.
Many thanks, Dr. Babu, for giving me this opportunity to chair this session. We have a very interesting topic that is going to be discussed in this session, that is a brief overview of the qualitative theory of various mathematical models. And that is being done by three very established professors in the fields of differential equations. And they have mastered several branches of differential equations. That is very, very interesting. The topic itself is very motivating. I'm sure those who are taking part in this session will be of great benefit to all the people. We have three speakers sharing this particular presentation in a period of 1.5 hours. The first speaker is Dr. Zahia Drissi. The second speaker is Dr. Farzana McRae. And the third speaker is J. Vasundhara Devi. It is my present duty to briefly introduce all the three speakers now. Dr. Drissi's research interests include various areas of ordinary differential equations. At present, she is focusing on fractional differential equations. She has co-authored with Dr. McRae and Dr. Vasundhara Devi number of research papers. They have also authored 2 books, and she has co-authored a research monograph with Professor V. Lakshmikantam. She will be present in the first part in the 3 parts of this particular talk. And the second speaker shall be Dr. Farzana McRae. Dr. Farzana McRae, she has hold on several fields of differential equations like stochastic differential equations, fuzzy differential equations, among many other fields. She has also authored many articles with Dr. Vasundhara Devi and Dr. Drissi. She has authored 2 chapters in qualitative theory of various types of differential equations. She has also co-authored with Professor V. Lakshmikantam a monograph. She'll be presenting the second part of this particular talk. The third part will be presented by Dr. J. Vasundhara Devi. She was mentored by Professor Lakshmikantam for her PhD degree. She has written 2 monographs with Professor Lakshmikantam. She has published more than 100 research papers in various fields of differential equations. She has completed 3 very good research projects funded by Government of India. Recently, she has authored a book on linear algebra and differential equations, which is published by Taylor and Francis. She has worked in several branches of differential equations. To mention a few: set differential equations, matrix differential equations, fractional differential equations, so on. She has collaborated extensively with Dr. Drissi and Dr. McRae. So I'm sure this is a wonderful team to really present us regarding various perspectives of mathematical models. I'm sure this will also give some input to the utility of the mathematical models that are going to be presented. We are eagerly waiting for the talks of all the 3 people. They'll be sharing this in a period of 1.5 hours. I think the sharing will be left to themselves. Thank you very much. May I now request Dr. Drissi to start her presentation?
Thank you very much for the introduction. I'm going to share I would like to share my presentation. Under the share, I'm not seeing, okay, let's see, I'm trying to. Hello, application. Can I get some guidance, please, on how to share?
How to show?
Ma'am, in the bottom you can see camera there, there's share button, share option, right?
Yes, and that's what I opened it, and it
And you'll get
says
the your presentations will be there, no ma'am. If you select the presentation tab, then you will get the share symbol in the bottom, ma'am. Then if you click, the screen, the share will be happen, ma'am.
if I do what? I'm sorry. It says, so when I click on it, it says open system preferences. So
It's a
I do
MacBook, ma'am.
that, and I have to go to Cisco, I suppose. Okay, hold on. Let me see. Hmm.
Madam, besides camera,
Oh,
there are
okay. I
dots are
think
there. 1, 2, 3 dots are there. Besides camera icon, 3 dots are there, madam.
okay.
So if you click
Oh, I
those
see that.
dots,
I see.
third
Okay,
option
let's
is
see.
sharing your content.
I see. I clicked on Cisco. Let's see if it's going to let me do that now. No, it's still telling me open access preferences, which I'm doing. Camera.
Ma'am, is it MacBook, ma'am?
Yes, it's a iMac.
Ma'am, have you joined from browser, ma'am?
From the browser. Okay.
You need to join from the application, ma'am. Cisco WebEx app. So then it will do. From browser it will ask permissions, ma'am.
Okay, so if I go to the browser, I'm opening Firefox, and then you're telling me to go to Cisco, join meeting. So should I leave this meeting and re-enter?
Yes, ma'am.
Is
Yes,
that what
ma'am.
you're
You
asking
need
me to
to
do?
again join from the application, ma'am.
So I'm going to leave this meeting and join from the
Application, ma'am.
because I thought that's what I did from the okay, sign in. Uh, okay. All right, I am in the web page. I entered my email address. It's asking me for a password. Is that the
Well, come and tell her the password, please.
Its password
I'm
is
looking for
2021, ma'am.
2021? Okay. No, it's not letting me. Oh. think I need to leave this meeting. I'm going to leave and re-enter with the. Where do I leave? Hello.
Ma'am, have you joined from
You
application?
hear me? Yes, I went to the application. I got the code. I did everything, and it's still giving me the same. Okay, open access. I'll try that. Went to Cisco. Yeah, I tried. I entered from the web. I did get a code sent to me by email. I used that to get in. But when I click on share, it wants me to go to my security thing and allow this. I click on Cisco, but nothing is happening. Click to. Okay, I think I got it.
Ma'am,
Oh, let's see.
you share the presentation to us, ma'am.
Yeah, I'm going through the going through the security checks, and no, it's still okay, let me try again. No, it's allow to share content, grant access. So I'm trying to grant access, going to the system preferences, which I did. Cisco Advanced, okay. Log out after 60 requirements. So it says it requires an administrator password.
Ma'am, we have shared the email address in the chat box, ma'am.
Okay,
You
hold on, maybe.
presentation to that mail, ma'am.
What's that?
Ma'am,
Requirement.
I have shared the mail ID in the chat box, ma'am. You can
Okay,
share the presentation to that mail ID, ma'am.
okay, let me try this.
Yeah, I can do it for you if you send me the presentation.
Oh, okay. All
Just send
right.
me
Okay,
the.
let's see. Let me see. He said he sent me something in the chat.
No, that's only to share the presentation.
Oh,
If
okay.
you
All
want, I
right.
can
So
do it for you, or they can do it.
all right. I'll send it to you. Hold on.
Okay.
Yeah, you should have sent us the instructions. All right. So file save. I send it to your JV,
Yeah,
JV Devi.
okay.
Okay, I sent it.
Okay, I'm waiting for it to come. 1 second.
Okay. So basically the problem was that in order to share, I had to set permission in the system preferences, which I tried to do, and I thought I did, but nothing was happening.
I still didn't get it, Zahia.
Okay, let me check. Well, it's a PowerPoint, so maybe it takes a... Let me check if it's sent.
Madam, Vasundhara madam.
Yeah,
Yes.
it is sent, so you should get it.
Vasundhara madam.
Yes, sir.
మేడం నేను నానాజరాని మాట్లాడుతున్నాను.
చెప్పండి సార్.
ఇప్పుడు మీ మెయిల్ కి షేర్ చేసి మీ నుంచి ఇక్కడ పంపించడం అవుదా?
నేను ప్రెజెంట్ చేస్తాను సార్, ప్రాబ్లం లేదు నాకు.
ఓకే ఓకే, నో ప్రాబ్లం.
నేను ప్రెజెంట్ చేస్తాను.
సరే మేడం, ఓకే.
ఓకే సార్.
So yeah, because it's a PowerPoint with about 30 slices, so maybe it's taking some time. I can see.
Why don't you send it again, Zahia?
Yeah, I'm doing that. I can see that it's uploading to as an attachment, and for
Okay.
some reason it's slow.
You can just start the general introduction.
Yeah, actually. Well, no, because without the visual, I think it's almost there. Yeah, perhaps I can just say, well, let's see. I close the. I need to try again. Okay. All right. So it should get there.
Got it.
You got it? Good. Ready? Can you all hear me? Okay. Well, thank you all for your patience and sorry for this technical problem. It's probably coming from I don't know which side, but anyway, it's good that now we're back to normal. Okay, thank you. Vasu, could you please go to the next slide? Since they have already introduced us, I think there is no need to go through that. I'm Zahi Adrisi, the first speaker of a three-part talk. As I said, first we want to thank Dr. Babu for the invitation. We also want to thank the members of the organizing committee. We thank the session chair. Thank you very much for that kind introduction. And we want to congratulate Professor Babu on his retirement. Next slide, Vasu. So as was mentioned earlier, we're going to look at a number of mathematical models and talk about the qualitative theory. Not just any qualitative theory, it's the qualitative theory introduced by the Professor Lakshmikantham It's a theory that's based on the differential and integral inequalities and also the comparison principle. So we're going to look, you see this list of mathematical models that collectively, the three of us and also other members of Dr. Lakshmikantham's group have worked on. And so you see we have from ordinary differential equation to integral differential equation, delay, stochastic, impulsive, fuzzy, set, fractional, differential equation with retardation and anticipation, and more recent result like the matrix and graph differential equations. Of course, the list is long. What we intend to do is divide up the work among the three of us. I will start with, and Basu, maybe you could go to the next slide. I'll start with the ordinary differential equation. I want to give the framework for the Lakshmikantham theory, give the basic results, and then do it with our ordinary differential equation so that things are simple enough so that you could see we can focus on the ideas. And then my colleagues are going to divide up the rest of the types of models and highlight the extension of the basic results. Of course, we're not going to cover all the basic results for each type of equation, but very selectively look at some result for some differential equation, and hopefully you'll have an overview of the theory, for all these models. Next slide, please. So when we say qualitative theory, what we really mean is properties of solutions of differential equations without actually solving the differential equation. So I've listed here a number of qualitative properties of solutions. I think many of you are probably very familiar with all this, but just for completeness, we have existence, uniqueness, properties, continuous dependence of solution on initial data, differentiability of solution with respect to initial data, and then you have some existence, especially proper to the approach that we're taking. You have boundedness, positivity of solutions, and then, of course, stability. Okay. Next, please. So what I want to do here is give you the framework or the basic structure of the theory. So it relies, as I said, on the differential and integral inequalities and the comparison principle. So first, using basic differential inequalities and the comparison principle, we're going to obtain the first basic result, which is the basic comparison theorem. So you see on the left there, I won't be able to show you, but on the left, you see you have the fundamental differential inequality result. And then we introduce the concept of lower and upper solutions. And these two basic results and concept will allow us to prove the basic comparison theorem. The comparison theorem or the comparison principle consists of using the differential inequalities to obtain a simpler problem, simpler in the sense of, for example, if the original problem involves vector valued function, the comparison problem could be just a scalar differential problem. And then the theorem we obtain are theorems that tell us that if the simpler scalar problem or the solution to the simpler scalar problem have certain properties, then under certain conditions, the original problem has the same properties. So you see it's a way through the inequalities, we transform the problem into a simpler one, do the work in the simpler setup, and then obtain results for the more complex system. So next then is with this basic comparison theorem and the method of upper and lower solution, we then can prove existence in a sector. And you see the little drawing I have there, the existence in a sector basically consists of showing that there exists a solution under certain conditions, of course, solution that's sandwiched between the upper solution, which is the one at the top, and the lower solution, which is the one at the bottom. So of course, and there are several theorems that, you know, in addition to the basic existence of solution theorem, but what I'm going to do is just show you representative theorems. So the next thing is with this basic comparison theorem, with the basic comparison theorem, the method of upper and lower solution, and the existence in a sector, we can get then into the iterative techniques. Iterative techniques means that you're going to obtain sequences of approximate solutions that converge to either, under the proper assumption, to the unique solution of the system, or to the upper maximal and minimal solutions. Okay, and the techniques that we have are the monotone iterative technique and the quasi-linearization, and of course the extension of each, and those are called the generalized monotone iterative technique and the generalized quasi-linearization. Next, please. And then, of course, we get into stability. And for that, we need the initial value problems to be well posed. And that means that we have to have a unique solution, and we have to have continuity with respect to initial values, differentiability with respect to initial values, as well as an additional conditions on the partial derivative with respect to initial time and initial, you know, with respect to t0 and x0, the initial values. So again, we're going to use the basic comparison theorem and the properties of the comparison problem, right? Remember, we're always, in a way, transforming the problem into a simpler one. And so we use those two concepts to prove, to obtain condition under which we have both the continuity and the differentiability with respect to initial conditions. And then once we have that, you see the next step is to obtain the variation of parameter formula and then start the theory of stability. The concept of stability that I'm going to mention are the three that you see there. I won't spend time now. So next time, next slide, please. And then this is another technique that combines the comparison principle, the nonlinear variation of parameter, and the Lapenoff function method to get the variational Lapenoff method. And this is yet another technique that allows us to obtain the type of results I was mentioning, you know, for a broader class of functions. So just to give you a sense of how complicated situation get very quickly, I have at the top there the basic initial value problem for ordinary differential equation. So you see x is vector valued, so is p, and you have given, so we have the ordinary differential equation and or system and the initial value. Look at how things get more complicated when we get into, for example, impulsive differential equation. So you see equation 19 there is the basic differential equation. And I should say that the system on the right is the initial value problem. And you see that in addition to giving the initial value and initial point, basically, you also have to give initial values at the impulses. The TKs there are the moment of impulses, and you see that you could have either fixed moment of impulses, meaning the impulses happen at regular time, or the impulses happen at variable moment of time. And you see that you have additional conditions. All right, the other example I have here is for set differential equation. Now the functions are set valued, so you have to, you know, the space is, in this case, the KCRN space, which is semi-linear space. We have to introduce the Hausdorff metric, and then the derivative is the Huku-Hara derivative, which you see on the right side. Again, I'm not going to get into all this because my colleagues are going to talk about that, but I thought I would show you that even though, you know, things may appear simpler in the case of ordinary differential equation, situation get extremely complicated for the other types of equation. Just for context, and so to compare this, the qualitative theory that we're talking about, and the basic classic theory. I have here the piano, and you'll see next in the next slide Picard. The reason I have them, so piano gives you existence under a continuity condition. Picard, as we know, gives us uniqueness, provided we have the Lipschitz condition satisfied. The point in both cases that I want to make is the fact that these are local existence theorems. Next, please. Next slide, yes. And then you see the other approach in a classical theory would be the use of fixed point theorem. And here I have the basic three fixed point theorem, Banach, Tikhonov, and Krasnodębski. And next slide, please. The reason I'm mentioning this again is to establish the comparison. So for all the theorems I mentioned, they all require transforming the differential equation into an integral equation, which in our case, there's no need to do that. We can work directly with the differential equation. The other difference is, as we mentioned, that's the third one in this list, is the local existence nature of those theorems. And for example, in the case of Picard theorem, we do have successive approximation and we do generate sequence. However, those sequences are not necessarily monotone, and we don't know anything about the rate of convergence of those sequences. Next, please. So now we get into the what we call the Lakshmikantham qualitative theory that uses, as we said, the basic inequality theorem. Here is the basic theorem. So if we have rho prime less than or equal to p of t rho and less than or equal to, yes, and theta prime strictly greater than p of t rho, and you see p is vector valued. If we have this order in the two function rho and theta at the initial point t naught, then we have the same order in the function rho of t and theta of t for t in the interval where, of definition, a subset of R. Then we define lower and upper solutions. So here is the definition. If V prime is greater than or equal to P of T rho, then we say that V is an upper solution. And if the inequality is in the reverse direction, then it's a minimal solution. Next, please. Here we define maximal and minimal solutions. So as one would expect, if x of t is less than or equal to psi of t over their common interval, over their defined, then x of t, psi of t is said to be the maximal solution, and if the inequalities are reversed, then you have minimal solution of 1, and the 1 is, Vasu, if you could go back to the previous slide. 1 is our basic, previous again. I'm just reminding this equation 1 is the initial value problem. So if you keep that in mind, when we say maximal solution, minimal solution, we're talking about this basic system here. Thank you, Vasu. Next. And next. Okay, so no, back, yeah. So, and then remember we said once we have the lower and upper solution and the basic inequality theorem, we can then get into the monotone iterative techniques. And here is the representative theorem. So here we say that if rho sub-zero and theta sub-zero are lower and upper solution of the initial value problem, such that rho sub-zero is strictly less than theta zero on J. J is a subset of the real line. Suppose further that we have a Lipschitz condition satisfied by P being the right-hand side of our initial value problem or differential equation. Then there exist monotone sequences that converge uniformly and monotonically on that interval to the minimal and maximal solution respectively, right? So this is, under these conditions, we have generated monotone sequences that converge uniformly and monotonically to the maximal and minimal solution. Next, please. So the rate of convergence for the monotone iterative technique is linear. And we mentioned that there was another technique, iterative technique called the Quasi-Linearization. That is a technique that was introduced by Bellman and Calaba. And what they proved was that under a convexity condition on the function P, it's then possible to show that the iterates converge quadratically. Yeah, that the convergence is quadratic, right? So it's a faster rate of convergence under convexity condition on the function P. In 1992, Professor Lakshmikantham and one of his students generalized that technique by relaxing the convexity conditions. And next, please. And they were able to obtain the, the fast rate of convergence, the quadratic convergence. So here is the theorem. I hope you can read. So the point, So let rho 0 and theta 0 be lower and upper. Thank you, Vasu. Solutions with this condition. So rho sub 0 is less than or equal to theta 0. And then instead of asking for P to be convex, now we ask for P plus a function phi, right? That's the sum of the two. That now is what we ask to be convex on this set, right? So the finding a function phi that satisfies these conditions, which when added to the function p and differentiated twice with respect to the second variable, gives us a positive quantity, then we have convexity of the sum of the two functions, and we have convergence, and the sequence converge uniformly to the unique solution. And the convergence is, we don't see the rest of it, but the convergence is quadratic. So it's fast convergence. Next, please. Let's do next slide. Oh, not sure what okay, you're showing us the rest. Thank you. The conclusion of the theorem. So next we get into stability, and for that, as I mentioned earlier, we need the well-poisonedness of initial value problems. I already told you what that means, so we probably could go to the next slide. And this is, okay, so this is a theorem that tells us under which condition the solutions be continuous with respect to the initial values. And what I want to highlight here, which I wasn't able to do very clearly on the monotone iterative technique and the quasi-linearization, because we didn't look at the proofs and it's harder to see. But here, as you see, we put a Lipschitz-like conditions here, right? We are using the function g, and we use g then to construct the comparison problem. And you see now that g is scalar valued, whereas the original function p is vector valued. And the theorem, oops, back please. Right, so we're assuming that the comparison problem admits the zero solution. And then what we prove is that if the solution of the comparison problem is continuous with respect to the initial values, then so will the solution of the original problem, right? So here you see the use of the comparison theorem in inequalities comparison principle. Next, please. Okay, and this theorem is a well-known theorem. This is showing the under the condition under which you have differentiability with respect to the initial values. And the condition 2 is, okay, what's this? Yeah, remember when we said the well-posed problem, well-posed initial value problem satisfies 3 conditions. The third condition is this, that the partial of x with respect to t naught exists and is solution of this, where h is the partial derivative of p with respect to x. Okay, now we are going to get into basic stability. So here, our basic initial value problem. The only additional assumption is that we're going to assume the zero solution, zero solution exists for this problem. And the reason we do that is because we're looking at Lyapunov stability and extension of that. So here our basic definition of Equi Stability, quasi-equi asymptotic stability. These are, so the basic Lyapunov theorems are under certain conditions on the Lyapunov function, you had uniform stability and asymptotic stability. Those were the 2 notions of stability that were defined, and these are extension, right? Additional, and these are not the only one. These are just representative stability properties that I'm mentioning. Next, please. And let's see. Yeah, then we're going to skip this because these are definitions of classes of functions that we need in proving the theorem. So we could skip this. We could skip this one. This is defining positive definiteness of, yeah, go ahead, skip this. Okay, so here we're going to then, and this is really what I want to highlight, the fact that we're always using a comparison theorem. Yeah, we can just go to this one. So yes, so what I underline here, you see we're using the Lyapunov second method, the comparison principle, and down here, what you have in equation 6 is the comparison principle. The thing to notice is that, again, the comparison problem is we're in scalar valued. The functions are scalar valued. Next, please. Okay, so this is a sample theorem. Let's see, Vasu, if you could, so that we could see the, could you reduce the size a little? Yes, thank you. So again, the thing to see is that you said we're using Lyapunov second method. So we define the function v, the Lyapunov function. G is the function that will constitute our comparison theorem. So we're assuming that that there's 0 when x is 0, some condition on v, positive definite, locally Lipschitzian in x. And then here is where we're defining the comparison problem. We're using dini derivatives, and everything is, you see, expressed in terms of the Lyapunov function here, the comparison problem. And then what we can show is that, you know, the equi, in this case, equi asymptotic stability of the zero solution of the comparison problem is going to give us the equi asymptotic stability of the trivial solution. Next, please. Yeah, so this is practical stability is another stability concept that's introduced. So in what we showed previously, we were looking at the stability of the zero solution, right? And we made the assumption that that indeed was a solution both for the original problem and the comparison problem. But sometimes we're interested in a state that may not be stable, but has some oscillation. And you see here, as I was going over the reviewing this, I drew myself some pictures, but you see, so for example, you have some oscillation about a given state. It's not stable, but it's probably good enough, right? So that's what that's the concept of stability called practical stability, and it was introduced by Lassalle and Lefschetz. Next, please. I'm going to just give you briefly the, okay, this is a comparison problem. Yeah, this is the definition of practical stability. You see, we're just saying if we have two positive numbers, lambda and a, such that lambda is strictly less than a, and if the norm of the initial point remains is less than lambda, if that implies that the norm of x of t is always bounded by this number a, for all t greater than the initial time, then we say the system is practically stable. And we can jump to the next slides. Yeah, here it is, right? Again, I underline the G because the emphasis in all this is, look, we can prove some stability properties if we are successful in establishing a comparison problem. And this is for practical stability. This is, again, you see the G of T norm X, and on the left-hand side, it's basically some form of derivative that we're introducing, right? And then the properties, if the comparison problem is practically stable, then the original problem is practically stable. And that ends the basic introduction I wanted to give you. This is the foundation for what comes next. So all the theorems and many more actually, but these are the sample theorems. These all have to be then obtained in the various setups that I mentioned earlier that my colleagues are going to talk about. Next slide, I would quickly want to show you some of the references. And Dr. Devi is going to probably have a longer list. Basu, could you get to the next slide, please? The references. The one above. I think you're in 34. How about, yeah, 33. So very quickly, could you reduce a little more? Yeah. Okay. So basically, the main references would be Volume 1 and Volume 2 by Professor Lakshmikantham and Dr. Leela. That's where the basic ideas were introduced. You see, it's called Differential and Integral Inequalities. Then we have, the book by Agarwal and Lakshmikantham on uniqueness and non-uniqueness of criteria for ODEs. Then we have the basic, I highlighted here the basic paper by Lapenoff. And then we have our own paper, which is, I think, a nice paper because it's an overview of differential inequalities and the comparison principle. And we say this is the core of Professor Lakshmikantham research. And then, Volume 2. And what I had on top is all this presentation comes from a chapter that the three of us have written. And I think the reference would be in Dr. Devi's talk. So I stop here. I hope I stayed within my allotted time. Next is Professor McRae. Thank you. We take question at the end of the talk, at the session.
Everyone, First of all, Vasu, I think you have my slides, so maybe you can show those. Yes, you can share. Do you? It
You need
starts
to
on
give me a
slide.
minute. You need
Okay.
to give me a minute.
Okay.
And just do the introduction part and I'll set it up.
Okay. Well, so my part of the talk is we're going to take what Dr. Drisi said about using the differential inequalities and comparison theory of Professor Lakshmikantam. She showed that if you had ordinary differential equations, we can use comparison to obtain a scalar differential equation whose properties we know, and then we can reflect whatever properties that scalar differential equations has. We can get information about the system, the problem that we are actually interested in. So what I'm going to do is talk about a couple of different types of differential equations. I think I'm going to look at, let's say, integral differential equations, then delay differential equations, and impulsive differential equations, and time permitting, depends on how long I'm going to take to do all of this. I'll look at fuzzy differential equations. So we're going to start off, and the basic idea is still the same. If we have, say, for example, an integral differential equation, we want to use comparison theory to get a scalar differential equation. We should be able to get at least a scalar integral differential equation. Of course, the best of all worlds is if we are able to find a comparison equation that is an actual scalar ordinary differential equation. That is not always possible, but we can at least go from a complicated system to a less complicated problem of the same type. Vasu? Next slide, Vasu. Is she there? Thank you. So this is an integral differential equation. And since Vasu is doing the sharing, I'm not going to be able to use my cursor to point things out. And she's helpfully pointing out that there's a typo on this slide. So if we have an integral differential equation, looks like this. We have f prime is equal to, this is the differential part, this is the integral part. And so if we have an integral differential equation like that, again, our goal is to be able to find scalar differential equations that we can use as the comparison theorem for this. So there are many types of existence results. The one, and what I'm going to do is for each type of equation, I will at least give a comparison result, and then perhaps maybe an existence or a uniqueness or stability result using inequalities. So, okay, now in this integral differential equation, if we have that the p part is bounded by this scalar equation and the g is bounded by this scalar equation. So the idea is you go from the integral, you're going to be bounding by scalar functions. And then if you have, what's the next? And using those ideas, we had the f and the h, which dominated p and g. Using that, we construct this scalar differential equation, even though it is still an integral differential equation. And we can show that under the conditions listed in this theorem. We assume that the scalar differential equation has a solution. Then if we can show that the g function is bounded, the integral of the absolute value of the norm of the g function is bounded by some n, then as long as the norm of the initial condition of the integral differential equation is less than or equal to the initial condition for the scalar equation, then we find then there exists a solution for our original problem 8, which satisfies that the norm of x is always going to be less than or equal to w of t, where w of t is the solution of a scalar integral differential equation. Okay, what are we doing? So we'll give an inequality result. The interesting part in here is that in this case, the integral differential equation is an implicit implicit integral differential equation. And so we see here that P is the operator, and it depends on t, x, and y, and also on the integral. And so if we have the non-decreasing and non-increasing in different variables, these conditions, then this is the key condition. If we have that the P of the VV prime SV is less than 0, and for the W is bigger than or equal to 0, then as long as the V is less than W at the initial point, then we would have that the V of t will be less than W for all t bigger than t0. Professor Drisi mentioned maximal and minimal solutions. So here is a result involving maximal and minimal, showing the existence of maximal and minimal solutions. Again, we need the boundedness of the various parts of the equation. Okay. Move on, Basu. Next. So, never mind, skip that. Go to that dilemma here. So we have various differential inequality results. This one is a lemma that's required to prove a fairly complicated comparison theorem. But the reason it's still up on the screen as opposed to skip that, then is because in this lemma, we use the idea of the right maximal solution and the left maximal solution. So if you observe that the right maximal solution, it starts at t0 and moves on. Remember, the time interval that we are looking at is from t0 to cap t. But the left maximal solution has its initial point at the right end of the time interval, and then it works backwards. And okay, so if these conditions are satisfied, then okay, so this is what I was saying just a minute ago, that it has some interesting features in that it introduces the left and right maximal solutions. And again, the interesting issue is that one goes forward, the other one goes backwards. What is this theorem? So can I see the conclusion? Oh, again, this is a differential inequality result that if we find a D such that this is bounded by the right-hand side of the integral differential equation, then, and again, this uses, as I said before, the left and right maximal solution. So it says if eta is the left maximal solution and R is the right maximal solution of this problem, u prime equal to ft t0 u0, existing on t0 to infinity, then as long as this inequality holds at T0, then, Asu, next. What happened here? We didn't have the conclusion of that theorem. Yeah, so there it is. I couldn't see it, sorry. And so then as long as they have the correct order at the initial point, then M of t will be less than equal to R of t for t bigger than equal to T0. So again, we're looking at things being bounded by the right-hand side of the integral differential equation, the complicated equation that we're dealing with. What am I doing here? Okay, so here we are going to give the monotone iterative, give a result involving the monotone iterative technique for integral differential equation. And just so that we don't keep repeating the same old thing over and over, instead of looking at an initial value problem, we are going to look at a periodic boundary value problem. So if we have the upper and lower solution, was it 1 second, go back. We can show that the existence in this closed sector, right? So which is between the lower and upper solution. Okay. Next. Okay. So here is the monotone iterative technique theorem, I believe. So if we have upper and lower solutions that satisfy, again, the lower solution is less than equal to P at rho, and the upper is bigger than equal to P at theta, where rho at 0 is less than equal to rho at 2 pi. This is the lower solution. Upper solution has initially, it satisfies this boundary condition. Okay, Vasu, move, please. And this here is the condition. It's sort of like a one-sided Lipschitz condition, not quite, because now we have integral differential equation. But if this condition is satisfied, where for technical reasons you need these conditions, given that, you can find there exist monotone sequences, rho sub n of t and theta sub n of t. Starting with rho sub 0 is going to be the lower solution, theta sub 0 is the upper solution. And those sequences, the rho sequences, converge to the minimal solution of the periodic boundary value problem, and the theta sequence converges to R, and the convergence is uniform. So yeah, so you have that there, gamma and R are the maximal and minimal solutions, and the maximal and minimal solutions are going to be between the upper and lower solutions. What are we doing? Move on. I think we should hit the stability thing in this next. I think that's what we had. Okay, so we're going to then next talk about some stability results. And remember, as Professor Tracy said, in order to talk about stability, we have to have that existence of the zero solution. And so you have this integral differential equation where this x is the integral part of the integral differential equation. And we are assuming that the zeros has the zero solution. If these two things are true, then okay, so this is our integral differential equation that we are looking at, whose stability properties we want to find. And in order to deal with that, we go to, what's the next? And these stability concepts, so we're going to use Lapenoff method to talk about stability. And so if we have, again, as Dr. Drisi said, these are just sort of technical conditions that the Lapenoff function has to be positive, definite, and decrescent. And then if we have W0 and W as with W0 of TU being less than equal to W, and eta V0 is the left maximal solution of this equation, and R of t is the right maximal solution of this scalar equation. Then, and if the Lyapunov function satisfies this inequality, that is, V prime is less than equal to W, where W is the solution of a scalar differential equation, then we have that the V is going to be dominated by the left left minimal solution. And so if we have that, then the stability properties of 14, here, this is the scalar comparison equation. So whatever stability properties this has will imply the corresponding stability properties of the zero solution of the integral differential equation, the complicated equation that we were interested in. Okay. Okay, that's the 15-minute mark. Let's see, skip. I'm already at the 15-minute mark. Go to the next thing. Okay, so next we're going to look at what I call delay differential equations, and what makes this, what is the special characteristic of a delay differential equation is that the initial condition, instead of being something like x of t0 is x0, that is value at a point. In delay differential equations, the solutions depend not only on the present value, but also on some past history. So for each point t, there is a little tail going from, say, 0 to negative tau, or from t minus tau to t. And this definition of x sub t is, we define that to be x of t plus s, where s is between negative tau and 0. And so then the graph of x of t is, x sub t is just the graph of x shifted onto that interval. But again, the essential issue with this type of problem is that the initial conditions at every point is a function rather than one value. Okay. So we would have an initial, for each point t, there's a tail attached, right? So when these, the zero is the functions where the initial functions come from, and we define a solution of a delay differential equation as a function which satisfies the following conditions. It's continuous and defined from the end of the tail, and the left end of the tail, all the way up to whatever our right end point is, that the initial function is this, and the derivative exists and satisfies 15, which was on the previous page. Next, awesome. Okay, so that's what is called a solution. And so with this idea, we are going to, this is a local existence theorem that's proved using Schauder's fixed point theorem. So here we are not using comparison or anything, we're just going with Schauder's fixed point theorem. But having local existence and the comparison theorem then enables us to get to a global existence result. And here, this is where you get the comparison system from. Here you have Q is less than equal to, this G is a scalar function, right? It's a ordinary differential equation. And so then if R of t is the maximal solution of this scalar ordinary differential equation, then this Q is going to be less than equal to R, provided at the initial points, this inequality holds. Next. Okay, so this was, I said, using that we can get the global existence result. Let's move on. Again, here also you have that comparison here where you're comparing the f function to is bounded by a scalar function. Okay. Global existence. We're going to talk about stability in a bit, and so in order to have stability, we need to have that the solutions are continuous and differentiable with respect to initial conditions. Dr. Tracy had a theorem on that for the ordinary differential equation. This is analogous to that, except that once again we have the initial condition being a function. And again, if we want to talk about stability, we have to assume that the zero solution exists. And these stability definitions are parallel to the regular stability definitions, just modified to take into account that the initial condition is a function. So we take the norm, zero norm of this is less than delta, implies that the solution is going to be, the zero norm of the solution is going to be within the epsilon ball, right? And so this is an asymptotically stable definition, again, very similar to what Dr. Risi said. So I'm just going to look at a theorem involving stability, which is what's coming up next. Okay. Here we define the zero norm of phi sub 0 to be the value of phi sub 0 at 0. And then if we have that, thank you, if ft phi is less than equal to g of t and the norm of phi 0, then if the trivial solution of the scalar differential equation, which we had a couple of slides ago, which was a regular ordinary differential equation, and if the trivial solution of that ordinary differential equation is stable, then the trivial solution of the delay differential equation that we are studying will also be stable. 9 minutes. What is this? Okay, this is asymptotically stable, same kind of things. Okay, here we are going to present a generalized quasi-linearization result. Both monotone iterative techniques and quasi-linearization, they give us, the process gives us approximate solutions that converge to either the unique solution or the maximal and minimal solution, depending on the conditions. Here, we are going to look at the difference between the quasi-linearization and monotone iterative technique is that in quasi-linearization, you get quadratic convergence. And so, of course, if you are looking for more, you have to assume more. So in this case, where's the condition? So here, in addition to the conditions that we had for F in the monotone iterative technique, we also have a Lipschitz type of condition on F sub phi, right? The Cauchy derivative of F. And here, this beta is any constant bigger than 1. If it's 1, you have linear convergence. If it's 2, you have quadratic convergence. Under this circumstances, you get not quadratic convergence, but you get, what's the next one? Superlinear convergence, right? Okay, so not quite quadratic, but better than linear. Okay, skip. I think we're going to move on to impulsive next. Okay. Well, I was going to talk about stochastic and random, but that requires so much machinery to set up even some basic results. So I'm just going to skip that. Okay, so that brings us to impulsive differential equations. These are differential equations where the right-hand side is not continuous but has jumps. The ftx has jumps at some given times. There are two types of impulsive differential equations. One is where the jumps are given at fixed times. And so here it is the fixed time. So within the interval t sub k to t sub k plus 1, this is just an ordinary differential equation. Then you get the jump at t sub k plus 1. And then from there, then you have another initial value problem on the next subinterval. So this is the kind of picture you have. The solution goes, then it jumps up, and it is left continuous. The other type of impulsive differential equations are where the variable moments of time. These equations are much more complicated to work with because the jumps occur at times that depend on the solution itself. And because of that, it can lead to all kinds of undesired things like pulse phenomena happening. So for a while there, after this notion, after Dr. Lark's book on impulsive differential equation, there wasn't that much work being done, but lately there seems to be a resurgence in this idea. So it's a much more rich theory than for the fixed time, but hey, fixed times are good because since the solution, since the differential equation is an ordinary differential equation within each subinterval, and then you just have to make sure that you take for the next subinterval, the initial condition is going to be the jump. And because of that, you can treat each subinterval as an ordinary differential equation, and whatever relationship, whatever properties you have can then be extended to impulsive differential equations as long as you have jumps at fixed moments of time. And but the problem, just as Dr. Tracy had said, that as soon as you put impulses, even though, I mean, in principle, it's not that complicated, you're just looking at jumps and ordinary differential equations within the intervals. But let's look at a very simple inequality result. This is a linear inequality. So here's inside the intervals, this satisfied m prime is less than or equal to p of t times m of t plus q of t. And at the jump points, this is what defines the jump. Now, with that, we want to get an estimate on, are we doing something else? So we want to get an estimate on m. And as you can see, we get this terrible looking equation, which sounds like it's some really deep result, but it's not really, because as long as you work interval by interval, you work on the first interval, then you would get m of t satisfies this on the first interval, then you move on using the initial condition for the second problem. second interval, and you develop this, which looks, like I said, it's a humongous expression, but to obtain it, it's just you go step by step. You show it on T0 to T1, then you show it on T1 to T2, and so on, and then you can establish that it is true in general over the entire interval from 0 to whichever T we are going to, okay? So as you can see, even something simple as linear inequality looks quite complicated. And so because of that, I'm not going to present any more results in here, except I just wanted to mention something that generally when we look at initial value problems, we assume that comparable solutions start at the same time, but this doesn't necessarily have to be the case. And so it could be that one X starts at T0 and then another solution starts at some tau 0. And then when we're going to talk about, we're left with the problem of comparing solutions with different starting times. And so that resulted in a few papers talking about solutions with initial time difference. Where is it? Differential equations with initial time differences. And in this particular case, we are talking about also not only the initial time difference, but if the differential equation is perturbed. So we are combining two notions of initial time difference and perturbation, which, so if the unperturbed solution starts at, say, T0, and the perturbed solution starts at some other time tau sub 0, then you would have a situation as follows. Okay. So this is the unperturbed solution starts at T0 plus. This is the perturbed solution, which starts at tau 0 plus. So when we have to work with this kind of thing, you have to take into account not just the difference in the values of x, but you have to put some kind of bounds on the difference between T0 and tau 0. Okay, having said that, we won't go through this is from a paper done by Yakar in Turkey. It's quite complicated in building up the steps. We can skip Lifshitz inequality, stability. So let's go to fuzzy. Okay, stop. Okay, and so the last type of equation I'm going to talk about is fuzzy differential equations. And fuzzy differential equations arise when, in general, we assume that the parameters, variables, and initial conditions are defined exactly. Whereas in reality, this might not be the case. And so in fields such as robotics, artificial intelligence, and language theory, it requires a new theory, a different theory to deal with this such imprecise parameters. And so in 1965, Zade initiated the development of a modified set theory in which he defined the concept of a fuzzy set, a tool that makes possible the description of vague or imprecise notion. So a fuzzy set basically is, well, let's give an example. If you had a set of all red balls, that's a crisp set, right? You take the red balls and a ball either belongs to the set or not. On the other hand, if you look at a set of all reddish balls, right, there you have the fuzziness because you would have a range of reddishness. So that's the kind of thing that fuzzifies the problem. And so you talk about a memberships function, which tells you, which gives you a range on 0 to 1, and at 0, it's really far away. And then when the membership is 1, it basically the crisp end of the solution. So spaces are, okay, and these fuzzy sets are function spaces with some special properties. And again, we're going to be working in convex subsets of Rn. And this is going to be pretty, when Dr. Devi talks about set differential equations, you're going to see similar things being required. But again, what we want to do is we want to take, let's look at the fuzzy differential equation. Oh, and then we define the distances between those fuzzy sets in terms of the Hausdorff metric. And so if we have a fuzzy differential system like this, then what our goal would be to be able to find a comparison equation to this, which is a scalar differential equation, and a scalar differential equations whose properties are known, and therefore we can get information about the, and so here is where the scalarness comes in, right? Here is, back up a little bit for the PTU, PTV. So if we have that the distance between P at U and V is less than equal to L times DHUV, this is again sort of like a Lipschitz condition. Then in this case, the initial value problem 24, which is the fuzzy differential equation, will have a unique solution. And again, what we want to do is, using this kind of idea, establish a comparison equation, which is a scalar differential equation. And something different here that we need to talk about is when we're looking at the scalar, back up, weighted norm. Yeah, so here we have to use a weighted metric. So this is something new that you need to do in when we're dealing with fuzzy differential equations. And having said that, we now have a bunch of comparison results, which if you're interested in, you should look at the book on fuzzy differential equations and inclusions by Professor Lakshmikantan and Mahapatra Rao. And with that, I will let Dr. Devi come up with her contribution. Thank you for listening. No, that's okay. Boundedness. I'm already 6 minutes over time, so forget. We'll not talk about boundedness. You can just end it, Vasu. And now Dr. Devi will take over and talk about set differential equations, fractional differential equations, and several other types.
Dr. Vasundhara, may I request you to continue the presentation, the third part of the presentation?
I could do it. Hello, can you hear me?
Yes, ma'am, you are audible now.
Okay, so I'll again start sharing my screen. Well, thank you. I sincerely thank the organizers for giving us this chance to share our whatever little knowledge we have. And also I thank Dr. Dreesy and Dr. McRae for making my job easy by explaining all the stuff. So I'm going to take the, they've been very nice, so they're making my life easy. And so I'm going to start with the part 3 of set differential equations. As I said at the outset, I would like to thank the organizers for giving me this opportunity. I guess I have to show my face, or is it not necessary? Do I need to show my face or not necessary? Okay. So this is my face. I'm going to share the screen. Okay. Can you see the screen?
Ma'am, yes, ma'am, yes, ma'am.
Okay. So what I thought was I will go a little easily, in the sense that I would like to make it as simple as possible. So as I said, we'll start with set differential equations. But how does that concept arise? Because till now we are either working on R or Rn, which is a vector or a scalar, and suddenly we are jumping into a set. So is there any motivation behind this? So let's take a simple example where someone is suffering from cancer and they have to do radiation or give chemotherapy radiation on the part. So suppose, or if they want to do a surgery on that part, remember they just cannot do like a point. They need a set over there, like a small disc or something. They would radiate and then they would try to cut the tumor. So the concept that you cannot work with a single element, but you need to take a group which has some regular structure, allows us to the concept of a compact convex set, and that is the KCRL. So if you take the intervals as the basic sets, closed intervals, let's say, then you're in KCR. And if you take this circular discs, closed circular discs, then you'll be in KCR2 and so on. So with this structure, once you have sets in place, I guess all of you are familiar with the Minkowski addition, but I'll just, for the sake of completeness, I'll just quickly go through this. So when there are two sets in KCRN, you add them pointwise. A is in A and B is in B. And if you have a lambda is any positive scalar, then you have lambda is the set where each element of A is multiplied by lambda A. And this gives us the semi-linear space setup because we are only working with lambda positive. Now, once this setup is there, then if you want to proceed further, especially if you want to consider the derivative concept, then we need the difference, because you know that in ordinary differential setup, we have x of t plus h minus x of t. So the question arises, what do we mean by difference in this setup? And that is a very complicated question because defining set difference is not that easy. So it is defined in terms of, we always use the positive setup, like this set differential equation is one place where you're always positive. You are never negative in any sense. So what happens is we start with a set C, and if we can find another set E when such that D is equal to E plus E, then we say that E is the difference of, or a difference of C minus D. I should not write this minus. So C minus D. Then remember that always we are interested in the positive setup of cones. So what do we mean by that? Because that means we need a partial order. So we want to work with inequalities, which is the Dr. setup. And if we want to work with inequalities, we need to somehow get that setup over in the set of in the space of KCRN. So a partial order is defined, and the way we define it is you take any set U where each term in U, which is a vector in Rn, is always positive. That is, the terms u1, u2, un are always positive or greater than or equal to 0. Then if you can find a set which is equal to d plus u, then we say that C is greater than D if all these ui's are strictly greater than 0. If some of them are equal to 0, we say that C is greater than or equal to D. Now, with this setup, we have the partial order. So we can start about defining the Poujara derivative, which is the concept that is used in set differential equations. And the noun that is used is the Hausdorff distance, as is in fuzzy differential equations. So the basic setup of fuzzy differential equations and the set differential equations is the same. And actually, we have a what is called as a relation between fuzzy differential equations and the set differential equations, which is there, but we will not go into it. Okay. So I have finished the basic structure that is there. This is the partial order that is defined. And this is the necessity of defining the Poujara differences to construct the concept of a derivative. So with this in place, we define that the same notion as that of an ordinary derivative. But you have to see that this is the right hand side and this is left hand side. Both of them should exist, and if they are equal, then the Poujara derivative exists at that point T0, and we write it in this fashion. Now, once this setup is in place, we define the initial value problem of a set differential equation, which is given by this. And now we follow Professor Lakshmikantam's technique and establish the basic comparison principle. You again need to check if x and y are any two function elements, I guess, when Kc are in. Then if this Hausdorff distance between p of tx and p of ty is less than or equal to a scalar valued function, this is again a scalar. So you're actually trying to convert the complicated set differential equation problem into a scalar differential equation over here. So if once we have that setup, if x of t and y of t are any two solutions passing through t0, x0 and t0, y0, then the distance between x of t and y of t will be dominated by the maximal solution of the scalar differential equation. So this is one major, this is one comparison principle that we have over here. Now, what I would like to do is I would like to go and present the generalized monotone iterative technique, which we haven't done till now. As we have said, we would like to give different concepts that have been developed by Professor Lakshmikantam's group, and this is one setup. So here we consider instead of p of tx, we take another function q of tx. So p and q have different behaviors. So let me go down a little. We introduce first the concept of various concepts of upper and lower solutions. So I'm going to show you the important parts. You remember the equation one we have where this is an equality with p of tx and q of tx. That's what we started with. Now you have the less than or equal to inequality to get the lower solution. Greater than or equal to inequality have the upper solution. Here when you have x on the left hand side, there is x on the right hand side of p and q. Similarly, If there is y on the left hand side, you have y on both sides. This is the natural setup of lower and upper solutions. Therefore, it is called as natural lower and upper solutions. But then they introduce different types of lower and upper solutions. This is what is called as generalization or refinement, maybe refinements, because they have introduced a new concept called as coupled lower and upper solutions of type 1, where if you have on the left hand side x, the p has the x but the q has the y. And when you have y on the left hand side, the p has the y and the q has the x. That means in each differential equation, both x and y are coupled together. Therefore, it's called a coupled lower solutions of type 1. Now, if you want to, there's also a type 2 and type 3. The type 2 will be opposite of that of 1. That is, if you have x on the left hand side, the p will have a y and the q will have the x. And if you have, this is with the less than or equal to inequality, and if you have the y with the greater than or equal to inequality, then the p has the x and the q has the y, which is the reverse of what we had at coupled solutions of type 1. So this is called as coupled lower and upper solutions of type 2. And the coupled lower and upper solutions of type 3 are, you can expect what it is. When there is x on the left hand side, you have total y. And when there is y on the left hand side, you have total x on the right hand side. So these are coupled lower and upper solutions of type 3. Now, if we make an assumption that x is less than or equal to y of t, that is, if you assume that x is the lower solution and y is the upper solution, then all these four setups reduce into the type 1 and type 2. So we only study the cases of type 1 and type 2, the natural lower and upper solutions, and the third couple solutions of type 3 reduced to type 1 and type 2. So our work is reduced because we always work with lower and upper solutions. Now this is the generalized monotone iterative technique. As we have said, we start with the lower and upper solutions. Here we are working with type 1 coupled lower and upper solutions. So you assume that P is non-decreasing and Q is non-increasing. And because we are in the space of infinite dimensional space, we need the condition that P and Q map bounded sets into bounded sets. Then we conclude that we can obtain sequences xn and yn which are converge, xn converges to rho of t and yn converges to r of t, where rho and r are coupled maximal and minimal and maximal solutions. So what happens is they satisfy the equation. You observe here, you have dh rho minimal solution because it's type 1, you have p of t rho and q of tr. And you have dhr, it is p of tr plus q of t rho. And they satisfy the initial value theorem. So this is the generalized monotone iterative technique for set differential equations. Now there are various, as I said, you can actually do lots of refinements over here. And if you want to look at the set differential equations textbook, which is I think the reference 43, you can see that there's a lot of work done over there. And there is another concept that is what is called as an epsilon approximate solution. This epsilon approximation solution comes up when because if you remember differential equation, it is dh, let's say I put y is equal to p of ty. So if you take this difference, whereas this difference in the sense of set differential equations, you cannot have the difference, it is only the distance between, positive distance between dhy and p of t, y of t. If this distance is less than or equal to epsilon, then this y, which has the initial value y0, will be called as an epsilon approximate solution. And if epsilon is 0, clearly it becomes a solution. Now there is another concept of what is called as an Euler solution. Now there is a comparison theorem. The existence of the epsilon approximation solution is established using the maximal solution concept. We will leave this for present. Oh, okay. Now what we have over here is another stability concept. I'm going to just show you the ideas over here. The proofs are quite complicated, so we will leave it to save time. Or rather, in fact, it's very difficult to explain also. So normally when we were working with stability, till now you have seen results on R plus cross S rho, where S rho is the space for X. But here what we are going to do is our X will be the set S row intersection S complement of the eta set. So it's like you're going to work in an annulus. So the region is smaller than the usual R plus cross S row. You have different conditions and you use perturbing Lapenoff functions, which means that you're going to use more than one Lapenoff function and get a setup. See, you're going to have the d plus 1v. It will have a condition on S row. Then you take a v eta, another function that has a condition on S row intersection S complement eta. And then this satisfies the the standard Lapenoff function conditions, including the Lipschitz. Then we have of course, there is a relation between all the two functions. Then we have that you again use the comparison equation and you say that you use two comparison systems over here and show that the zero solution of the set differential equation is equistable. There is also this bounded concept, but we will leave this because we'll be in constraint of time. Now, let me go to fractional differential equations. As all of, I guess there's no one right now who does not know a fractional differential equation. People have been working so much in that area that everyone has to write at least one result or prove one result in this area. Now, the idea, as all of you know, came up with the notation introduced by Leibniz. I'm sorry if I'm repeating because most of you know it. I'm just doing it for completeness sake and I'll finish off in a minute. So this was the introduced notation introduced by Leibniz when for the nth order derivation of function of t. Then L'Hopital said what will happen if n equals to half, and that roused the interest of all mathematicians of that time. So you name any mathematician worth his name has worked in this area. But what happened was the people were working in this area for a long time. In fact, there are many there is also a popular book by, I think, I'm forgetting his name, which has actually helped in the development of applications in the fractional differential equations area. I'm sorry, I'm forgetting that name right now. So with applied people started working using fractional differential equations. But as far as we are concerned, Professor Lakshmikantam introduced the concept of fractional differential inequalities and wrote his famous book, Fractional Differential Systems. Actually, he wrote it at Vizag and has been kind enough to put me as a co-author. We worked together in that area. So with that, even our group also started working in fractional differential equations. But the first few papers were by Professor Lakshmikantam and Dr. Vatsala in this area. In fact, they got the fame of maximum downloaded papers. Their two papers became very famous. So there are two derivatives that are important over here, Caputo fractional derivative and Riemann-Duval derivative. Let's just look at this. So the definition of a Riemann-Duval fractional derivative is of this type. You can understand that it is a generalization. I don't have time, but the way this derivative comes up is very interesting. You have the Cauchy derivative where the n integrals can be reduced to a single integral. That concept is used, and wherever n is there, they put the fraction, and you get n factorial over here. So because they're generalizing, gamma is a generalization of factorial function. In place of the n factorial, you get here, they put a gamma p, and where you have an n over here, when there are n derivatives, they changed it to p, which is a fraction. And that's how the fractional derivative was introduced. Integral was introduced first. Then the derivative was introduced using the idea of if you have d power q, you can write this as d power m plus alpha, where alpha is the fractional part and m is the integer, and write this as, no, actually you can write d plus m plus q plus minus m. And this m stands for derivative and minus m stands for integral, and they use that concept to come up with this integral, which is a fractional, we came up with this derivative, which is the fractional derivative. You can observe that d by dt is the derivative outside, the integral is inside, which I have told you now, the concept. Now, instead of taking the derivative outside, if you can shift it to inside, this becomes m prime of s. And what happens if you have m of t as a constant, then in case of Riemann-Liouville derivative, when the derivative is outside, the integral is inside, the dqm of t or the Riemann-Liouville derivative constant is not 0. But when you use Caputo derivative, you have m prime of t, which will make it 0. Therefore, the integral becomes 0. Therefore, the Caputo derivative of dqm of t is 0, of a constant is 0. So, it reduces to the ordinary differential equations. And all of us know that we are very happy when we get something that we are familiar with. So people were very happy with the Caputo derivative, and there's a lot of work done on Caputo derivative. So here what happens is we need to observe that any result that is done for Riemann-Liouville fractional derivative will hold for Caputo derivative, but the converse is not true. Now here I am going to introduce you the concept of Euler solutions for the Riemann-Liouville fractional derivative. So what we do is let me go, it's easier to work with this thing. You have a partition, say, of t from t0 to t. You break it into parts, and you take the fractional derivative dqx is equal to say p of tx, and with the initial value x at t0 is equal to x naught. So you take one partition, call it as pi, and the interval t0 to t1 in place of x naught you put, in place of x you put x naught. It becomes a constant fractional differential equation, and therefore you can solve it, and then you use that value to get the arc from t0 to t1. Now at t1 you calculate the value x1 using the solution. Now you place this in the x with x1, then you get another constant differential equation, and then create the arc. It's same thing as we do for Peano's theorem, where you construct the arcs and proceed to get the solution. So for each pi, we are going to get one solution, one arc, which is called as Euler arc. It's x pi. Then as you change the partitions pi j, where the length of this interval is going to decrease, maybe going to 0. Then if the solutions x pi j converge to a function x, this is what is called as the Euler solution. I hope I'm clear. So with this Euler solution in place, we have a result again using the comparison theory. Once you know that this is all the explanation that I have given, this is the Euler solution definition. You have the Euler curved arcs x pi j. So as the diameter tends to 0, you have the solution. Okay. So with this in place, we have the theorem, which again we use the comparison technique. That is, we already have a solution whose behavior is already known. We take a fractional difference. See, here we are not taking a scalar fractional differential equation. We are taking a simpler scalar fractional differential equation. This P is an Rn, so a fractional differential equation which is an Rn is being reduced to a scalar differential equation, scalar fractional differential equation in R, and we are going to use its behavior to say that the existence of a Euler solution holds. Now we have a result involving perturbed Lapenoff functions. Maybe I have to talk about variational Lapenoff method for the simple reason that Dr. McRae has given this concept. So you have Q of Ty is here you are not using any time difference they are starting at the same time. There are results where they start at different times too, but we are giving the simpler setup. So you have dqy is equal to p of ty and q is dqx is equal to q of tx, and let us assume that one is the perturbation equation. I guess that's what it is. Now we are going to, as I said, variational Lapenoff method. So you have to introduce the Lapenoff function, and also you have to use the variation of parameters formula. And quickly I'm going to show you where we have done that. Normally when you write d plus q, v, it is s x of s or y of s. But here what we are doing is, basically I think it's going to be, let's see. it's x of t t0 x0. But what we are going to do is, sorry. We are going to use here. I'm going to write this. So here it's going to be y of, in place of this, you have t naught x naught. Now remember, when we are in our undergraduate students, or we teach undergrad students, the variation of parameters formula for second order differential equations, where in place of x naught and y naught, we put u of t and v of t and try to find the solution for the non-homogeneous differential equation. The same idea is used. That means we replace the function in place of initial values. So in place of t0 and x0, we replace them with values s and x. Oops. Values s and x. So this is where the variation of parameters is used, and this is the Lapenoff function. So it is called as the variational Lapenoff method. The structure of partial fractional differential equations is very complicated, so you get a whole messy setup, and we won't be having time to deal with all this. So we will leave it at this, and I guess we will go to differential equations with retardation and anticipation. How much time I have? Can someone tell me, please?
Another 5 minutes maybe.
Okay.
Yes.
Okay. So differential equations with anticipation and retardation is came by a Caldera-Calesi model. This was started. Okay, maybe I will go through this. So what we do here is, we have x prime of t is equal to t x sub t. This x sub t deals with the anticipation stuff, and as we can always observe is that this anticipation is not known. You want some anticipation. You want to achieve something, and you have your goal, but you have to proceed from the t0. Let's say, so suppose you start at t0 and at t you want to achieve this goal, then you have to find this approach. So what we do is we make some estimate and then find a solution with this estimate and try to reach. So this estimate is something as, in place of the unknown x, we put some z of t or z of t, and using the z of t, it all becomes an ordinary differential equation, and we try to solve it. This was the first approach that was done on anticipation, one of the first papers. Later on, we added anticipation and retardation. So because there's always a past history to anything, so this is the tail retardation, t minus tau region. This is the tail, and this is the anticipation at t. And you have a differential equation of the type x prime is equal to x of, sorry, I'm so sorry, x prime equals to some p of t x unknown x sub t, that is the delay, and x sub t, that is the retardation. And of course, there's a lot of theory that has been developed. In fact, we have done quasi-linearization for this setup. And I think actually one of my colleagues has done, I think Dr. Sridhar had done integral differential equations for using anticipation and retardation. Now there are two more areas. I'll quickly go through them. We also have worked on what are called as matrix differential equations and graph differential equations. The idea of a graph differential equation comes up with that of the work of Ciliac. Remember that a graph always, when you have any network or any social problem that has internal interconnections and networks, interrelations, it can be represented by a network, and every network can be represented by a graph. So a graph basically represents, has a lot of information in it, and a static graph would not be that useful. So Ciliac introduced the idea of a graph that changes with time. So you have a graph that changes with respect to time, and therefore the concept of graph differential equation was introduced by him. And he also studied the stability of a prey-predator model. Then we had a NBHM project on this setup, And so we introduced what is called as a pseudograph. And then we developed the basic theory of graph differential equations. And also because there is an isomorphism between a graph and a matrix, we use this happily, conveniently, and developed the theory of matrix differential equations and graph differential equations together. Now, finally, I would like to introduce one concept, which is called as stability in two measures. So, give me 2 minutes, Dr. Srinivas, and I will be done with this, because that's one concept that is hasn't been touched by any one of us. So, let me go till that 65, say. So, there is, okay, let me see this. 1 minute and I'm done. So we introduce what is called as two measures. That is, say if you are in two different spaces, then for example, we are working with delay differential equations. Sometimes we are in C row and sometimes we are in C. So if that is the case, you need two different norms. And that generalization was done by introducing two measures, because a norm can be considered as a measure. So you have H0 and H. These are two different measures. So in one space, that is in the initial space, it is H, and in the others, in the different space, it has a different norm H. So combining these two, they introduced what is called as a differential stability in two measures, the concept. And there is a book by Dr. Lu and Dr. Lakshmikantam on this, the theory of stability theory in two measures. It's a very interesting concept. These two are related by a concept called that H naught is finer than H. So there is a lot of work. It's a very wonderful area where there is a lot of work that has been done, and whatever we have showcased is just what should I say, a needle in the haystack, or maybe because there is a lot of work. So let me conclude. In conclusion, it is the concepts of differential inequalities and comparison principle and iterative techniques using upper and lower solutions are powerful tools for studying a wide range of differential equations. The results presented in this talk are only a sample of the vast amount of research being done in this area. More complex phenomena were modeled by combining these types of differential equations. For example, delay differential equations with impulses, set differential equations with delay and impulses, impulsive fractional differential equations, impulsive fractional integral differential equations, impulsive fuzzy differential equations, and so on, to name a few. Well, I once again thank you all for giving us this wonderful opportunity to share the work that has been started by Professor V. Lakshmikantam, of which we are a part. We are so proud of that, of course. And once again, I thank you all, thank the organizers, and I also wish Dr. Ravindranath Babu, on behalf of all of our team, a very happy superannuation, and I hope he will continue doing his wonderful research work. Thank you all. Thank you once again. Sir, I'm stopping my sharing the screen.
Any questions? Okay, in the absence of any questions, I thank profusely all the three speakers, Dr. Drissi, Dr. McRae, and Dr. Sundhara Devi, for their wonderful presentation. It was very elaborate presentation of so many essential aspects and fundamental aspects associated with differential equations like integral differential equations, fuzzy differential equations, delay differential equations, impulsive differential equations, set differential equations, fractional differential equations, matrix differential equations, graph differential equations, many more. It has given a very broad outlook of what is happening right now. I'm sure this is of great use for all those youngsters who wish to take up a beautiful work and take it forward. Many thanks, madam, to you and as well as to your colleagues. It was a great presentation. We appreciate it a lot.
Thank you very much, sir. Thank you very much.
Okay. Next program.
I invite Professor T. Song, IIT BHU, Varanasi. Please deliver a talk, sir. I welcome you, sir. Now I request Professor B.S. Thakur, please share the session and by giving brief introduce about Professor T. Somugaru. Sir, please welcome, sir.
Thank you. Thank you.
Thank you, sir.
So it's my pleasure to introduce my friend Professor Tanmay Som. He is presently Professor and Head in the Department of Mathematical Sciences in the Institute of Technology, BHU, Varanasi. He has very vast experience of more than 35 years in teaching and research. His research areas are functional analysis, fuzzy set theory, mathematical and optimizational modeling, soft computing, image processing, etc. He has guided 16 PhD students for PhD. 8 students are working under his able guidance. He has more than 100 publications in national and international journals, 6 book chapters he has also written in his record, 1 edited proceeding, number of invited talks he has delivered in India and abroad. He visited many more countries like Texas A&M University, USA, and Thailand, and Berkeley, USA. He has completed number of projects. He was previously head of department in Assam Central University, Silchar. He has organized a number of programs, conferences. He is editor in number of journals. So this is few of very vast biodata of Professor Tanmay Som. With this brief introduction, I request Professor Som for his talk. Professor Som, please.
Yeah. Hello.
Yes, please.
Yeah. Are you getting me?
Yes.
So thank you very much, Professor Thakur, for introducing me, for having a nice introduction. And also I give my special thanks to Professor GVR Babu for inviting me to deliver a talk on this international conference. Okay, important occasion. And this is really a great thing that at the time of retiring, he has organized a very big conference, and his vice chancellor has already awarded to continue his research collaboration with the university. Very nice. And so today I am going to talk on some, let me share the slide. Is it visible, sir?
Yes, sir. It is visible.
Okay, so my talk is on few recent fixed point results with some applications. Okay, these are not more recent, but yet some recent. That means within last 10 years, some developments which have taken place. Okay, last just 1 decade. So I have given like this. We have introduction, some single valued mappings, multi-valued mappings, some couple fixed point. Of course, I will not cover because I'm given only half an hour time. This was only for 45 minutes. So I will deduct some of the things, and then I will then applications and references. So already we have heard last 2 days. Really, it was a good event that many people have, many experts have talked on fixed points, their applications, convergence schemes, then numerical schemes, and stability. Going to add something there. So most of the scientific resources acknowledge that metric fixed point theory was initiated by Banach, although there are instances of fixed point theory which can be found in the papers of Liouville. Okay, This is earlier than 1922. The fixed point theorem, which was provided by Banach, then be provided. Okay. The main success of the Banach is the abstraction of the successive approximation. Okay. In these earlier results, and provide an elegant self-contained fixed point results in the setting of a complete normed space. Based on this observation, in some sources, the well-known Banach contraction principle was called the Picard's Banach contraction or Picard's Banach theorem. It is an indispensable fact that the approach of Banach strongly affected the nonlinear function analysts. Okay, both the statement and the proof of Banach fixed point theorem were expressed in a perfect way. The theorem not only guarantees the existence and uniqueness of the fixed point for the contraction mapping, but also indicates how to find the desired point, okay, desired fixed point. The certainty of the method brings a wide application potential not only in various branches of mathematics, but also in distinct disciplines, including economics, computer science, and so on. Sometimes we use even in image processing. Nowadays, the techniques are developed. Okay. So let F be a mapping of a non-empty set X into itself. Then F is said to be a fixed point or said to have a fixed point if there exists some U such that U in X such that Fu is equal to U. Okay. So this fixed point theorem admits, okay, by fixed point theorem, we mean that there exists some fixed point. The mapping admits a fixed point. And here the Banach actually stated that the contraction mapping satisfying the condition dfx fy less than alpha dxy for all xy belonging to x, where x is a complete, okay, either metric space or a Banach space. Okay,
Professor Som, sorry to interrupt you. Just can you increase the zoom of your presentation? It is quietly very small.
Okay, now is it all right?
Yeah, it's perfect. It's perfect. That's good.
Sorry, I forgot to zoom it. Okay. So what you are getting here, something, okay, let me remove. So this is the main condition, contraction condition, and alpha is the factor, okay, Lipschitz constant, okay. So this ultimately there were some silent observations during 1922 and 60, very few results. Not much attention was given, but only during 1960, again, it became a hot topic. And then Edelstein proved a theorem for contractive mapping, stating that if F is an epsilon k uniformly locally contractive mapping of a complete chainable metric space X, then F has a unique fixed point. And U is nothing but it is the limit of Fn x naught. That means F is acting on x naught n times. And if n tends to infinity, then it is going to the fixed point, converting to the fixed point. Further, in 1962, Edelstein proved a theorem on the convergence of fixed point, is stating that F is a contractive self-map of a metric space X, and there exists some x naught in X such that F and for any x naught, if I choose, and if I take this sequence F and x naught, okay, F iterating over x naught, okay, has a convergent subsequence converging to some U, then U is also a fixed point. Okay. Initially, it was nothing but it was going directly to the fixed point f and x naught. And if I took any x naught, if a subsequence converging to some U, then U is a fixed point. So there are many developments during last 5 decades. The results of Kanan, Boydan, Wong, Singh, Wright, Hardy and Rogers, Hadjic, Chatterjee, Sirik, Hussain and Sehgal, Wong, Khan, Som, so on there are some significant results. Okay. So other similar theorems are obtained by Kanan, Wong, and Gobil, Kark, and Shimi, and many others in other using using non-expansive mappings. Again, in 1953, Mann gave an iteration scheme for convergence to the fixed point mappings. Of course, Kanan, Wong, and Goebel, Kirk, they gave an theoretical development for expansive mapping. Mann gave an iterative scheme. Okay, convergence scheme was further extended by Krasnoselevsky, Kirk, Ishikawa, Bose and Mukherjee, etc. Also, so have developed some developments have been there. Okay, for non-expansive mapping. So existence theorem are often expressed in the form of fixed point principle. Fixed points and fixed point theorems have been an important tool in the field of differential equations, economics, game theory, dynamical system, control theory, and broadly it is a major theoretical tool of functional analysis. So nowadays this fixed points principle is applied not only in differential equations, now it is in integral equations and others. Okay, and very recently in 2014, Twardowski proposed a new relation between dxy and dtxty. Okay, where t is a self-mapping of a metric space xt. Using an auxiliary function from, now it is not from x to x, now we have a function from 0 infinity to minus infinity to infinity, satisfying open interval, the whole real line. Okay, that satisfies certain condition. Roughly speaking, Twardowski proved that every f contraction, capital F contraction, has a unique fixed point where the f contraction is defined with the help of aforementioned auxiliary function f. We'll define it just now. Clearly, for the proper choice of auxiliary function f, okay, the Banach contraction principle is concluded. So this is an extension of Banach contraction. So there are some notation. So capital S the set of positive integers and 0 is the non-negative integers. R is the set of real number, R plus is the positive real numbers, R0 plus set of non-negative real numbers. X is any non-empty set. Okay. Now, in the metric space setting, what we have, so let this particular function f, what we are talking about, this capital F, that is my auxiliary function f, we take from R plus to R, and now with the following conditions, that this f is strictly increasing. Okay, that means whenever epsilon xi is less than eta, f xi is strictly less than f eta. Every sequence tn positive real numbers which converges to 0. Okay, if tn converges to 0, if and only if, that will imply that if tn converges to minus infinity. Okay, both way. And there is, or there exists some k in interval 0, 1, such that there is open interval 0, 1, such that if limit when t is tending to 0 from right hand side, that multiplication of t to the power k f is 0. Okay, the set of all such functions defined above is denoted by now this capital F, that is okay. And so we have this capital F, that is a class of functions f1 to f3. Okay, so these are all my auxiliary functions, and there are some examples here of such auxiliary functions. If I take, say, f1t is equal to, okay, ln t, okay, or t plus ln t, or minus 1 by root over t, or ln of t square plus t. So all these four, on f2, f3, f4, they are they satisfy the above class. Okay, so they are this class of auxiliary functions. Now, the actual theorem, which gives you the fixed point here. Let xd be a metric space. A map t from x to x is said to be an f contraction on xd if there exists this mapping f. Now, if this f belongs to this class capital F, okay, and there exists some tau greater than 0 such that for all xy in x, dtx dy greater than 0 implies tau of, okay, tau of q plus f d dx dy is less than f dxy. So this capital F plays an important role here. This capital F plays an important, I think, why, just wait. So this capital F plays an important role here. And then this tau is also a controlling factor here. Okay. So this is the generalized contraction. Okay, this is the generalized contraction here. In the sense of Banach, you can say. Okay. Now, the theorem is that let T be a self-mapping of a complete metric space Xt, and if T forms a F contraction, then it possesses, if T forms an F contraction, then it possesses a unique fixed point U. Moreover, for any x belonging to capital X, the sequence T and X also converges to U, also converges to U. So this is a very important result. Then based on this, we have next result that let I have an auxiliary function f to this class is continuous, and suppose that xd is complete, then for every n greater than 0, now I have a sequence of mappings from x to x be a contraction and Zn be its fixed point. So Tn is having a fixed point Zn, T1 is having Z1, T2, Z2, and then if Tn converges to pointwise to some map T again from x to x, and infimum tau n, okay, infimum over n is greater than 0. Remember that all these tau n were greater than 0, so infimum is also greater than 0, where Tn is a constant associated with Tn, and then from 1, okay, as we have defined it earlier, then T is an F contraction. Okay, so wherever this Tn converges to this another mapping T, that is also a contraction. Okay, and if Zn is convergent to some Z, okay, then Tz goes to Z, Tz goes to Z. So these are some beautiful results. Then we have another generalization of the same. We take the help of what is called a very, very general Hardy-Rogers type. Okay, generalization, Wardowski's type. This is Wardowski's type. Let Xd be a complete metric space and T be a self-mapping of X, and capital F is a class, auxiliary class of functions tau in R plus, such that T is an F contraction of Hardy-Rogers type. This is a classical Hardy-Rogers type, and now you have, instead of classical Hardy, now you have this Wardowski's type. Okay, tau plus f d tx dy is less than equal to f, capital F of now. Okay, alpha d xy plus beta dx dx plus gamma d. Okay, this relation for all xy belonging to x, and with this condition that tx not equal to ty. And alpha plus beta plus gamma plus 2 delta is equal to 1, gamma not equal to 1, and L is greater than 0. Okay, this L here factor is greater than 0. Then T has a fixed point. This L is greater than 0. T has a fixed point, and if, moreover, alpha plus delta plus L is less than equal to 1, then the fixed point is unique. Okay. Now, we have another definition. This is another unifying category, unifying type of. Let Xd be a metric space, a self-mapping. T is said to be F weak contraction. Okay, if there exists capital F belonging to that class and tau greater than 0, such that for all xy in X, now this contraction condition goes like this: that tau of plus f d tx dy is less than equal to f mxy, where mxy is again a type of this, that is a maximum. Okay, max of d of xy, d of xtx, d of yty, then d of xty plus d of ytx by 2. Then every f contraction is a f weak contraction, but the inverse is not true. Okay, this is a weak contraction, and then this is an example here. Let T be a mapping from 0, 1, closed interval 0, 1 to 0, 1, given by Tx equal to half if x belongs to close 0 to 1 open, and when x is equal to 1, this is 1 by 4. This is certainly not continuous, hence not an F contraction. Okay, but think if I take Ft is equal to ln t and t greater than 0 and tau I take as ln 3, then it will be a weak contraction, though it is not a contraction, but by just using this like this, it is a weak contraction. Now, for weak contraction, we have a theorem. Let Xd be a complete metric space. T be a mapping from X to X be a weak contraction F. That is, with the help of auxiliary function F. This is a weak contraction. And if T or F is continuous, then T has a unique fixed point U. And for all X belonging to X, the sequence T and X, for any X, okay, belonging to X, this is convergent to U. Okay. So this is a very larger class of mapping. Then introducing a large class of functions by replacing condition F3. Now we are F1, F2, F3, what we have taken. Now we take another auxiliary function defined on that we write now F3 dash. Okay, F is continuous on, okay, open interval 0 infinity. Now curly F, this is a class of functions from R plus to R where F satisfies F1, F2, F3 dash. Instead of F3, now you have F3 dash. Okay. So, okay, that F3 dash is continuous on this. Okay. Then now we have this theorem. Let Xd be a complete metric space and a mapping T from X to X, a mapping, and suppose that there exists an F belonging to this new class of F functions F tau greater than 0 and all xy belonging to X. dtxty greater than 0 implies tau of F dy, okay, F dtxty is now less than equal to F dxy. Then T has a, now remember, now this F belongs to this new class, capital this, okay, and then has a unique fixed point. And for every x, any x you take, the sequence n x converges to U. Okay, so this is an what is called extension of the. You just see what is there in. This is F1. Sorry, F3. This is a example. Your F3, it was something, just simply this. Okay, that this limit is equal to 0. But in that case, or next case, this is a continuous function. So there is some changes. Now, after this, what we have, next theorem, okay, that sorry, I think I have already covered this, yes. So this is this one. Based on this, we have this, now this, then. Now, Cyric type of extension. Let Xd be a metric space, T from X to X be a mapping, then T is said to be Cyric type generalized F contraction if F belongs to the earlier class, capital F, and there exists some tau greater than 0 such that dtxty greater than 0 implies tau plus F dtxty less than equal to F mxy, where mxy of this class, then this has a fixed point. This is Cyric type, okay? Then this has a fixed point, okay? I think the theorem is here that let X be a complete metric space and T from X to X be a Cyric type generalized F contraction. Now, if T or F is continuous, then T has a unique fixed point. Then we have another type, what we have here. Let Xd be a complete metric space, T from X to X be a mapping, then T is said to be an almost F contraction. Okay, that this F belongs to the earlier class and there exists some tau greater than 0, L greater than 0 such that we have dtx dy greater than 0 implies that tau plus f dtx dy, you see the structure, fd is less than equal to f dxy plus l dx, sorry, y dx. Okay, this is another structure. Okay, for all xy belonging to x. Then this is f contraction. We have a theorem that let Xc be a complete metric space and T from X to S be an almost contraction. So there is a difference between what we have taken earlier. Now we have some factor L here, L greater than 0. So this is an extension of that. Then this T also has a fixed point. Now another extension of this, let Xd be a complete metric space, T from X to S be an almost F contraction, and suppose that F T also satisfies the following condition, that I have a auxiliary function G in capital F, and now I have L1 greater than 0 and tau1 greater than 1. Okay, such that dtx dy greater than 0 implies that tau1 plus G dtx dy is less than equal to G dtx dy plus L1 dx dx. For all xy, then T1 has a unique fixed point. Now we have a unique fixed point. So these are mostly what is called results on metric fixed point theory, which was developed during last 5 decades. Now it is very much extended by Brodowski in 2014. And these are also some important results. And because of these controlling factors, they are having lot of applications. Then I come to what is called some fixed point theory in what is called in two metric space, or what is called multi-valued mapping. Okay, so on a metric space XT denote. So I have a CB is the class of all closed and bounded subsets of it. And if it is a closed and bounded subset, I have not the usual metric. Now we have a Hausdorff metric denoted by capital H. Okay, going from CBX cross CBX to R plus R0 plus, and this is defined by max of supremum. I have XB, okay, where X belongs to A and this here, then supremum of supremum dya, where y belongs to B. So it is a distance from a point X to B, and this is a distance from Y to E. And supremum, both the supremum, then we take the maximum. That is the Hausdorff distance. And for every AB in AB CBX, okay, DUB is infimum. What is DUB? It is infimum of, okay, UY, where Y belongs to B. And here H is known as the Hausdorff matrix. Now, on this Hausdorff matrix, now we define a theta from R plus to R as theta T naught, not tending to 0. Okay, for each decreasing sequence, whenever F theta, but decreasing, but it is not tending to 0. Now, whenever t tends to 0, what we have that theta Tn less than Tn minus Ftn plus 1. So this is okay, how this is developing. Okay, it is like this. And the thing is that sum of Tn, whenever n, so Tn is nothing but a sequence, its sum is less than infinity. So it is bounded. Okay, then let delta be a set of pairs, whatever we have taken, theta f, that is my function f, and from that class, and then a theta belonging to this class here, theta. Okay, this class theta satisfying this. Okay, and it satisfies F1 and F2, what we have defined earlier. And then we have some more, another development here, what is called weighted F contraction. So let X be from now X to closed and bounded subset of X be a set valued mapping on a metric space XT. And now we take F theta by 2 belonging to that delta. class, then S is called a theta weighted F contraction if the following implication hold, that theta d xy plus fh, okay, now it is multivalued, fh sx sy is less than fd xy, all xy belonging to x, where x sx is not equal to xy. Okay, then this is my condition here, weighted F contraction. This is known as, because of this theta, this factor theta, this is known as weighted F contraction. Let XD be a metric space, S be a mapping from X to CBX, be an weighted F contraction, and let F be a set valued mapping on a complete metric space, XD. Now, if either S is compact valued or F is continuous, S is compact valued from right, then S has a fixed point. So here, these are the things what we already know. These are XDBA metric space. I think this is how metric we have defined. It is similar thing. I'm just skipping this. Okay. Known things. We have another result. Let X from be a mapping from X to closed sets. Okay. Be a multi-valued mapping, and the graph of T be a set D xy. Okay, we know the graph already. So we know the graph of T by gt, and then T is, suppose T is closed. If this condition is there, then it is closed multi-valued mapping if the graph of T is closed and subset of x cross x. Then this theorem is analyzed as a Roger-Hardy type, that let X be a complete metric space and T be a self-mapping of X. Assume that there exists a function in this class F, in the class F, capital F, tau in R plus has that tau plus F. Now this is okay, multi-value F H X Y, sorry, H T X T Y less than equal to F alpha D X Y beta D X T X, exactly. Okay, L. For all xy belonging to x, x not equal to ty, where, okay, that Roger-Hardy type of condition, then T has a fixed. So this is the Siric type, okay, F contraction, multi-valued F contraction. Now this is nothing but Siric type of contraction, generalized Wardowski's type, Siric type contraction, and this is the condition where M, okay, this is given by this, then this also has a fixed point. Okay, so this is the theorem is here. Let XD be a complete metric space. Now X to KX, where X is the family of non-empty compact subsets of X, be a multi-valued F contraction. Then if either T or F is continuous, then T has a fixed point. Then we have another theorem. Yeah. Let XD be a complete metric space, T from X to closed and bounded subset of X, be a multi-valued F contraction. And if F satisfies that, is another condition F4, that F infimum of A for all A belonging to this set, okay, 0 infinity, with infimum A greater than 0, okay, then T has a fixed point. So we have some altering distance. I think, let me, okay, how much time is there? Let me, I will go to the next part otherwise. Professor Thakur, please.
Sir, it is, I think, almost over. You can take 5 minutes more.
Okay, so I will skip some part. I will come to the application part actually. Okay, so let me. I think these are already known thing, compatible mappings. Okay, alpha, what is called altering distance. These are results published in during last decade development. So I'm just skipping this part. We have for common fixed point results, we generally use Zoom type. Then many results which are generalized. Shesha also did. Okay. So myself also, we have done a lot of generalization, compatible, weakly compatible, all these mappings. So I just skip this part. Then this is the most generalized result here. Okay, a compatible pair. This psi is a control function here. This psi is okay. That psi dx psi dt okay psi d ax by is less than hm psi. Okay, this function where psi is satisfying, say, is a function from R plus to R plus. A S B T be weakly commuting pairs of a self map on a complete metric space, and psi satisfying this condition. And we have some containment, that AX contained in TX, BX contained in SY, and this is a very general type of condition, max condition. Then now either of these pair are psi compatible pair of reciprocally continuous mapping, then all these A, B, S have a unique common fixed point. Okay. So these are all beautiful results here. All these, some good results here. There are many results. I'm just skipping. We have many results in our papers. Now I will come to the application part. Okay. So basically what you have seen, the solutions of differential equations. Okay, well known Picard's theorem is analyzed in many large way. And we have a lot of speakers have already expressed a lot of theorems. Okay, they presented many theorems on differential equation. All are really very nice results. So here I have another one. Okay, let x, and this is a notation partial order, okay, set. So where this is a partial order is a relation on X, okay, and define a metric D on this partially ordered set, okay. It is like this then. So this is partially ordered metric space. So I have a fixed point theorem for monotone operators in ordered metric space. Widely investigated and have found application in differential and integral equation. We consider the following Volterra type non-homogeneous integral equation of second kind. So this is a Volterra type nonlinear integral and homogeneous integral equation. And here xt is unknown, takes the value, where the unknown function xt takes the values, and T and S, these are some parameters in the closed interval AB. So this particular integral equation has a solution based on this theorem. Okay, let x be a interval x be a function on AB, where a is less than b. Certainly, a space of our real valued continuous functions defined on AB, and it is well known that all this CAB endowed with, if I write continuous function, generally we denote by CAB, endowed with a metric given by this, that dou t dtxy is which is sometimes we denote norm x minus y, is nothing but it is maximum xt minus yt, where t belongs to AB, and into e to the power minus tau t, where tau is greater than 0. So tau is again a controlling factor here. Now define a mapping t x to y by dx t is equal to ft plus the integral from gt to s. Then st k t s sx ds for all t belonging to AB. Now we designate the following assumptions, A1, A2, A3. The first assumption for this integral equation is that this fg, whatever we are taking, fgh belongs to this continuous function, and k from AB cross AB to, cross R. Okay, this k is defined on AB cross R to R is a continuous function, and tau is greater than 0. And this Sx Sy is less than e to the power minus tau x minus y modulus for all xy belonging to x, whenever x minus tx is greater than 0 modulus for all ts belonging to AB, then, and the condition this, A3, that this integral e to the power tau s ds over gt to ht is less than e to the power tau eta. Okay, then what we have the result that let x be a set of all continuous functions, then x with this metric d what we have defined just now, and then t, f, g, h, f, these satisfy the assumptions. Whatever we have just mentioned here, all these functions satisfy the assumption a1, a2, a3. Then these nonlinear Volterra type non-homogeneous integral equation of second kind as a solution in this class set of all continuous functions AB. So these are the main application part. Okay, and remember this is multi-valued closed-end type of thing, and with these and Wardowski's results also has lot of applications to be explored. And whatever we are saying, all these results have some applications. Say multi-valued mappings for weekly commuting. Okay, all these mappings have some.
Sir, Professor Swamagaru,
Yeah.
please conclude your talk within 5 minutes, sir, please.
Just I am finishing. These are the references here.
Okay, thank you.
Okay. And these are the references. Okay. These are the references here. Oh, so thank you very much for patience hearing. So if there are some questions, I invite.
So I invite anyone, please, you want to ask some question or queries with the Professor Som, please you can ask. So I think there is no question. So thank you very much, Professor Som, for your nice presentation. You have covered a lot of developments in last 10 years in this area, and also given some very nice application. So thank you very much for your nice lecture. Thank you, Professor.
Thank you. Thank you for.
Sir, thank you, Professor Somagaru, for your wonderful lecture, and it's very useful, especially you are touching the Cyric F contraction, Cyric type generalization of F contraction is very useful, and also you gave some examples on the contractions. It is very, very useful for young research scholars and many delegates are coming from various places for this international conference. And also the F contraction is especially so, which is a very enlightened, and it's very different from all the previous contractions, and many more. In particular, the solutions of nonlinear integral equations are very generalized conceptual points, sir, no doubt. So undoubtedly these concepts are very enlightened, and it's very useful. Thank you very much, sir, and sharing the
Okay, I will share.
Okay, on behalf of organizing committee of international conference, I'm once again thankful to your valuable time, sir. Thank you. Now,
Okay, thank you very much. Really, it was good that many participants will be benefited with this material later on. Yeah.
And also, I'm thankful to Professor B.S. Thakur Garu for sharing your valuable time for chairing the session, sir. Thank you. And now I have a small announcement. So, Professor Thakur Garu, please share the session for the paper presentation session. So, which is commence from 12 noon to 1:30 p.m., sir. After your talk, sir, P.P. Murthy talk. Okay, yes, sir. So, after completion of your talk, please share the session for the paper presentations. Okay. I request Professor Swamagaru, please share the session for Thakur Garu.
Okay. It is really a very good honor for me to chair the session of Dr. B.S. Thakur. We actually met sometime in 2012 in Texas, and really this is very difficult to remember. Okay. And Professor Thakur, also known from Professor Sahu, that he is now professor and head of the Department of Mathematics at Pandit Ravi Shankar University, Raipur. He is a product of that university itself. He has completed 4 research projects during his past quite a few years, I think maybe around 25 or 30 years. He has guided already 5 scholars. 3 scholars are working under him in the area of mostly on fixed point theory. And he has also guided about 20 MPhil projects. 100 research papers are there to his credit in many reputed journals, including SCI journals. He has research collaborations with Professor Khan, Professor Jung, Professor Mihai, Professor Agarwal of Texas, and so on, all from abroad. He has visited USA, Romania, Taiwan, then Muscat, Turkey, China, and Thailand for either some research visit or conference presentation. He is a member of many reputed academic and board of his studies, many academic societies, and also board of his studies in few universities. He was recently awarded twice UNESCO Associative Award for 3 years. So I welcome Professor B.S. Thakur to present his talk on some remarks on reckoning of fixed points using averaging iterations. Over to Professor Thakur.
Thank you very much, Professor Som, for nice elaborative introduction.
That's a small announcement, sir.
Yeah.
So I request all the participants for paper presentation. Be prepared for your paper presentation in the WebEx after completion of this Professor B.S. Thakur narrated talk. Thank you. Thank you, sir. Please continue your session, sir.
First of all, I would like to thank the organizers for providing me opportunity to deliver lecture here, particularly my friend and elder brother, Professor G.V.R. Babu, for inviting me here. So I think I should first present the screen. Let me present the screen. I think the screen is visible, sir. Hello.
Yes, yes, sir.
So as the hello.
Yes,
Sir,
it
your
is coming.
voice is audible, sir, and your presentation is very clear, sir.
Okay, voice is not clear?
No,
clear.
clear.
Sir, clear.
Clear.
Okay.
Okay, sir. Thank you.
As you can see, I have chosen the topic some remarks on the reckoning of fixed point using averaging iterations. So there are number of talks on fixed point theory. So I just briefly introduce what is the meaning of iteration in the fixed point. So as you see, fixed point is very much applicable in many areas, particularly solving some equations. So whenever we have to solve certain equation, suppose we have to solve an equation fx equals to 0 using the fixed point technique, then first what we have to do is to change it in the fixed point formulation, that is an equation of the form x equals to phi of x, where phi is the mapping. Then while solving using the iteration method, what we do is that we choose an approximate solution x naught. Then we substitute it in the right hand side of this formulation, that is this place phi x naught, and the calculated value is stored as x1, as you can see here.
Then we put x1 in place of again x, then we get x2. So continuing this process, we get an equation of the form xn plus 1 is equal to phi of xn, and we continue the process till we get two successive iterates which are approximately equal. Approximately equal means up to certain degree of approximation what we have earlier decided. And if this is approximately equals to xn plus 1, that means xn is approximately equals to phi xn. And in that sense, we say that xn is approximate fixed point of the mapping phi, and this xn is an approximate solution of the original equation fx equals to 0. So there are certain questions connected with the method of iterations. First is whether the sequence of successive iterates always converge to some number for any formulation. The answer is generally no. We can see by taking a simple example here. Suppose we consider a simple example, 10x minus x minus 2 is equals to 0. Suppose we have to solve this equation. Then we can formulate this in two different manners. First, one way is to simply write it 10x minus 2. Then other way we can write is that 10x is x plus 2. Here this can be calculated at log base 10 plus 2. Here is formulation of this. So suppose I want to start my calculation with x naught is equals to 1. Then here what we can get here is that 10 to the power 1 minus 2, it is 8. If we go for x2, so x2 is nothing but 10 to the power 8 minus 2. And we can see that gradually the value of x is increasing and it is going unboundedly increasing. So it's not converges to any limit. On the other hand, if we go at that point, so what is x1 here is nothing but log of x plus 1, that is 2. If we take this 1, so it log 3. Log 3 is approximately 0.477. So up to 2 or 3 steps, what we get here is that it is approximately equals to 0.37 or so on. So what we see is that for the same equation, some formulation works and some doesn't work. So the next question is that what would be the criteria by which we can say that the certain formulation converges? It is well-known result earlier mentioned by all the speakers. And this is the celebrated result of Banach. That is a mapping which satisfies this condition, known as contractive condition, when this constant lies between 0 to 1. If it satisfies this, then space is complete, then every formulation converges to the fixed point of that map. So the criteria, yes, there is a criteria, Banach-Cartesian principle. Now, what happens if we go beyond to this? That means a mapping which is just outside the contractive mapping, for example, non-expansive, where the contractive condition, the constant is admitted to allow the value 1. Okay, so it is a non-expansive mapping. For non-expansive mapping, if we see that the successive iterate doesn't work, that means it doesn't converge to the fixed point of a mapping. Let us see an example. So let us take this example. This example was first appeared in the paper of W. Riemann in 1953, where he has taken a unit ball of radius 1 in R2, and the mapping is defined as the translation that is anti-clockwise rotation by pi by 4. So as you can see that if you rotate some point by pi by 4, then it never converges to the fixed point. Obviously, 0 is the fixed point of this mapping. So let us see that if we can apply it in the matrix form, then By this matrix formulation, we can convert to the we can obtain the coordinate of the next point. Here, if we take the point at 1, 0, then its rotation it first go to 45 degrees, then at 90 degrees, then at 135, and so on. If we continually go in this way, we never get a point. That means we are getting a periodic line behavior of the system. So it shows that the method of successive iterates are what we call as Picard iterate doesn't work for non-expansive mapping. So we have to find some other remedy. Is there a remedy? Yes, there is a remedy. What was the remedy? Is that instead of taking mapping T, if we consider an average mapping means a mapping instead of T, we took a mapping of this type T half. T half is nothing but 1 by 2 of identity mapping plus 1 by 2 of T. Okay. This is an average mapping, and you can see that, as I think I remember the last day, the lecture of Professor Berende, there was question, he was using a mapping of type T lambda. There was a question by Professor Babu that whether the fixed point of T lambda is T same. Yes, the fixed point of T lambda is the same, and the fixed point of I plus T by 2 same as the fixed point of T. Okay, so we can try this type of mapping. Let us examine the behavior of this. So instead of using xn plus 1 equals to txn, now try to examine the behavior of iterates of this. So now this is fast iterate. Fast iterate is nothing but average of these two, this and this. Average of these two, so it comes in between these two. Now come to the next iterate, and you can see that it is deviating from the earlier iterate. Now in the next step, what we do, we take this and the txn and the average of these two. So it is deviating like this, and you can see that after certain iteration, it converges to the fixed point of t. That means a simple averaging technique works for Picard iterate, where the original Picard iterate doesn't work, but this average is working here. So this behavior was first observed by Krasnoseletsky in 1955, where he proved that let A be a bounded closed convex subset of a uniform early convex monarchy space, and T be a non-responsive, completely continuous mapping on K into itself. Then for any choice x naught in K, the sequence xn defined by this xn plus 1 is equals to half xn plus txn converges to the fixed point of T. Later, this averaging was generalized to the weighted average. What is the weighted average? Instead of half, this type of mapping is defined that instead of T half, what they define is that it is T lambda. So T lambda is nothing but 1 minus lambda times identity plus lambda times of T. The generalization of Krasnoseletsky's result by Safir in 1957, and he proved that it converges to the fixed point of non-expansive mapping under certain different conditions than the Krasnoseletsky. So this was the result of Krasnoseletsky iteration. This was the Safir. So next obvious generalization is that instead of T alpha, we take a variable type of quantity alpha n. This was known as the Mann iteration. Actually, it is not. This is not the exactly Mann iteration.
In some technical problem.
Yeah. Again, I'm saying.
Yeah. Yes.
So this is the Mann iteration. Actually, it is not the exact Mann iteration. It is the equivalent formulation of Mann iteration. Mann iteration was actually defined for some matrix type structure. And as you can see in the reference that although the Mann iteration is considered as generalization of Krasov-Sheletsky and Safir's result. But as you can see that the Krasov-Sheletsky's result was appear in 1955 and Safir's result on 57, while the Mann result was published in 1953, well before the results of Krasov-Sheletsky and Safir. But it was not proof for non-responsive mapping, it was in some different setting. Okay. Now, there is some class of mapping for which the Mann iteration doesn't work. And the one of such mapping is this type of mapping, which is known as pseudo-contractive mapping, which is defined by Browder and Patterson in 1967. If this mapping satisfies this inequality, norm of px minus px square is less than equals to norm of x minus y square plus I minus px minus I minus py whole square. For this class of mapping, Ishikawa defined a new iteration, which is nothing but a two-step averaging iteration, and he proved that if K be a compact convex subset of a Hilbert space, and T is a Lefschettian pseudo-contractive mapping, and X naught is any point of K, then sequence defined by this two-step averaging iteration converges strictly to a fixed point of T. That was appeared in 1974. So we have an Ishikawa iteration. Then in 2000, there was a three-step averaging iteration was defined by Noor. That was actually defined for solving a generalizational inequalities. So we have one-step averaging method. Now we have a two-step averaging method. This works when Mann doesn't work. Then we have a three-step averaging method by Noor. He says that it is more stable than the Mann and Ishikawa iteration. So when we have a number of threads, now our search is changed. Search is changed in the direction that the people are trying to design a new iteration which is faster than the earlier one. And the first of this result, which is a pioneering result, a pioneering iteration was defined by Professor D.R. Sahu along with Professor Agarwal and Donald O'Regan. And that paper was published in 2007. You can see that what was the change here. It is a small change, but very remarkable thing is that he used, in this place earlier there was only xn. He used, instead of xn, the iterate of xn here in convex combination, and that has changed the convergence rate of the mapping quite remarkably. Now, what was the claim of the paper made by the authors in this paper is that the rate of convergence of S iteration is similar to the Picard iteration, but faster than the Mann iteration process or contraction rate. And this was the example they have used in their paper, that is mapping from K to K. K is this range, and T is X defined by then. And they have calculated their result for 9 iterates, and their comparison is here, right, which we can see that it is converging faster than these two iterations. Once the idea of Professor Sahu and Professor Agrawal was published, many papers in the same ideas have again appeared. So one is the iteration defined by Professor Abbas Nazir, that was published in 2014. What they did is that instead of two-step averaging, they used three-step averaging, and they used, instead of y and xn, they use this type of structure, and they claim that their paper, their iteration is much faster than the earlier. This was the example, and this is the result. Well, you can see that their iterates. You can see here it is quite converging faster than the earlier. We also designed two iterations. One is published in that Journal of Impulsive application 2014, another in Philomet, where we have used again a three-step averaging method. Difference is that instead of taking xn here, idea we choose is that instead of using the initial approximation, we use the calculated value here to improve the rate of convergence in S-type structure. And in second one, instead of taking this xn here, what we did here that we use this zn here. And the finding of our equation is that for this particular set of example and this particular set of choice of alpha and beta and gamma n, it was converging faster than the other iteration. Then for second our iteration, what we call BDM, here it is also converging faster than the earlier ones. In last 4 or 5 years, there are a number of new iterations has been designed by many authors. It is not possible to include all of them here, but I have listed some of them here. The idea is that instead of using that x and y, and people are trying to use more iterations here. Here you can see that average, then we apply over t, then we again apply this over this t, and so on. So nowadays you can see that almost every year there are number of new iterations that have been designed by that manipulating the combination there. And what the people doing is that they are using some example and particular set of parameters, and they show the numerically that their iteration converges faster than others. So in this way, they are claiming that they are designing a new, much more faster iteration. So if you go about the comparison of efficiencies of iteration, first result in this direction we found in the literature was done by the W.D. Dodson in 1970, and where he compared Picard and Mann iteration, and what he found is that for continuous non-decreasing self-mapping, Picard iteration is better than the Mann. Next, systematic study, we found criteria by the roots. This was the criteria of roots. What was the criteria of roots? We can see here is that it says that if two iterates u and vn, the two iteration procedure that converges to certain same fixed point p for a given operator t, then un is considered faster than vn if this condition holds. That means for each iterate, un minus p norm is less than equal to norm of vn minus p. It is very simple criteria, but it's quite difficult to prove during the calculation time. In every step, it is quite difficult to show that un minus p norm is less than equal to norm un minus p. Then he, in 1977, he made some other nice calculation using computers in those days. And that was in 1977. He used these two examples. One is fx is 1 minus x to the power m. Obviously, it is defined in 0 to 1. And for this alpha n, square root of n plus 1 and plus 2, he used certain calculation for particular Mann iteration. And he showed that for what value of m and for what value of k, Mann iteration behaves nicely. And he made a remarkable statement in some paper that is doubtful if any global statement can be made to compare the efficiency of two iterations. The next and much more used criteria nowadays is the given by the Berinde. This is the criteria of Berinde. What he did is that instead of directly comparing norm of xn minus p and norm of yn minus p, what he did that he used two more iterations an and bn, and they bound this by an, this by bn, and if this is that if a and bn are two sequences of positive real numbers converging to 0. Then he says that if the bound of xn minus p converges faster than the bound of n minus p to 0, then the original sequence xn converging faster to y. And using this criteria, most of the papers, authors use this criteria for particular contractive type condition and show that their result is faster than the earlier. But what our observation is that when we go numerically, sometimes we get a finding which doesn't match with this criteria are the finding the authors are claiming. Now, this is the scenario here nowadays. If we go for that, what the established thing is that the Iskawa is considered to be slowest among the Man and others. So, Man is considered faster than the Iskawa, then Picard is considered faster than the Man, then Agrawal, etc. considered the faster than this. Abbas claimed that this is faster than this, and we have defined two more, which we consider that they are faster than the Abbas iteration. This relation was based on the criteria given by Professor Beret. Now we go for some numerical. Okay, so we examine these things in three different ways. One is the number of steps required to reach the fixed point. Then we empirically examine this for terms of computation time taken to reach the fixed point. And lastly, the consistency for larger class of mapping, whether it always works for all the class of mapping or it works with only certain parameters. So let us first look at the number of steps. And with the number of calculations for different set of parameters, what we found that we cannot say anything confidently. For some set of parameters, is power iteration which is considered as slow behaves faster than the third one in a bar iteration. In some sense, S iteration converges faster than a bar. So there is a very chaotic behavior we can find here. So as you can see that here we are considering a mapping defined Tx equals to under root of x square minus x plus 40. Obviously, I use a fixed point. We started with x1 equals to 15. And for this set of parameters, alpha n is nearly approaching to 1, beta n is nearly in the middle, and gamma n is 0.22. What we found here is that this is the iterate of Ishikawa. And you can see that surprisingly, it converges faster than the other iterations. Now, for some other set of parameters, you can see here that the S iteration, which was proved by Abbas, theoretically, that it is slower than the his iteration, but for this particular set of parameters, that means where alpha n is near 1, beta n is more than 0.5, and gamma in is near the 0, then this iteration, S iteration converges faster than the Abbas iteration, which doesn't support the theoretical one. So similar finding is also here. And here you can say that, see that this for this set of parameters, this is converging faster than the other iteration. That is, if we are taking alpha n very small and we took beta n near 1, then Abbas iteration converges faster than that. So what we see here is that there is no consistency regarding the number of steps in different iterations. It is very much dependent upon the choice of parameters we are making. So now, next we examine regarding the computation time. We use these two computers with the examples. This is the finding with respect to number of steps. And what we have calculated this with the computers, then this is the finding. The number of steps is here and time is here. Although the Man iteration, you can see here that the Picard is taking 27 steps, Abbas is taking 16 steps, but it's taking less time than this. So if you apply this in computers, then our finding is we are getting the different finding. Now, finally, go for the larger class of mapping. This time is just completing. I just brief in 4 minutes. So what we did here is that we took this mapping 1 minus x is equal fx equals to 1 minus x to the power m, and this parameter alpha n, beta n, gamma n. Whenever we use more parameters, we took all are equal, and we try to find the behavior for this all. That is, M ranges from 1 to 6, K ranges from 1 to 8. So you can see that. So there are 6 set of mappings. We have 7 iterations and then 7 set of parameters. So for each mapping, we try to calculate the behavior of each iteration, and for each iteration is examined for all set of parameters. And what our finding was, just I put in some slides here. So these are the behavior for different iterations. This is Mann iteration, this is Kava iteration, this is Noor and other iterations. For this particular set of mappings, 1 minus x, obviously the point is 0.5. And for this set of parameters, for varying k equals to 3, 4, 5 others. So here you can see that this normal averaging, where we have not applied anything to increase the iterations, are behaving, but although S iteration is converging faster, but these two set of iterations is not working. Okay, here also this is not working for k equals to 3. If we go for this, we are getting much worse condition that the new iterations are working for only selected set of parameters. You can see here that only for k equals to 7 and 8. Here it is only working for 6 and 5. It is working for only 7 and 8. So the classical iterations are more stable than the newer iteration defined recently. This is for the x minus 3. This is for the case x minus 4. Here you can see that it is working for only one parameter. It is not getting for any parameter. It is working for only one parameter. So this is x for x by 5, and this is lastly for x minus 6. Here you can see that this iteration is not working for any case. This is not working for any case, and this is working for only one case. But however, this Ishikawa iteration is working in all cases in this particular set of example. So this time is going over, so I think I should stop here. So in the conclusion, what I want to say to the young researchers, whenever they are going to define any new iteration, don't go with any particular set of your choice of set which gives a favorable result. Okay. So you put all those observations which doesn't support your finding also, so that other can get a true idea about the new iteration. So we should take care about the dependency of the control parameters also while defining a new iteration. The computation time is also important, because when you go to apply something, always it goes on some computers, and computation time is much more important. Then, as you have seen in the last slides, stability for different class of mappings are very much important. If you're defining for a particular set of mapping, if it doesn't work for other mapping, then iteration is very limited use. And last, we have not considered here is sensitivity to initial point is also important. Some iterations are very much sensitive about the initial guess. If we start from the other point, it converges very fast. If we start from some other point, it takes very more steps. So that are some empirical evidences what we have found in our study in last 3-4 years. I share here. If anyone has any query or questions, I welcome their queries or questions. Thank you.
So it was a very nice talk delivered by Professor B.S. Thakur on different iteration schemes. Yeah. And now, if there are some questions from any participant, please.
Professor B.S. Thakur, I have one question.
Sure.
You compared Picard iteration, Noor iteration, Ishikawa iteration, and then Mann iteration, all these by using some computer techniques. You explained it's good, but is there any mathematical formula that gives us the idea of rate of convergence, which iteration converges faster?
Actually, that criteria given by the root is very much stable, but applying that criteria is quite difficult. because in that criteria we have to show that in every step the norm of xn minus p is less than equals to norm of yn minus p for all n. For that, people uses the criteria given by Professor Berende, but that there was some flaw in that criteria, that when we prove something theoretically true, but if it is not verified by the numerical example, that means there is some flaw in that criteria. So except that criteria Professor wrote, which is quite difficult in applying during the comparison, I have found no global criteria that can be used globally for comparing any two iterations.
Okay. Actually, there is a formula which iteration converges faster. There is a comparison given by Berinde.
Yeah. Yes, Berende's criteria is not very consistent. Theoretically, what I want to say is that Abbas proved that his iteration converges faster than the iteration S iteration, okay, using the criteria of Berende. But when you we apply numerically, then we found that for certain set of parameters, their finding is not true.
Okay. Then it's okay. That's the, okay.
I think if there is any other question, please.
Hello, Professor Thakur.
Yes, sir.
Very nice presentation.
Thank you.
Hello.
Yes, please.
Professor Sahu, please.
Yeah, but one thing is that there is more possibility with the S iteration process that we can not only calculate the fixed point of one operator, that we can also do the common fixed points of the more than one operators. So what about the other iterative techniques?
No, I'm not claiming that I have covered all the iterations.
No, I'm not saying to you. But what about the possibilities of the other? Because you are expert, because you have nice.
Definitely.
Yes.
You can try it. Your one iteration that is accelerated is also very good. People can try. What I want to convey to young researchers is that nowadays they are simply making the combination of Txn and Xn and just apply taking an example and a particular set of particular choice of parameters. They use computer technique and they claim that their iteration faster than the earlier one. What I want to say to those researchers that when you rely on the computation techniques, you should apply for a certain number of parameters. And if you are getting the result in the similar fashion, then only you claim that your iteration is faster.
But can you stop this sharing, because this is important discussion and in between it is interrupting and we are not able to. Yes. Hello. Professor Babu is here and he is also expert of the iteration techniques. And I remember the paper, it was published in the Proceeding of American Mathematical Society. And this is not the simple thing for the Indian community, but particularly mathematician in iterative techniques. So still there is a nice the question by Professor Babu, and it is still open question. However, partially it was given by some Romanian mathematician. It was published in Journal of Fixed Point Theory by it was of Professor Agarwal. So still it can be done. So it is the open challenges for young researchers still. Okay, thank you very much.
It is open problem for young researchers to rectify the criteria given by Professor Berende. So the theoretical finding should be verified by the computation using certain examples. It is an open problem nowadays.
So, in my opinion, I think that there should be one more additional condition is required in addition to the Berende's definition. In that definition itself, some more additional condition is required, I hope.
Yes, sure.
Okay, thank you very much. Professor Sahu and Professor B.S. Thakur and B.S. Thakur. Okay. Hello, Professor Som and Professor. So, concluding remarks by Professor chairman of this session, chair of this session. Then I thank.
Thank you, Professor Babu. I am sorry that I could not attend yesterday's morning session because I had to go to hospital and I had returned around 2. Then I attended afternoon session anyway. And
First
then
you thank that talk for Sir B.S.
Let me thank Professor Thakur for a very nice and illuminating talk. Okay, and really it has given a new direction and on iterative techniques. Really, I'm very much. We are actually happy with his lecture, and I'm just talking to Professor Babu. Anyway, it is really it is a good program going on. And yesterday we saw some new all our old colleagues which we met somewhere in the USA or in Thailand. They were there. I'm very happy with Professor Babu's program. Thank you very much, sir.
Thank you very much, Professor Som, for giving your interesting talk and chair a session and accepting your our invitation and your valuable time you spared here. And thank you very much, Professor Som. And I thank Professor B.S. Thakur for chairing a session, and he extensively described the iteration procedures and their convergences. I thank Professor B.S. Thakur for giving his nice lecture and chaired a session and accepting our invitation and for sparing his valuable time in this conference along with us. Thank you very much, Professor Thakur.
Thank you, Professor Babu, for providing the opportunity to interact with many more friends and scholars. Thank you very much.
Thank you very much. Thank you very much. Namaste.
Thank you, sir. Professor Balwant Singh Tagore, sir, and Chair Som, sir. The next section is paper presentations. I invite B.S. Tagore, sir, to chair the session for paper presentations.
Yeah.
Sir Tagore, sir.
Yes.
I have already shared the list to you, sir.
Okay. So, should I invite the speakers one by one? Yeah.
The first one is Asghar Hussain. The title of this paper is Nonlinear Programming Problems with Quasi-Strongly E Pre-Invex Functions.
Yes, sir.
So, all the participants have 5 years time, I think.
Yes, sir. 5 minutes, sir.
So please take care of your time. You start your presentation without going to any much more introduction. I hope you should focus on your contribution so that your presentation will be wind up in a time limit. Please start. Sharing and you start.
Yes, sir. Am I audible?
Yes. Please start. Share your screen and please start.
Yes, am I audible, sir?
Yes, you are audible. Your screen is also appearing. You just you select that window. Yes. You start now.
Okay. Good evening. Good afternoon, sir, to all. My presentation topic is nonlinear programming problem with Cauchy strongly E pre-invex function. These are outline of my presentation. Abstract, introduction, preliminaries, main results, nonlinear programming problems, references. In this article, we extend the class of strongly E pre-invex functions strongly E inverse function to quasi strongly E pre-inverse function, quasi strongly E inverse function, and pseudo strongly E inverse function. Some non-trivial example are constructed in the support of our definitions. Several interesting properties and relationship of these functions are given as a application to nonlinear programming problem has been considered. Preliminaries. Rn denotes the Euclidean space is mapped from Rn to Rn. A set is called a strongly inverse set with respect to phi with this condition for ub belongs to S, alpha, and lambda in unit interval. Let S be a strongly inverse set. A function is called strongly E pre-inverse function on X. If this inequality holds for every u b belongs to S and lambda belongs to unit interval. S be a non-empty set, a function is called quasi-strongly E pre-inverse function on S if left hand side less than max h of e and h of v for every ub belongs to S alpha and lambda belongs to unit interval. H is called strictly if the inequality is strict. H u not equal to E for every u b belongs to S alpha and lambda belongs to this. Quasi strongly E pre-inverse function with respect to psi is E pre-inverse if lambda is equal to 0. And this example shows this H is quasi strongly E pre-inverse as well as E pre quasi inverse with respect to, but it is not strongly E pre-inverse. By this H is strongly H is not strongly E pre-inverse. An E pre-quasi function with respect to psi need not necessarily quasi strongly. Give an example. Suppose H from R to R, psi, this value equal to 2 and max is equal to 1. Here, this inequality does not hold. It means that let's come to our results. Let S be a strongly E inverse set. H is quasi strongly E pre-inverse with respect to psi on S. Then this inequality hold for all v belongs to S and lambda belongs to unit interval. Suppose S subset be a strongly E inverse set if the function are all quasi strongly with respect to psi, then H aj is quasi strongly E pre-inverse function on S. And again S be a subset strongly E inverse set H I belongs to I. The collection of function defined on S. Supremum exists in R for every u. H be a function defined y hu supremum for u belongs to S hi for every I or all quasi. Then H is quasi strongly E pre-inverse function. And again H be a quasi strongly E inverse function and psi be a positive homogeneous non-decreasing function. Then composition is quasi strongly E pre-inverse on X. In the following theorem, we show a relation between strongly E pre-inverse function and quasi strongly E pre-inverse.
Please sum up in 1 minute.
Yes. Let S be a strongly E inverse set. H be a strongly E pre-inverse function on S with this inequality for every UV belongs to S, then H is quasi strongly E pre-inverse. Quasi strongly E pre-inverse is the generalization of strongly E pre-invex function. Hj be a Cauchy strongly E pre-invex function with respect to, if this assumption E of S subset S, then S is strongly E-invex set. Let Hj be a Cauchy strongly E pre-invex, then the intersection of is also strongly E-invex set. Cauchy strongly E-invex function. Now we define a Cauchy strongly E-invex function on a strongly E-invex set. Here a H is called difference. Here H be a differentiable function is called Cauchy strongly E-invex with respect to psi on S. If this inequality implies this, for every UB belongs to S, alpha belongs to unit interval. For alpha 0, H reduce E Cauchy invex function defined in 4. Example, this example in the support of Cauchy strongly E invex function. Again, the theorem, let S be a strongly E invex set, H be a differentiable on S. With this condition, then function H is Cauchy strongly E invex. In the following theorem, we show the relationship between Cauchy strongly E pre-invex function and Cauchy strongly E invex. H be a differentiable function, differentiable strongly E invex function on S, satisfied with condition A. And this inequality, for every UB belongs to S, then H is called Cauchy strongly E pre-invex function on S. Another definition, we define pseudo Cauchy strongly E invex function on a strongly E invex set as follows. H, a differentiable function H, is called pseudo strongly E invex function with respect to psi if this condition hold implies. For every belongs to S, alpha belongs to unit interval, alpha is equal to 0, H reduce is pseudo strongly E invex function. And this example in the support of pseudo strongly E invex function, which shows the existence of pseudo strongly E invex function. Now come to the last result of this section. In the next theorem, we discuss the relation between strongly E invex and pseudo strongly E invex is as follows. H be a strongly E invex with this condition, for every UB belongs to S, alpha belongs to unit interval, then H is called pseudo strongly E invex function on S. And now we come to the nonlinear programming problem. In this section, we consider the Cauchy strongly E pre-invex programming problem, which generalize the results obtained by A equal nonlinear programming problem, where Hj
Please, finish your presentation.
cause Cauchy strongly, yes, and
Please
X
finish.
the set of feasible solutions. E of X subset, then X is strongly. In the last theorem, H be strictly Cauchy strongly E pre-invex function with respect to psi on S be Cauchy strongly E pre-invex on. U star is a local minimum point, is a strict global minimum point. These are references.
So if any has any questions, you can ask. Okay, if there is no questions, so thank you very much for your nice presentation.
Thank you.
So you can share your video. So next is B.B. Chaturvedi.
Kunj Bihari Kaushik. The presenter is Kunj Bihari Kaushik.
Okay. Kunj Bihari Kaushik is here.
Yes, sir.
Please present your screen and start. Please take care of time. No? You have only 5 minutes. You just go to your main findings.
Okay, sir.
Please start. Yes, it is visible. You just start now.
Okay, sir. Good afternoon to all of you. I am here to present on research Equi semi-symmetric mixed super quasi-Einstein nearly Kähler manifold. This contains semi-symmetric and Equi pseudo-symmetric manifold, Equi pseudo-symmetric mixed generalized quasi-Einstein nearly Kähler manifold, projective flat Equi pseudo-symmetric mixed generalized quasi-Einstein manifold, and references. Abstract. In this paper, we have studied new curvature properties of projective curvature tensor in nearly Kähler manifold. The aim of this paper to study projective Equi semi-symmetric mixed super quasi-Einstein nearly Kähler manifold and a projective Equi semi-symmetric mixed super quasi-Einstein nearly Kähler manifold. These are the keywords. Introduction. An even-dimensional differential manifold Mn is said to be a nearly Kähler manifold if a complex structure F of type 1, and a pseudo-Riemannian metric G of the manifold satisfies these three following properties. These are the basic concept. In a non-flat Riemannian manifold is said to be a quasi-Einstein manifold if the non-zero Equi tensor satisfies Sxy is equal to alpha gxy plus beta ax ay, where axi is the non-zero one form, G is the Equi symmetric. With the above expression, we can conclude R is equal to n alpha plus beta. With the above equation 2.2 and 2.6, we get this expression. The Walker spacetime is an example of a quasi-Einstein manifold. The concept of quasi-Einstein manifold came out during the structure of exact solution of Einstein's field equations as well as consideration of a quasi-umbilical hypersurface of a semi-Euclidean spaces. Also, a quasi-Einstein manifold can be taken as a model of a perfect fluid spacetime in the general theory of relativity. The notion of generalized quasi-Einstein manifold was introduced and studied by M.C. Cauchy in 2001. Later on, in 2004, UCD G.C. Ghosh cited an example of a generalized quasi-Einstein manifold. A Riemannian manifold MNC satisfies this condition. Then the manifold is called generalized quasi-Einstein manifold, and these are the basic calculations. After the above calculation, we have gone through all developments in quasi-Einstein manifold, generalized quasi-Einstein manifold, mixed generalized quasi-Einstein manifolds, and we plan to study projective Equi semi-symmetric mixed generalized quasi-Einstein nearly Kähler manifold. According to Jade Wheel, if the manifold satisfies R dot R is equal to 0 for all vector fields x and y, then the manifold is called a semi-symmetric manifold. Definition: an n-dimensional Riemannian manifold MNG is said to be Equi pseudo-symmetric if and only if the tensor Rs and QGS are linearly dependent with these conditions, such that U is defined as x belongs to M such that S is not equal to R by N G at x, where Ls is a certain function on Us. The projective curvature tensor W in a nearly Kähler manifold is defined by this. Along with this, in a nearly Kähler manifold, a projective curvature tensor also satisfies this 3.7. Projective Equi pseudo-symmetric mixed generalized quasi-Einstein nearly Kähler manifold. We have defined a nearly Kähler manifold is said to be mixed generalized quasi-Einstein nearly Kähler manifold if it's a non-zero Equi tensor of type 02 satisfies the equation 2.13. Throughout this paper, we denote this by this. Again, these are the another definitions. These are the basic calculations we have done. Now I come to the theorem. A projective Ricci pseudosymmetric means generalized quasi-Einstein Hiller manifold. If beta is equal to 0, then either the manifold will be projective Ricci pseudosymmetric generalized quasi-Einstein Hiller manifold, or Wxy Romeo is equal to Ls Cx Ay minus Cy Ax, where C and A are non-zero one form. Ls is the certain function. Corollary: in a projective Ricci pseudosymmetric means generalized quasi-Einstein manifold, if beta is equal to 0 and del is not equal to 0, then the vector field rho and mu corresponding to one form A and C respectively are codirectional if and only if Wxy Romeo is equal to 0. Theorem: in a projective Ricci pseudosymmetric means generalized quasi-Einstein manifold, if del is equal to 0, then either the scalars beta and gamma are equal, or these conditions satisfied. These are the proof. Again, we get one corollary. These are the references. Okay, thank you, sir.
Hello.
Hello.
Thank you.
Thank you, ma'am. Thanks to all of you, sir.
Yes. Thank you, Kunj Bihari Kaushik. Next presenter is Bijendra Paswan. Bijendra Paswan. Bijendra Paswan.
Yes, ma'am. Yes. Am I audible?
Yes, sir, you are audible. Please share your presentation.
Thank you, sir. Thank you, madam. Good afternoon, all of you. I am Dr. Bijan Paswan. I am working as an assistant professor in the Department of Mathematics at Guru Ghasidas Vishwavidyalaya, Bilaspur. I am going to my research topic, mathematical study of the polarized shear wave propagation in a layered structure. The content of my presentation is formulation and solution of the upper semi-infinite media, and formulation and solution for the sandwich layer, and formulation and solution for the lower semi-infinite media, and then boundary condition, and then numerical examples and discussion, and then conclusion, and then bibliography. In this problem, we have taken a layered structure comprised of a magnetoelastic orthotropic layer sandwiched by two semi-infinite media. These two semi-infinite media, upper semi-infinite media and lower semi-infinite media, are heterogeneous media, and we have considered the heterogeneity of the upper semi-infinite media as a quadratic heterogeneity, and in the lower semi-infinite media as a linear type of heterogeneity. And we have taken different type of initial stresses, and all this system, all this composite structure are under the initial stresses. In the upper semi-finite media, we have taken a stress S1, and in the medium interface sandwich layer, we have taken interface S2, and in the lower semi-infinite media as an initial stress S3. For the upper semi-infinite media, we have done some basic calculation, and the equation of motion for the wave propagation in the upper semi-infinite media can be written by equation number 1, and by using the condition of seismic wave, horizontally polarized shear wave, this equation reduces into equation number 2, and we have taken the heterogeneity, variation in rigidity, and variation in the initial stresses as a quadratic variation, which are given in equation number 3. And by using the stress-strain relation, we have equation number 4. This equation 2 reduces into equation number 5. And we have used the equation number 5 as a transformation, the displacement small v1 equal to capital V1 e raised to power iota k x minus ct. And by using this transformation, this equation reduces to equation number 6. And after some basic calculation, we get the displacement in the upper semi-infinite media as v1 equal to 1 upon 1 plus z upon j1 e1 a1 e raised to power alpha 1 z into e raised to power iota k x minus c2, which are equation number 8. This is the displacement for the SH wave propagation in the upper semi-infinite media. And in the same manner, we can find the displacement for the SH wave in the sandwich layer, which are magnetoelastic orthotropic material, and which is given by equation number 23. And in the same manner, we can find the displacement equation for the lower semi-infinite media as equation number 33, 34. And by using the boundary condition, we get the dispersion relation. Boundary condition at the between two upper semi-infinite media and in the sandwich layer, the stress and displacement at the interface between the lower semi-infinite media and interface between the lower semi-infinite media and a sandwich layer, these two stresses and displacement will be equal. And by using this boundary condition, we receive the dispersion relation in the form of a tan. And by using the numerical example, which we have given a numerical example for the graphical representation for the upper heterogeneous media, magnetoelastic layer, for the lower semi-infinite media. And we can plot the displacement phase velocity of the seismic wave, SS type seismic wave with the wave number. We have seen that by using the above data, we can find that as the wave number increases, when we are increasing the wave number, the phase velocity of the SS type seismic wave decreases. And these are the heterogeneity parameter. As the heterogeneity parameter increases for the media, upper semi-infinite media, the phase velocity also decreases. And the same type of graphical representation can be done for all the initial stresses, like initial stress, heterogeneity parameter, and then magnetic field. Conclusion. Now the next last topic is the conclusion. The phase velocity of the wave decreases as the wave number increases. That is the wave number disfavor the phase velocity. From the graphical representation, it can be concluded that the initial stresses significantly affect the phase velocity. And the third point is phase velocity of the SS type seismic wave decreases with the increment in the heterogeneity parameter in the presence and absence of the initial stresses. And the fourth is magnetoelastic coupling factor has the significant effect on the wave propagation. Thank you.
Thank you, Bijendra Paswanji. Sir, B.S. Thakur, sir. Thakur, sir. Thakur, sir. Okay. Next presentation is by C. Gangireddy and D. Bharati. D. Bharati or C. Gangireddy. Title of their paper is Symmetric by Generalized Sigma Tau Semi-Derivations on Prime Near Rings. D. Bharati. D. Bharati. Okay, in that case, we'll move to the next presentation. By Dr. M.V.R. Kameshwari, Department of Mathematics, Geetam University, Visakhapatnam.
Thank you, madam. So firstly, I thank the organizing committee who has given Hello? Yeah. Am I audible? Firstly, I thank the organizing committee. Firstly, I thank the organizing committee who has given this chance to present my paper. So the title of my paper is Almost RG Sci-Fi L Weak Contractive Inequalities with an Application. So the abstract of my paper is we initiate almost RG Sci-Fi L weak contractive inequalities rendered by rational expressions on a metric space with a locally S transitive binary relation and carried out to study the existence of unique common fixed points, coincidence points and common fixed points. These results are enriched through examples. These results generalize the results of Jaggi, Das and Gupta. As an application of these established results, we solve a boundary value problem. So coming to the main definition, these are the definitions I used here. First definition is binary relation, next definition is comparability, and next definition is inverse dual relation, reflexive closure, smallest reflective relation, smallest symmetric relation. And then the sequence, R preserving sequence, and R preserving Cauchy sequence, and R preserving Cauchy sequence. Then, okay, sir. Then S closed definition and SG closed definitions, and then R continuous, GR continuous maps, and R preserving compatible maps. These are the definitions. I mean, already these definitions. This is the literature review I used here. And coming to the main result. Coming to the main result. Here, firstly, we use these notations phi. This is a function, a continuous function, and psi t is equal to 0 if and only if t is equal to 0 and psi is increasing. Phi, this is for any sequence Pn in 0 infinity with Pn tends to t for any t greater than 0 and limit infimum n tends to infinity phi of Pn greater than 0. And n naught is n union 0. And then coincidence points of SG and common fixed points of SG. Now, first here we introduced a definition here. Let MD be a metric space with a binary relation R and S and G be self maps on M. Then S is said to be almost generalized, almost sci-fi L generalized weakly contractive map on M if there exists psi in psi, phi in phi, and L greater than or equal to 0 such that psi of D of SP SQ less than or equal to psi of M of PQ minus phi of M of PQ plus L times N of PQ. And where MPQ is defined as maximum of D of GPGQ, GQSP, GQSP, and yeah, it's repeated. I'll change it. Next, D of GQSP 1 plus GPSP by 1 plus GPGQ, and D of GPSP 1 plus GQSP by 1 plus GPGQ. And N of PQ is defined as minimum of D of GPSP, GQSP. For all PQ and M with GPGQ related belongs to a relation, binary relation. Now a proposition, this is the proposition we used here, and because to show the symmetry, that is let SNG be self maps on a metric space on a binary relation, then for all psi in psi, phi in phi, and any L greater than 0, the following two conditions are equivalent. Psi of SP SQ less than or equal to psi of M of PQ minus phi of M of PQ plus L times N of PQ for all PQ in M with GPGQ belongs to M, and psi of SP SQ less than or equal to psi of M of PQ minus phi of M of PQ plus L times N of PQ for all PQ and M with GPGQ belongs to M. And okay, where MQ and NP are defined as in definition 2.1. So we proved this result first, and then coming to main result, let SNG be self maps on a metric space with a binary relation R with the following conditions. S is almost RG psi phi L weak contractive map. And if there exists P naught belongs to M such that GP naught, SP naught belongs to what? And Q is a complete subset of M with the Q is contained in GM and SM is contained in Q intersection GM. And R is SG closed and locally S transitive. If one of the following succeeding conditions is satisfied, that is either S is GR continuous, S is continuous and G is bicontinuous, and R by Q, R restricted to Q is a D self-closed, or alternatively, SG is R compatible and S and G are R continuous, then S and G admits a coincident point in AM. Now this is the proof. I'll quickly the proof. Next, suppose that this next theorem is proved to show the uniqueness of this coincident point. That is, suppose that all the postulates of above theorem are satisfied, and in addition to those conditions, if G alpha and G beta are comparable for all alpha beta in SG with alpha is not equal to beta, and one of G or S is 1, then the coincidence points of S and G is unique. And in addition to these conditions, if the pair SG is weakly compatible, then this SG is a singleton set. And this set of fixed points is in a singleton set. And again, to prove the uniqueness, we have added some more conditions here to show that this fixed point is an unique fixed point. So we in theorem 2.5 we have used additional condition to show the uniqueness. That is, in addition to the condition stated, if R by SM is complete, then the pair SG is a unique coincident point. Moreover, the pair SG is weakly compatible, then S and G have a unique common fixed point in M. And these are the consequences and examples. This is the first example. And we have given another example. This is another example. And then applications to boundary value problems we discussed here. We solved the equation d square u by dt square is equal to f of t ut with the t in 0, 1 with the initial conditions u0 is equal to 1, u0 is equal to u1 is equal to 0, and f must be a continuous function. And the Green's function associated with the above equation is given by GST is equal to this one. And then M is equal to C of 0, 1 be continuous functions defined. We define D is supremum of T in 0, 1 PT minus QT. We know that C is a complete metric space. And with these, the following conditions, then the differential equation may possess a solution. So let S be a self-map on a complete metric space. A function F is 0, 1 cross to 0, 1 satisfying F of T Qt minus F of T Pt less than or equal to 8 times M of Qt Pt minus phi of M of Qt Pt, such that for all Pt Qt in R with the Pt less than or equal to Qt where phi in phi where M of Qt maybe is defined like this, and there exists say U naught. This is actually sorry, this is a mistake here. This is P naught in C 0, 1 in closed interval 0, 1 such that S of Pt, not this S of ut, this is S of Pt is equal to integral 0 to 1 g of Ts f of T Pt dt. Under the above assumptions, the equation 4.1, that is differential equation, has a unique solution. So these are the differences we used here. Thank you once again. Thank you all.
Thank you, Dr. Kavya Kameshwari.
Madam, can we apply this equation for higher order?
Yes, please.
Sir, please once again, please ask your question, sir.
In applications, second degree derivative.
Second derivative? Yes, sir. Yes. So we haven't tried for higher order, but we tried up to second order. We are exploring. So,
Okay, thank you, madam. Next, we move to the next participant. Next participant in the next presenter in the list is actually B. Raviteja, but he could not present due to his ill health. So next we move on to G. Varaprasad. G. Varaprasad, M. G. Varaprasad. Sir, if you are there, please unmute yourself.
Hello, may I audible, please? May I audible?
Yes,
Hello?
sir, you are audible.
May I audible,
You are
please?
audible. Please share your presentation, sir.
Okay, ma'am. Okay. Okay. Welcome. A very good afternoon, all of you, one and all. This is Varprasad, and now my research paper is a public key as a L matrix on Hill cipher and affine Hill cipher under modulation of prime number. I am working as an assistant professor in NSRIT College of Engineering, and now I am going to present these outlines of this presentation. First one is the abstract, second one is the introduction, third one is the reflection matrix on Hill cipher and affine Hill cipher, and next one is 12p matrices. And now my proposed work is generating a public key as a 12 matrix crypto system using on Hill cipher and affine Hill cipher, and finally conclusion and reference. So now my first one is the introduction. Now I will go for the definition. So I will go for that. This is the reflection matrix or householding matrix. This householding matrix or reflection matrix is that it is a symmetric and orthogonal and self-invertible matrix. So in this crypto system, I am constructing generating a self-invertible matrix. So this matrix will be so this is the simple example. From this, I will consider as a plane equation, homogeneous plane equation. Then I will choose as a key, the q is equal to prime number, q is equal to 37 under 30 modulo 37, and I will consider as a keys. B is equal, B transpose is equal to 1, that is keys, and n is that. Now I will construct a key. After under modulation of 37, it is the self-invertible matrix. Then it will comes that k is equal to, after under modulo 37, it comes after inversible. Inverse, and then it will come same matrix. Same key will get it. And after that, my proposed encryption algorithm is that now first thing is I will generate the reflection key under modulation of prime number, and after that calculate that encryption. After that I will go for the encryption, that is S is equal to k into r mod q. That is, this is for only Hill cipher only, and print. After that I will print the ciphertext after applying S is equal to k into r mod r represents that cipher, r represents given text, and after that decryption algorithm I will go for decryption algorithm. Now I will go for the calculate the r is equal to k into s. Why I will go for the k into s again? I will go for the k is because there is self reflection key, so it will comes r is equal to k inverse is equal to k. So r is equal to k into s and mod q. Then finally I will get a required, that is original plain text I will get it. And after that, so I will go for that simple example, and I will go for that plain text is Google. Google for I will go for that, that is R is that block of a plain text. Then I will go for generate a some key. So here the coefficients are x1 coefficient is 1, and x2 coefficient is 2, and x3 coefficient is 1, x4 coefficient is 1. These keys are will consider as the keys. These are also considered as the keys. So to generate self-invertible matrix, so I will go for that. Then I will go for that. The matrix reflection matrix formula is k is equal to, this is order is 6. So matrix M. So I will consider as that homogeneous 6 keys. So I will consider as I6. 2 into n power of n transpose. After that, I will get a key matrix. Then if you go for that inverse matrix, then also it will get like this K inverse also will get same K is equal to, then I will get it here. This is that. After that, I will go for the encryption. What is that encryption here? I will go for the algorithm for S is equal to K into R under modulo of 37. So S is equal to, then I will get it here. The Google will become, ciphertext will become Q8YQ50. Then after that, I will go for decryption. Then after that, I have to use same key under modulation of 37. Then after that, I will get original plain text, that is that Google. Then so I have to increase this one. I have to increase the security level. Then I will go for that module. I will go for that public key. So I will choose a Pell P matrix as a public key. What is a Pell P matrix? So in Pell P matrix, this is the Pell P matrix of order P plus 1 by P plus 1 matrix. So what is the use of Pell matrix means? This Pell matrix means the characteristic equations of Pell matrix is that generalized characteristic equation means alpha over P plus 1 minus 2 into alpha over minus 1 is, so these are the characteristic equation. Then what is the advantage of Pell P matrix means? You will get it here either eigenvalues are either complex numbers or a rational numbers. So we won't get a real integer numbers. So if we consider P is equal to 1, the Pell matrix will become A is equal to 2, 1, 1, 0 matrix. The characteristic equation will like this. So the eigenvalues are, these are that. So then I will go for the P is alpha 1 is equal to 1 plus root 2 and alpha 2 is equal to 1 minus root 2. Then similarly we'll go for the P is equal to and P is equal to 3. We will get that either complex roots or rational numbers. These are the eigenvalues. By using this matrix, I will generate a public generating a public key Pell matrix crypto system using Hill cipher and affine Hill cipher. So here we have to exchange that plain text to ciphertext and ciphertext to plain text. We need two persons. So I will choose one person is person A, another one is person B. So here first person B selects a Pell matrix as a public key and whose eigenvalues are already I told that either not an integer, that means are rational numbers or imaginary numbers. So the eigenvalues of matrix I will consider as that keys will become the A minus alpha into I. For any integer, alpha is number 0 because all eigenvalues are either not in integers or rational numbers or imaginary numbers. So I will consider this is as a public key. And after that, and here also we have to choose that integers, that means not an integers means eigenvalues I can choose as a key also. Then I will go for the one simple example. So this example I will apply on affine Hill cipher. So person B computes that A minus 2i invertible with its determinant GCD of determinant of A minus 2i comma 37 under modulo of 37 is equal to 1, GCD is equal to 1. So then it will exist inverse of the inverse. So person B chooses P is equal to 2. So the Pell matrix will become that order 3 by 3 matrix, which eigenvalues are these values. These values are complex numbers. So these are not an integer. So the key will be, so that means the security will be increased. So person B computes the matrix A minus alpha is invertible with the GCD of data of A minus lambda I Q is equal to 1. So this is accessible. So then he will take a keys from before. I will already discuss some keys from. So I will choose key is equal to 37 and the taking a keys from that previous examples, and I will compute the encryption. That means I will compute first one is A minus 2i as a public key, and after that key matrix E of 2 is equal to A minus 2i into K. K means already this is that K is that self-invertible matrix which is generated from that homogeneous equation. So this is that I got the keys that E of 2 is equal to, I got it is 18, 31, 14, and that matrix is self-invertible matrix. This is that that means here not an integers, eigenvalues are not in integers, and complex variable, that is the complex numbers or rational numbers. So then I will go for the encryption. I will choose a simple example of plain text as S. So then I will apply that in key and it will get it here. The matrix will become F or this message from send to B. Then after decryption, here you will get it after receiving the encryption message, the person will decrypted the ciphertext message. It will become that again he will choose an integer D is equal to. D is equal to means it is an integer. So determinant is not equal to 0. So it is invertible. So then if I will got it here. So again, it is a self-invertible matrix. So after finally, I will get it is virginal plain text, which gives virginal plain text. So finally, our conclusion. The proposed method develops a security of the system. It is more than 3 digital securities digital signals. Namely, here we have to take it as a is one of the and K is the self-invertible matrix. B is another, which is generated from the equation of coefficients of A's, and also K and B are homogeneous linear equation coefficients are known as to the person P and person A. It is not possible for anyone to break the system. So if we consider taken as an integers as the eigenvalues, and also coefficients are the homogeneous coefficients also we are generating self-invertible matrix. So this is that it will increase that security of the matrix, security of the key. So public key means here we are securing is integers if we consider integers, and private key. What is the private key? Is the self-invertible matrix. So this proposed method is mathematically simple and secret key is self-invertible. The proposed system can take care of the data integrity and authentication. K is known to be person A and person A also. Even if anyone acts as person A, sends a person B message using public key, then person B can send standard message to any one person encryption along with the alpha different. Alpha he will choose that his diary he will change the alpha values. Alpha is equal to 1, alpha is equal to alpha is equal to 3. Finally, to determine authenticity of the others. So this is that.
Okay, sir. Sir?
Okay, sir. This is the my references. Okay, these are the my references. Thank you.
Sir, in the Pell matrix, for finding the eigenvalues, can you get the complex eigenvalues? Is there any condition?
Yes, sir. Sir, if we take some other Pell matrix, we will get complex matrix also. So I will show that, sir. So
Okay.
here.
One more thing. You have taken 3x3 matrices. Can we get higher order matrices also?
Yes, sir. Higher order matrix also. We can take any order also. P is equal to. We can take any higher order also, sir. This is generalized matrix.
Okay, sir. Okay, sir. Good
Okay,
concept.
Sir. Okay.
Any questions from the audience? Okay. Thank you, sir. Varprasad, sir.
Thank you, sir. Thank you.
You can answer. The next participant is M. Vijayasanti, T. Chennapal Naidu, who is presenting Sravani Srinivasarao garu.
Sir, myself, A. Srinivasarao, presenting, sir.
Okay, sir. You can share now, sir.
Okay, sir. Just 1 minute, sir. Sir, is my screen visible, sir?
Yes, sir.
Voice also, sir?
Yes, sir. Visible. You can continue.
Okay, thank you. Myself, A. Srinivasarao, research scholar, and under the direction of Professor M. Vijayasanti garu, Department of Applied Mathematics, Andhra University, Visakhapatnam. And my title of my presentation is Viscous Ricci Dark Energy Cosmological Model in a Scalar Tensor Theory of Gravitation, sir. And the overview of my presentation is Introduction, Sayes-Ballester Theory of Gravitation, Metric and Field Equations, Solutions of these field equations, and some important properties of the model, and finally conclusion. Now coming to introduction, recent observations of the Hubble relation provide strong evidence for acceleration of the universe. In the recent era, this expansion of the universe is one of the most attractive topics among the cosmologists. Such expansion of the universe is caused due to some mysterious energy with a strong negative pressure dubbed as dark energy. One of the approaches to answer this dark energy problem is to introduce dynamical dark energy in the RHS of Einstein field equations in the framework of general relativity. And second one is to modify the LHS of Einstein field equations, leading to a modified or alternative theories of gravity. One of them is Sayes-Ballester theory of gravitation, which is of our matter of interest. In this theory, the metric is coupled with a dimensionless scalar field in a simple manner. This gives satisfactory description of the weak field. The field equation in this theory is given by equation 1 and 2, where Tij is stress energy tensor, W is dimensionless constant, N is a constant, and the metric energy and the metric that we considered in this case is a spatially homogeneous Marta type metric of the form represented by equation 4, where dE and F are functions of time only, and the energy momentum tensor is given by equation 5, and effective pressure P bar D of Ricci dark energy is given by equation 6, where H is Hubble's parameter of bulk, Xi is bulk viscous coefficient. Now equations with the help of equation 5, field equation 1, 2 and metric 4 can be written as equation 7, 8, 9, 10, 11, and conservative equation leads to equation 12. Solution of the field equations. Solution of the field equations are 13, 14 and 15. The field equations 7 to 11 forms a system of 5 equations with 8 unknowns: DEF, rho m, rho RDE, P bar D, P bar D, and phi and xi. So to solve this system, we consider the following additional conditions. These are some of the additional conditions which are used to solve the system of equations. Now, from equation 13 to 17, we obtain the metric potentials. We obtain the metric potentials and scalar field phi as given by equation 18, 19, 20 and 21. Now the metric 4 can be expressed as equation 22. Equation 22. And some of the properties of the model, that is spatial volume and average scale factor of the model, is given by equation 23. Hubble's parameter, scalar and shear scalar is given by 25 and 26. Anisotropic parameter is given by equation 27. And these are some of the graphs. Now figure 1. In figure 1, we have plotted the volume V versus redshift Z, and we observe that the trajectories of the volume is monotonically increasing against redshift Z for different values of alpha and beta, which indicates that spatial volume V increases exponentially and showing the spatial expansion of the universe. And similarly, a plot 2 is between H and theta versus redshift Z, and these are the some of the graphs related to this. And finally, coming to the conclusion part, the mean anisotropic parameter AH not equal to 0 for the model 22, hence the model is anisotropic throughout the evolution of the universe. Also, as cosmic time t approaches to infinite, the mean Hubble parameter H, the expansion scalar theta, shear scalar sigma square are all converges to a constant value. That is, the universe is expanding at a constant rate. And these are some of the conclusions. And another one is, in our model, the deceleration parameter is parameter is time dependent and exhibits a transition from early decelerated phase to current accelerated phase of the universe for 3 different values of alpha and beta. It is concluded that the nature of the deceleration parameter agrees with the recent cosmological observations. Finally, the obtained model provides a very nice description of the transition of the universe from early deceleration to the present cosmic acceleration, which is an essential feature of the present cosmic evolution of the universe. And these are my references, sir. Thank you, sir.
Thank you, Mr. Srinivas Rao Garu.
Once again,
Any
thank you,
questions
madam.
from the audience? Okay, then we move to the next presentation.
Okay, madam. Thank you. Thank you.
Thank you, sir. Next presentation is by Anne Willally Abraham George.
Yes,
Abraham
madam.
George.
Yes.
Yes,
Yes.
sir.
Yes.
I welcome
madam.
Tagore, sir.
Okay, madam.
Yes, thank you, madam. Thank you. Sorry for not being there for some presentation.
No problem, sir.
Okay, madam, you can see my slide.
Yes,
you can see my slide.
Your presentation is visible.
Oh, visible. Okay, thank you. Yeah, I'm going to present on the paper title, a study of in-steady state of two server. Sorry, we have something is. Sorry. Okay, sorry. The paper title is a study of the in-steady state of two server finite capacity batch service queue with second optional service. The presenter is Mr. Andrew Abraham George, a research scholar. Sorry. My presentation framework, I'm going to look on abstract, introduction, model description, mathematical formulation, performance measure, numerical analysis, and the discussion, and then to conclude the presentation. In this paper, we study the performance of finite capacity of two server batch service queue with second optional service. We computed the in-steady state probability by using decomposition method, and also we presented the numerical result and the discussion to demonstrate the impact of the model parameters and system behavior. And finally, we developed the cost model to optimize and to determine the optimal service rate. In this paper, our main objective is to investigate the performance of finite buffer two server batch queuing with second optional service. In existing literature review, no work has been reported with the combination of two server batch queue with second optional service. This inspires us to investigate the two server batch queue with second optional service. Model description, we considered the Markovian arrival with Markovian batch service with two server and finite queue model with second optional service, whereby the service times of two servers are independently identical and exponentially distributed. The first essential service, we call it FSC, is required by all arriving customers, and after completing the first essential service, they may opt the second optional service with probability R, or may leave the system with probability 1 minus R. The capacity of the queue is finite. In this model, we modeled by three-dimensional continuous time Markovian process, where NT is the number of customer in the queue, and ST is the number of the server in the first essential service, and the JT is the number of server in the second optional service. We have some definition here. This is we obtained the differential difference equation of the model by using the Markovian theory. Due to the time, I can't explain of each of these equations. So we obtained this equation. And again, we need to know the performance measure. In performance measure, we are trying to determine the expected queue length by giving this formula, and also the blocking probabilities. As you know that because the system is finite, the queue is finite, so some of the customers, they can't enter in the queue when the queue is full. So those customers are termed as blocked. So in this case, we need to determine the blocking probability by using this method, this formula. Also, we need to determine the effective arrival rate. arrival rate, the effective arrival rate are those customers who are entered in the queue, who are succeeded to enter in the queue. So we need to obtain it by using this formula. And again, we need to know the average waiting time in the queue by using this formula also. And in this case, we computed the model numerically by using mathematical software and the MATLAB by assuming some of arbitrary parameters. And in this table, now we can see this table 1, which shows the effect of service rate mu1 and mu2 on the expected queue length, waiting time, and the blocking probabilities. And this table, it shows that in this table, we observe that increasing the mu1 and the mu2, decreasing the expected queue length, waiting time, and the blocking probabilities. And also, we have seen that blocking probabilities tend to 0 due to the faster service rate. So it means if you increase service rate, the blocking probability is going to 0 because most of the customer will be saved on the queue. So there will no, the blocking probability will be reducing. And in this table 2, this for in case of we fixing R, if you fix R as B increases, this mu1 star, mu2 star, LQ, and F of mu1 star and mu2 star, all of these parameters are decreasing. This is what we are expecting. And again, if we go to the table in this figure 1, in figure 1, we show the effect of the buffer size n on the blocking probability for different batch size B. We observe that blocking probability monotonically decreases as n increases. So if n is increases, this one blocking probability is decreasing, and it reaches its minimum value 0 as n is sufficiently larger. So it means when n is sufficiently larger, this one is going to 0 almost. Moreover, when n is kept fixed, the blocking probability decrease with the increase of B. So it means when n we keep constant, the blocking probability decrease with increasing of this B. Figure 2 in right, it shows the effect of the arrival rate on the expected queue length for different values of n. In this case, it is clear that as arrival rate increase, the expected queue length increases for all value of n, as you can see on the figure. This is what we are expected to be. And again, we proceed with figure 3. Figure 3 shows the effect of arrival rate on the expected waiting time in the queue for different value of R. For fixed R, it is observed that expected waiting time in the queue increases with the increasing of the arrival rate, is what we expected also. Furthermore, for fixed lambda, the waiting time in the queue is smaller in the absence of second optional service. It means when R is equal to 0, it is smaller compared to others here. Furthermore, and as R increases, the expected waiting time is also increases, as you can see here. So in table 4, we show the effect of probability R, probability of opting second optional service on the expected queue length. We observe that as R increases, the customer tends to enter in second optional service, thereby increasing the expected queue length in this case. Also for fixed lambda, for fixed R, as B increases, more customers are saved at time. So it means more customers are saved because it is batch. As batch increases, so more customers will be saved. So in this case, resulting on decreasing the expected queue length. By conclusion, performance measure and numerical illustration discussed on this paper are providing the valuable insight about the functioning of the two saver function model for batch service with second optional service in the area like a transportation system, manufacturing, and production system, telecommunication system, and etc. So these are some of the references which have been used. Thank you.
Okay, sir.
So, any question or queries? No. So, Dr. Jaj, one question from my side.
Okay,
Have you examined your model in any real world scenario? Or it is purely theoretical?
Sorry, sir, I don't understand your question.
No, you given a model, okay?
Okay.
Okay, so have you tested it in any real scenario, or you are just giving us some theoretical model?
Sir, I don't understand what your question. Sorry, come again. Sorry.
Okay, no problem then. So thank you for your nice presentation.
Okay. Thank you, sir. Thank you.
So
Okay, sir. Thank you, sir.
next presentation will be
The next presentation is A. Bharati.
Yeah. Please share your screen.
Bharati, madam.
Yes, sir. Good afternoon, sir. May I audible, sir?
Yes, you are audible. Share your screen.
Sir, good afternoon to one and all. This is Bharati, working as assistant professor in mathematics, Miracle Engineering College. My title of this paper is.
Madam, please share
yes,
your
sir.
screen.
Yes, sir. I share.
Not visible.
Okay, sir.
Share screen and select that window.
Sir, 1 minute, sir.
Reshare check.
Now it is visible, sir.
Okay,
Yeah,
okay, madam. Now.
Okay.
Yes, sir.
Yes.
Okay, my paper title is a common fixed points for a pair of maps in bicomplex valued generalized matrix spaces. So this is the abstract of the my paper is the purpose of this paper is to set up generalized bicomplex valued matrix spaces and prove common fixed point theorems for a pair of weakly isotone increasing self maps satisfying more general contraction conditions rendered by the rational expressions. These results are supported through some examples, and here I am using some supporting of the Jebret and the Baguette references, and this is my introduction. By using this concept, I recall the some definitions, that is bicomplex numbers and bicomplex numbers, and this is the basic definition for here. I used this result, that is bicomplex valued matrix space. It is defined as x, let x be a non-empty set, and a function dbc is defined as x cross x2. X cross x2 r is called a bicomplex valued matrix space for x comma y comma z belongs to the z. It's satisfying the following conditions. The conditions are dbc of x comma y, which is greater than or equals to I to 0, and dbc of x comma y is equal to 0 if and only if x is equal to y, and the symmetric property is dbc of x comma y is equal to dbc of y comma x, and the triangle inequality condition is dbc of x comma y, which is less than or equals to I2 dbc of x comma z plus dbc of z comma y. So this is the when the pair the function dbc is satisfying the following conditions, then the pair x comma dbc is called as a bicomplex valued matrix spaces. Now based on the bicomplex valued matrix spaces, we extend the definition for the generalized bicomplex valued matrix spaces. This is the definition for the bicomplex matrix spaces, that is let x be a non-empty set and the function dbc maps x cross x to c2 is called a generalized bicomplex valued matrix space on x if for all x comma y belongs to the x and all distinct u comma b belongs to the x. Each one is different from the x and y. The following conditions are satisfied. That is, the first condition is 0 is less than or equals to I2 dbc of x comma y, and the second condition is dbc of x comma y is equal to 0 if and only if x is equal to y. Next, the symmetric property condition is dbc of x comma y is equal to dbc of y comma x, and the inequality condition is it is extended to dbc of x comma y, which is less than or equals to I2 dbc of x comma u plus dbc of u comma v
plus dbc of v comma z. So if the function satisfying these are all the four conditions, then the pair x comma dbc is called as a generalized bicomplex valued metric space. This is the example for the generalized bicomplex valued metric space. And here we can note that this is the example for this is the condition which is not satisfying. Then this is for it's not hence it is a not bicomplex valued metric space. Again here some more definitions are defining, that is a convergence definition, Cauchy sequence definition, and Cauchy sequence definition here we defined, and these are all the lemmas here we used. And another definition for the weakly increasing and t weakly isotone increasing, that is the definitions are like this. So let x less than or equal to be a partially ordered set, and s comma t is the self maps. Then the pair s comma t is said to be the weakly increasing if satisfying the condition, that is if xx is less than or equal to tsx and txs is less than or equal to stx for all x belongs to the x, and if s is equal to t, we have the sx is less than or equal to s square x for all x in x. In this case, s is a weakly increasing map, and the another definition is t weakly isotone increasing, that is the condition for sx is less than or equal to t sx, which is less than or equal to st sx. So here again we have the another definition, that is the totally ordered, a non-empty subset W of a partially ordered set X is said to be the totally ordered if every two elements of W are comparable. So this is the theorem. So the main, now I am coming to the main result of this theorem. This paper, the main result of this paper is let x is less than or equals to be a partially ordered set such that there exists a complete generalized bicomplex valued metric dbc on x with a d generated the condition dbc of x comma y plus dbc of u comma b plus dbc of w comma z for all x comma y comma u comma v comma w comma z belongs to the x, and s comma t maps the self mapping be the mapping satisfying the condition. This is the for every comparable condition is like this. So here the conditions are where alpha p q r s mu lambda belongs to the x, and beta comma delta is belongs to the closed interval 0 comma 1, with the condition is beta plus 2 lambda which is less than 1, and this is the condition. Here we use dbc of s comma x tx is equal to 0 when the condition is mu into dbc of y comma sx plus lambda into dbc of x comma ty plus dbc of x comma y is equal to 0. And also suppose that if S is a T is a weakly isotone increasing on X, if S comma R, S or R, T is continuous if or for any non-decreasing sequence Xn with Xn tends to the Z, in X we have the condition that is Xn is less than or equals to Z, then S and T have a unique common fixed point in X. Moreover, the set of common fixed points of S and T is totally ordered if and only if S and T have a unique common fixed point in X. This is the proof for the given result.
Go to next.
This is okay. By based on the above proof, by these are all the corollaries by choosing the different conditions. If we choose the by choosing the S is equal to T on the main result, this is the first corollary. And when you are choosing P is equal to R is equal to 1, Q is equal to 0, S is equal to 0, lambda is equal to 0, and mu dbc of y comma tx plus lambda dbc of x comma ty is equal to 1, then we will get the another corollary. This is like this. And if you are choosing the P is equal to 0, Q is equal to 0, S is equal to 0, mu is equal to 1, lambda is equal to 1, and R is equal to 1, we have the another corollary. This is like this. And another condition by you are, if you choose the P is equal to 0, Q is equal to 0, S is equal to 0, mu is equal to 0, lambda is equal to 0, and R is equal to 1, we have the following corollary. The corollary is like this. Now, now one more corollary is there. Then here we are choosing the alpha is equal to 0 and lambda is equal to 0 in the above corollary. Then we have the another corollary that is like this. Now, this is the example for the basic, my main result of this paper. That is, let x is equal to closure 0, open infinite with the partial order x is less than or equals to y, if and only if x is equal to y or x comma y belongs to the closed interval 0 comma 1 with y is less than or equals to x. Here we are defining the DBC by complex metric space as a self map x cross x to C2 by the condition DBC of x comma y is equal to I1 I2 mod x minus y. Then x comma DBC is a complete bicomplex valued metric space with the degenerated the condition, that is DBC of x comma u plus DBC of u comma v plus DBC of v comma z for all x comma y u comma v belongs to the x. This is the example for the main result of my this paper. And this is the conditions. Here we are defining the Sx and Tx as like this. Let S comma T maps x cross x to R be defined by the Sx is equal to x by 4 if the x value is belongs to the 0 closed 0 comma 1, and if the x value belongs to the open 1 comma infinity, here we are defining x by 2 into 1 plus x. This is the defining Sx. Now defining for the Tx as if x belongs to the closed 0 comma 1, defining x by 8. If x belongs to open 1 comma infinity, defined x by 4 into 1 plus x. These are all the, we first to here we are prove that the T is a weakly isotone increasing by basing what we defined in the earlier. So this is the conditions. Here we discussed the two cases. One is the case when x belongs to closed 0 comma 1, and another condition is when x belongs to the open 1 comma infinite. And again here we are defining the
next one.
Okay. This is the another example. Here we discussed it. Another example, let x is equal to 1 comma 1 by 2 1 by 3 1 by 4, and defining the bicomplex metric space, that is x cross x to C2 by DBC of 1 comma 1 by 2. Here we are using the symmetric property, that is DBC of 1 comma 1 by 2 DBC of 1 by 2 comma 1 defined as I1 I2, DBC of 1 comma 1 by 3 DBC of 1 by 3 comma 1 defined to I1 I2, DBC of 1 comma 1 by 4 DBC of 1 by 4 comma 1 defining I1 I2 DBC of 1 by 2 comma 1 by 3 equals to DBC of 1 by 3 comma 1 by 2 defining a 5 I1 I2, and DBC of 1 by 4 comma 1 by 2 is equal to DBC of 1 by 2 comma 1 by 4 defining 4 I1 I2, DBC of 1 by 3 comma 1 by 4 DBC of 1 by 4 comma 1 by 3 equals to 3 I1 I2, and the another condition is DBC of x comma x is equal to 0. Then here we proved that it is a generalized bicomplex valued metric space, and here we can observe that it's not a bicomplex valued metric space by based on this condition. Now here we are taking the another condition, that is defining x is less than or equals to y. If y is greater than or equals to x, here we are defining the conditions like this.
Please sum up. Please sum up.
What, sir?
Please sum up your presentation. Huh?
Okay, sir. So it's one more theorem defining on this paper, that is let x less than or equals to be partially ordered set such that there exists a complete generalized bicomplex valued metric space on x with a degenerated to the DBC of x comma y plus DBC of u comma v plus DBC of w comma z for all x comma y u comma v w comma z belongs to the x, and the function s comma t is self-mapping, be a mapping satisfying the following condition like this. So this is the proof for the theorem. Again, here we are defining the corollaries by based on the conditions of the above theorem, and these are all the examples based on the above theorem. So these are all the references I used here to write this paper. Thank you, sir. References, yes, sir. Thank you, sir.
So, any questions from audience? Okay, no question. So I have one question. Do you have tried for any application of your result?
What, sir?
Have you tried for any application of your result?
Yes, sir. I'm trying to do this one, sir. Sir,
Because you are using the rational type inequalities. In past, for generalization of metric space, people have used lot of rational inequalities like papers, okay, where the inequality size of length up to 1 page is also. So, but I haven't found any application of rational type inequalities in any problem. So I suggest you go for to find some applications you have to result also. Okay.
Okay, sir. Sure, sir.
Okay. Thank you for your presentation.
Thank you, sir. Thank you. Sir.
Okay, madam.
Thank you, sir.
Okay, madam. You can unshare. Sir, can we call the next participant?
Yes, yes, please.
Yeah.
Mohammad Furqan, I think.
The next participant is Mohammed Farkan.
Yes, sir, I am here.
Yeah, please share your screen.
Can you see the screen, sir?
Yes.
Yes, yes, it's visible. You're audible. Please start.
Okay. So my name is Dr. Mohammad Furqan, working as an assistant professor of applied mathematics, University Polytechnic, Aligarh Muslim University. So as the time is very less, so it is difficult for me to figure it out, what to speak and what not to. So let me tell you that it would be a kind of overview. So I shall be speaking on the main highlights of this paper. So the main feature of this research work is we are approximating here the common solution of split monotone variational inclusion problem and hierarchical fixed point problem. So which is very interesting fact is here that we are taking a family of finite family of non-expansive mappings. We are not taking just a single mapping. So further, we deduce some special cases from our main convergence result, and at the last, we give a numerical experiment in order to demonstrate the applicability of our method. So this is what we have assumed throughout this paper. So we are taking H1, H2 to be the two real Hilbert spaces with usual inner product and norm, and C and Q, their respective non-empty closed and convex subsets. So T, I already told you, T is this non-expansive mapping here. So we can denote the fixed point set of T by this fixed T. So this is the main problem of this paper, which I talked about you earlier in the beginning. This is the hierarchical fixed point problem. So I was talking about that we are taking here a finite family of non-expansive mapping. So the hierarchical fixed point problem is to study or is to find a fixed point which lies in the intersection of the fixed point sets of the mappings TIs such that this inequality one holds. We denote the solution set of this hierarchical fixed point problem by phi. So there are many cases which can be deduced, which can be transformed from the hierarchical fixed point problem of the previous slide. So one can be represented, you might be looking from the inequality 2, which was initially studied by Modafi and Menge. So this hierarchical fixed point problem 2 can be made equivalent to the fixed point problem, which we are denoting by 3. So if suppose that we take in our hierarchical fixed point problem S to be the identity mapping, and so our set of fixed point set intersection of fixed point set is just the fixed point set of one single mapping T. So this problem can be reduced to the hierarchical fixed point problem studied by Modafi and Menge. So there are many particular case of this hierarchical fixed point problem, like minimization problems over equilibrium constants, hierarchical minimization problem, and all that. So with this setting, the hierarchical fixed point problem can be reduced to hierarchical variational inequality problem, which is we are giving here by 4. So with this setting, this can be reduced to the following mathematical programming problem. And suppose that M1 becomes del phi, where del phi is the subdifferential of a lower semi-continuous and convex function, then our problem reduces to this following hierarchical minimization problem. Yes. So Modafi initially introduced this iterative algorithm, which we are denoting by 7, in order to find the hierarchical fixed point problem, solution of hierarchical fixed point problem 2. So there are several special cases which can be deduced from our next problem, split monotone variation and inclusion problem. So many special kind of problems can be deduced from this type of split monotone variation and inclusion problem. So what is it all about? So it is to find X star in the Hilbert space H1 such that the inclusion 8 holds, and the image of X star under the bounded linear operator, which we are denoting with the Y star, solves the inclusion 9. So Modafi introduced the following algorithm, which we are denoting by 10th, to find a solution of a split monotone variational inclusion problem, which we were denoting by 8 and 9. So suppose that in 8 and 9, the problem discussed above, we take f and g to be 0, then this problem will reduce to the following split 0 problem, or some say that this is a split null point problem, which is to find a 0 in the M1 X star, and the image of X star under the bounded linear operator A solves the 0 belongs to M2 X. So many research papers have been published in this direction by many authors, but what is more interesting that most of them are basically associated to the weak convergence of their methods to find the solution of hierarchical fixed point problem and whatever split monotone variational inclusion problem. So this is what makes it interesting, and you can say this is the motivation to carry out this research work, that we are proving a strong convergence theorem to find the common solution of a split monotone variational inclusion problem and hierarchical fixed point problem. So this is the basic identity. You can say yes, this is the identity, and second one is cadectily property. This is also very well known. So these are some basic features of projection mapping. This is the very basic definition of monotonicity. Alpha inverse is strongly monotone, and Lifshitz continuity you must be aware of. So in the setting of multi-valued mapping, so we can define by this inequality the monotone mapping, and this is the graph of the monotone mapping, which we are denoting with M1. Yes, this is also a very interesting setting, or this is the definition of WN mapping generated by the family of non-expansive mapping TIs and the parameters lambda NIs. This is the definition of W mapping. So what is the significance of taking this definition? The significance of this definition is that you can see in the next lemma. First lemma is nothing but the demi closeness principle, but the second lemma, yes, you can see here, the fixed point set of the W mapping coincides with that of the intersection of the fixed point sets of the mappings TIs. So this is the significance of talking about this W mapping.
Hello, sir. With the permission of the Thakur sir, Mohammed Furkan, please.
Yes, sir.
Please show your main results.
Okay. Okay, sir. Okay, sir.
Thank you very much, sir.
Okay, sir. So this lemma basically talks about the point-wise convergence of the WN mapping to the W mapping. So this is our main result to approximate a common solution of a split monotone variational inclusion problem and hierarchical fixed point. So you can see here we have taken everything according to, as I already told you, H1 H2 to be the two real Hilbert spaces, M1 M2 two multivalued maximal monotone mappings, and TIs a family of finitely many non-expansive mappings. So this is our iterative algorithm. So this is so suppose that the common solution set of common solution is non-empty. So with these conditions, the sequence of iteration, which we are denoting here with the xn, converges strongly to the solution of the split monotone variation inclusion problem and hierarchical fixed point problem. So these are some special cases which can be derived from our main convergence theorem. So first one is to approximate the common solution of a split null point problem and hierarchical fixed point. So I'm not going into the detail as we are lacking the time. So these are some applications with the appropriate settings. You can see this next theorem is to approximate a common solution of a split variational inequality problem and hierarchical fixed point problem. You can see here. So the next application is to split feasibility problem, which is described in this theorem. Yes, this is the numerical example in support of our main convergence theorem. So here we have taken all the requisite according to the hypothesis of the theorem, and this is our iterative algorithm, which looks like to be like this. So here we can show that 2 by 3 is the common solution of the proposed problems. Yes. So with the use of MATLAB, you can see the sequence of iteration converges to the solution of these fixed point of these problems. So this is the pointwise convergence of the WN mapping, and one more condition we were taking, you can see it is converges to 0. So this is the conclusion, and these are the references which have been used throughout this research work. So at the last, I say thank you very much.
So, if any questions from audience?
Hello, sir.
Hello. Yes, sir.
Okay, Dr. Furkan, you
Sir,
are
any
very
questions
nice.
from audience?
No, I think there is no question. So thank you, because we are lagging with
Sir, no
time.
questions are arise. May I call for the next participant?
Please ask.
Thank you, sir. So participant P.
Yes, sir.
Satyanarayana.
Yes, sir.
Shirisha, who is going to be present now?
P. Satyanarayana. Yes.
Okay, P. Satyanarayana. Share your video and PPT also, and we have only very short term. Next invite talk is also already he is waiting. Therefore, split for 5 minutes. And please show your important definitions and your results and conclusions.
Okay, sir. Thank you.
Thank you very much. Please start it. Share your PPTs, please.
The visible, sir?
Not visible. Not visible.
Sir, wait.
Your PPT is not visible. You have any technical problem?
No,
if you have any technical problem, please give a chance to us. We will call later.
No, sir. No, sir. Please wait.
Hello? P. Satyanarayana?
Visible, sir?
Not visible.
Sir, visible, sir? Screen?
No. Your audio is good, but PPT is not visible. Thakur, sir?
You can ask next in the meantime.
Okay, sir. P. Satyanarayana, solve your technical problem. I call you later. Sushila Shukla. Are you there in line?
Shukla, sir. Sushil Shukla.
Okay.
Yes, sir.
Please share your PPT and video also.
Yes, sir. Share screen. Start now. Share content.
Oh, Dr. Shukla. Sushil Shukla, sir, please. Okay.
Sir.
It is visible, but show your PPT now.
Yes, sir.
Go for your folder. Please, sir.
Is it visible, sir?
Yes, visible, sir. Thakur, sir?
Yes. It is visible.
Okay.
First of all, I am thankful to the organizers for providing me opportunity to present my paper here. Respected chairman and participants, the topic of my presentation is on recurrent light-like hypersurfaces. In this paper, we discuss the properties of recurrent light-like hypersurfaces of cosymplectic manifold with a special type of connection that is known as LM type connection, which is given by DSGN. Before giving the details, I want to describe some introduction. A linear connection delta bar on a semi-Riemannian manifold M bar G is called LM type connection, which is given by DSGN. If linear connection delta bar and its torsion tensor T bar is given by this, where LM are smooth functions on M bar, phi is a tensor of type 1, 1. Theta is characteristic vector field on M bar. Theta is one form connected with smooth vector field Xi with theta U equal to G U Xi. And delta bar and Levi-Civita connection. Delta is connected by the relation delta bar UV equal to delta UV plus theta B LU plus M phi U, where delta is Levi-Civita connection. Actually, LM type connection is the generalization of different type of connections studied earlier. If we take some particular values of L and M, then we get the different connections. For example, if we consider L equal to 1 and M equal to 0, above connection becomes a semi-symmetric non-metric connection. And the notion of semi-symmetric non-metric connection on a Riemannian manifold was introduced by Agassi and Chaffley and later studied by several authors. And if we consider L equal to 0, M equal to 1, then this connection becomes non-metric phi symmetric connection with phi UV equal to G phi UV. And the notion of non-metric phi symmetric connection was introduced by D.S. Jin. If we put L equal to 1 and M equal to 0 in first equation, that is 1.1, and L equal to 0 and M equal to 1 in second equation, then the connection delta bar becomes quarter symmetric non-metric connection. The notion of quarter symmetric non-metric connection was introduced by Golab and then studied by Sen Gupta and Viswas and Ahmad Hasib.
Hello,
In
Sushil
case,
Shukla.
yes, sir.
Please zoom out your PPT. Please zoom out a little bit. Or, sorry, and zoom out, not zoom
in. Case,
no, zoom out. थोड़ा सा make it small, please. Small. You are doing reverse, please.
And
small करिए.
Take Lm equal to 0, 0 in first equation and Lm equal to 0, 1 in second equation, then this connection becomes quarter symmetric metric connection. And notion of quarter symmetric metric connection was introduced by Yano and Imai. And in first equation, if we take Lm equal to 0 and L equal to 0 and M equal to 1, then this connection
hello Sushil Shukla, please 1 minute. हम लोग देखने के लिए बहुत मुश्किल हो रहे हैं, थोड़ा सा स्मॉल करिए ना.
यस सर.
और करिए और इट्स गुड नाउ प्लीज. नो थोड़ा सा बड़ा करिए और थोड़ा सा बड़ा. ओके, अब टाइम वेरी शॉर्ट है. मेन रिजल्ट्स एंड मेन डेफिनेशन दिखाइएगा सर को.
Yes, sir. In this case, delta bar becomes semi-symmetric metric connection, and the notion of semi-symmetric metric connection was introduced by Haydn. This is some basic definition. What is cosymplectic manifold? What is almost contact manifold? An almost contact manifold with an almost contact metric structure phi j theta g consisting of 1, 1 tensor field phi. Satisfying this condition, and an almost contact manifold, if we define two form by phi UV equal to G phi UV, M phi J theta G is said to be an almost cosymplectic manifold if the form phi and theta are closed, that is D phi equal to 0 and D theta equal to 0, where D is the operator of exterior differentiation. In other words, we can say that if the almost contact structure of an almost cosymplectic manifold is normal, then it is said to be a cosymplectic manifold. And the necessary and sufficient condition that almost contact metric structure is cosymplectic if both delta phi and delta theta vanishes. With the above calculations, we can find these two results, which are useful in to find the results. These are some calculation on light-like hypersurfaces. These are calculations on ELM type connections, which are shown here, which are used in the proof of the theorem. Here is my first proposition. Consider light-like hypersurface M with ELM type connection of cosymplectic manifold M with condition J is tangent to M. Then the necessary and sufficient condition that V symmetric is M equal to 0. This is proof. These are simple calculations which are used. This is the example of cosymplectic manifold. Here recurrent hypersurfaces. Structure tensor field F of M is said to be recurrent if there exists a one form omega with delta UF V equal to WUFV and light-like hypersurface M on cosymplectic manifold is recurrent if it have recurrent structure tensor field F. The first theorem in my paper is there is no recurrent light-like hypersurface of cosymplectic manifold with LM type connection and J is tangent to M and recurrent F. This is proof. Next, structure tensor field F of M is said to be Lie recurrent if there exists a one form nu with LUFV equal to nu UFV, where LU is the Lie derivative of M with respect to U, and F is Lie parallel if LUF equal to 0, and light-like hypersurface M on cosymplectic manifold M bar is Lie recurrent if it have Lie recurrent structure tensor field F. And the second result in my paper is consider Lie recurrent light-like hypersurface M of cosymplectic manifold M with LM type connection and J tangent to M and Lie recurrent F. Then F is Lie parallel, one form ta satisfies ta equal to 0, and shape operator omega satisfies omega U equal to omega B equal to 0. And this is its proof. And these are some references which I used. Thank you, sir.
Thank you.
So, any questions from audience? Okay, so we are lagging from time. So you please ask the next speaker.
Okay, sir. Tirtharam or Rohit Kumar Bharadwaj. Are they in line?
To present paper, sir.
Rohit Kumar Bharadwaj. Okay.
To
Your signal is good? Tirtharam?
जी sir.
Sir, namaste, sir. Thakur, sir.
Namaskar, sir. Namaskar.
Tirtharam?
जी sir. I am.
Tirtharam, okay. Please give your voice.
Sir, am I audible, sir?
Tirtharam.
जी sir.
Please give your voice, please.
Tirtharam, please unmute yourself.
Please unmute yourself.
Yes, just a minute, sir.
Your signal is good or not in your area? Please unmute yourself, Tirtharam or Rohit Kumar Bharadwaj. Please.
Yes, sir. Am I audible, sir?
Hello.
Hello, sir. Am I
Hello?
audible, sir? Hello.
Hello.
Hello, sir. Am I audible, sir?
Your voice is very low. Your voice is very, very low.
Yes. Now, sir.
No, very low.
Sir, अब देखिए, sir.
No. Please increase your volume, please.
So now it is 100%, sir.
No, volume is very low.
Yes, sir.
Anyway, you just start.
Sir, I think so. Maybe there is a bandwidth problem there in JK.
No, the bandwidth problem will suffer the video quality. I think audio quality is.
Hello, sir. Hello, sir.
Yes.
Yes, now it is okay.
It's better.
Who is presenting, Tirtharam or Bharadwaj?
Tirtharam, sir.
Okay, so you have only 5 minutes only. Please strict on it.
No problem, sir. No problem, sir.
Okay, please show your main results and important definitions and references.
Okay, sir. Okay, sir. I will try to complete in 5 minutes only, sir.
Thank you. Thank you very much for your cooperation to me.
The topic of my paper is on vector variational like inequality and vector optimization problem with G alpha univexity. So this is the overview of my paper. So in this paper, we introduce and study G alpha univax functions by generalizing the alpha univax functions and establish the relationship between vector variation like inequality problem and vector optimization problems. Furthermore, we formulate the equivalence among the vector critical points, weak efficient points of vector optimization problems, and the solution of weak vector variation like inequality problem under the pseudo G alpha univexity assumptions. So I will skip the introductions. These are equalities and inequalities will be used throughout the paper. So next definition, a subset X of Rn is said to be alpha invex set with respect to eta if it satisfies this condition. Suppose X subset of Rn be a non-empty set. The differentiable function f is said to be alpha univex with respect to alpha, eta, phi, and b if it satisfies this inequality. This is said to be strictly alpha univex if this inequality is strict. Pseudo alpha univex if it satisfies. Suppose X subset Rn be a non-empty set and G be a continuous differentiable functions. This function f is said to be G alpha univex if it satisfies this inequality, and it is said to be pseudo G alpha univex if it satisfies this condition. Given X subset Rn and a function f, the vector optimization problem is given as it is just a minimum of this function over this X. In vector optimization problem, the objective function often conflict with each other. Consequently, the concept of optimality for single objective optimization problems cannot be applied directly to vector optimization. In this regard, the concept of efficient solution is more useful for vector optimization problems. Given an open set and a function, a point is said to be efficient point if and only if there is no y in X satisfying this condition. It is bigly efficient if it satisfies this strict inequality. The variational like inequality problem is to find y in X satisfying this inequality, and vector variation like inequality is to find y in X. There is no X in X satisfying this inequality. Similarly, it is a big vector. If this inequality is strict, then it is called weak vector variation like inequality problems. And consider the following vector variation like inequality problem, generalized form of above problems as generalized and generalized weak. If alpha equal to 1, then these problem reduces to the problem studied by Carson. So this is the basic result, a relationship between these two problems. Let f be a differentiable function, and if this gradient equal to f is a g alpha univex with respect to alpha, eta, phi, and b with phi t less than equal to 0. If y is the solution of vector variation like inequality problem and g dash is positive, then y is efficient solution to vector optimization problem. This is the example to justify the main result. The next theorem, if y is a weak efficient solution to vector optimization and g dash is positive, Then by is the solution of vector variational like inequality problem with the same alpha, eta, phi, and b. So if this f is strictly g alpha univax with respect to alpha, eta, phi, and b, if by is a big efficient solution of vector optimization and this g dash is positive, then by is also an efficient solution to vector optimization problems. A feasible solution is said to be vector critical point to vector optimization problem if there is a vector lambda in RP satisfying this condition such that this pairing is 0. So this is the Gordon theorem which is used to prove next result. Suppose X is a vector critical point to vector optimization problems and if F is pseudo G alpha univax on X with respect to same alpha, eta, phi, and b, then by is a bigly efficient solution to vector optimization problem. So suppose every vector critical point is a bigly efficient solution to vector optimization problem if and only if this F is a G alpha univax on X with respect to same alpha, eta, phi, and b, where this W is any vector critical point of vector optimization problems. Now we can relate the vector critical point to the solution of a big vector variation like inequality problem by using the previous theorem. Let f be a differentiable functions and this f is a pseudo G alpha univax with respect to alpha, eta, phi, and b satisfying this. Then the vector critical points to the bigly efficient points and the solution of a big vector variation like inequality problem are equivalent. So these are the references. Thank you, sir.
Okay, thank you for your presentation. So please ask next speaker. Yeah.
The next participant, Charan Kumar G. Sobalata. Sir, Charan Kumar or Sobalata, who will present the paper? Hello? Charan Kumar. Hello? Charan Kumar, are you there? Sobalata. Please respond.
I think they are not present, I think.
Okay, sir.
So please ask the next.
Okay, sir. Okay, sir. Okay. Lac Halibram, are you there? Hello?
Yes, yes.
Okay, are you present the paper now?
I am here, sir.
Okay, right. So, due to time constraints, please focus on the main results. And if there are any examples, please cover the examples. Only 5 minutes. Within 5 minutes, please cover the focus on the main results and examples if there any. In 5 minutes, you have to
Can you see my presentation? Hello, sir.
Start.
This
Yeah.
work in the...
Please continue your talk.
Hello, sir. Good evening. This work in the title Well-Poisonedness and Exponential Stability for Attenuation Ecosystem with Thermodivisive Effect. This work is composed by introduction, main results, and exponential decay. Introduction. We know that the classical Timoshenko is given in 1920 by the following from, and the constitutive elastic laws are, where x is retangent and t is the time, p is the transverse displacement, and psi is the rotation of motor axis due to bending. Here, ρ1 equal and ρ2 equal, where ρ is the density, a is the cross of air, and E the second moment of the cross air. by S dot not the shear force, and M is the bending moment. We know also that the any system is stable or not. So the first stability result of the Timoshenko was due to Svian, where proved the system is exponentially stable if only if the condition of equilibrium speed hold. Condition 1. Since then, there are so many stability results on partial damping system under the assumption 1. And the other assumption, we can see the reference under or other. Recently studied have appeared on the Timoshenko beam with model thermal and mass diffusion effect. By motivation of previous work, we present in this paper a new study for a Timoshenko system with thermal diffusion effect. We establish exponential decay of the system with boundary condition in the assumption of equal speed. So, in this work, we state the following system, following 1-1, with initial condition, and we consider the following boundary condition. We establish exponential decay of the system 1-1-1-3 if the assumption of equilibrium speed hold. We assume the matrix Psi is divinely positive. Main results. We give the well-poisonedness of problem 1-1-1-3 firstly. We given the following space where equipped if the product scalaire divided by for E the system Y equivalent the proper abstract problem Cauchy system 2-1 and an operator linear divided by with the domain. Theorem 1. Let U0 appartient this space. The problem 1-1-1-3 admit a unique solution. In addition, the solution is a classical solution. Appartient this space. Remark. To prove of theorem 1, we will show that the linear operator A is monotone and maximal. See reference 2 and 6. So, on defining energy of the system 1-1 defined by this relation, it is easy to get the derivative the energy is equal. The stability results states the following theorem. Theorem 2. Let phi psi theta p be a regular solution of problem 1-1-1-3 and let 1 for hold, then there exists two constant positive lambda 1 and lambda 2 such that the energy is less than or equal this relation. On defining that lam1 on defining the function g dt by where the function g satisfies that there exists two constants c1 and c2 and c2 such that la derivative de g dt less than or equal. To prove the lemma on utiliser inequality de Poincaré and Young and Cauchy-Schwarz, and this estimate where C1 equal and C2 equal. Lemma 2 on defining the function h de t defined by la derivative du function g h de t less than or equal. On proof the lemma by using inequality Poincaré, Young and Cauchy-Schwarz. Lemma 3 on defining the function a de t by this relation. Assumption of the condition 1-1 hold, then the function a de t satisfies for any t positive, a derivative to a de t less than or equal. By using 1-1 and 1-2, we have, which noting the following estimate. So, on defining la function Lapenoff such this relation, where n and 1 and 2 be determined later. It is easy to get that there exist two positive V1 and V2 such that in aiding by Young inequality we obtain that there exists a constant and 0 positive such that we can that take n large enough such that n1 and 0 positive to get 350 with V1 equal and V2 equal. Proof of theorem 2 of combining 2, 3, 1, 3, 3, and we get la derivative du Lapenoff function less than or equal this relation. Taking epsilon 1 equal and epsilon 2 equal and epsilon 3 equal, we obtain la derivative de Lapenoff function less than or equal. So we take an for positive such that this relation is positive. We for fixed and for we chose and to positive such large this relation is investigate. And then taking an positive such large enough this estimate hold and this estimate hold. Therefore, there exists a positive V0 such that the derivative de Lapenoff function less than or equal. By 3.16 and by 3.15, we see that la derivative ODT less than or equal this relation. By meaning this constant, we have the proof of theorem 2. This some reference used in this paper. Thanks for listening and following. Thanks for listening and following, sir.
Thank you, Ibrahim. Thank you very much. Any questions from audience? Okay, I think there is no question. So thank you very much for your presentation.
Thank you, sir. Thank you.
The next participant.
Yes, it's next one.
Hanan Chauhal, Mustafa with Yorao. Who will present the paper? Hanan Chauhal. Are you there?
I am here.
Yeah. Are you ready to present the paper?
Yes.
Hanan
Yes,
Chauhal.
yes.
Yeah. Okay. So only your time is 5 minutes. Due to time constraints, just you have to focus on your main results and if there are examples, if there are any.
Yes. Okay.
Did you understand?
Yes.
Okay. Thank you.
Good evening, everybody.
Time starts now.
I am Hanan Shwiel, and I am a PhD student from University of Jijel, Algeria. My topic today is existence of a solution for differential inclusion governed by a mixed semi-continuous set-valued mapping. This work prepared by me and Mustafa Fatih Yaro. Our presentation will be started around the 3 parts. Firstly, we start with an introduction. Secondly, I will give you some definition we are using throughout work. Finally, I will present my work to you. Our aim in this work is to prove a general existence results for one in the convex case with a mixed semi-continuous set-valued mapping. The result is based on a set-valued version of the fixed point theorem. Latino negative F and G B2 set-valued mappings with closed values. We considered in differential inclusion 1, where F and G have no convex values. F measurable integrably bonded and the lower semi-continuous. G satisfies the linear growth condition and mixed semi-continuous. Here the notation, the definition, and the basic results that are going to be used throughout the work. The decomposable set, upper semi-continuous, lower semi-continuous, the normal cone, and the projection. Now we give our results. We begin by hypothesis HF and HG such that F measurable, lower semi-continuous, integrably bonded. HG G measurable, mixed semi-continuous, and the intersection between G and the Claus-Ball empty. Let us define by inequality for where zeta and z the absolutely continuous solution of the next equation. Now we gave our results. Theorem assume that HF and HG are satisfied. Then for any x0 in Rn, the problem 1 admits at last one absolutely continuous solution. The proof is done in two steps. Steps 1, where we associate with f the set valued mapping Kf defined by this. Kf is close decomposable values because f is measurable with close values, and Kf is lower semi-continuous. Hence, Kf has a continuous selection. On définit the function g by this. G is integrably bounded unbounded subset of Rn, and for Htx, l'intersection of the multi-application G between B, the center G, Tx, no empty. Then by theorem 1-1, for any epsilon positive, there is a closed convex valued mapping phi, such that inequality 5 and 6 holds. Now we define the set valued mapping psi by this. We will prove that psi is subset of S, and the convex compact, and the graph of psi is closed. And using Cauchy fixed point theorem, there is x there is x in S such that x is absolutely continuous as an application. We consider the convex perturbation of this form, the so-called sweeping process. The sweeping process is an evolution differential inclusion governed by a maximal monotone operator, defined as the subdifferential of the indicator function of a convex or non-convex set. The problem is the following: 7. Let's recall first these results in the new convex K. That is when the set CT are uniformly prox regular. Proposition. Let's see set valued mapping with the no empty clause values such that C uniformly L prox regular and C Lipschitz. The solution of sweeping process 8, if and only if there is a solution of the differential inclusion 9. 8 and 9. Press. Now we are the start our result theorem assume that H1C and H2C, HF and HG are satisfied. Then for Hx0 in C0, there is an absolutely continuous solution of the differential inclusion 7. Let's X defined by and M is a so absolutely continuous solution of differential equation. Step 2, on define the P by this. Repeating step 2 of the proof of theorem 3.1, de obtient de convexity compactness and upper semi-continuous of P, and using Cauchy fixed point theorem, the set value the mapping P has at last one fixed point that is X in X, such that X in PDP.
Anin Chahal.
We
You have already 4 minutes over. Just only 1 minute is time is there. So you have to conclude within 1 minute.
Yes, yes.
Oh, thank you.
Finally, putting Q and B by the inclusion 10 equivalent to 11. Et this obtient the solution of the problem reference. Thank you for your attention.
So, thank you. Please ask next presenter because we are already going very late. Thank you for your presentation. Thank you.
Now the next participant is Imani Meshamma, Sabaran Luis, Mustafa Fatima. Who will be the present the paper? Okay, thank you. So just a small announcement. You have only 5 minutes time due to time constraints. Just you have to focus on the main results, and if any examples, just you have to touch it. Okay. Hello.
Okay.
Okay.
Hello, everybody, and welcome to my presentation. Today, I am going to talk about existence result for a non-convex truncated differential inclusion. Governed by me, I am Iman Isma and Lunis Sabrin and Mustafa Fathia. I divided my presentation into 3 parts. First, I would like to talk about the introduction. The notation and preliminary. We begin with the introduction. Sweeping is a particular differential inclusion governed by normal constant moving sets. This type of problem play an important role in elastoplasticity and dynamics. The naming of sweeping process is due that the fact that U is swept by C. Present, we are many interested to study the following new variants of sweeping process. Whereas standard for a Clark normal contour the closed set C as a derivative of U. Uniformly smooth set dependent jointly on time state and viscosity, and that is external for the apply on the system. In casting for the first time studied this problem where say dependent on the state, then various extents has been obtained by many authors. Recently, in the dimensional space, Adley and Lee provided a new result to the problem D, where the moving set depended on both time and state under the assumption that the moving set is closed, convex, and has some Lipschitz variable. In our work, I generalized the same result to the non-convex case. By considering the non-convex case that is for uniformly subsmooth set, and under the assumption that the set value mapping say depending on time, state, and viscosity is Lipschitz and is contrary to truncated house of Pompeo distance. Consider the unbounded set value perturbation for which only the element of minimal norm satisfies linear growth condition. Let's move on to some notation and preliminaries. We separable Hilbert space endowed with the inner product and the associate norm. Let S1 be a non-empty subset of H and the row positive. We define the house of row truncated distance between S1 and S2 by R2 is the pseudo excess of the row truncated of S1 over S2. The Hausdorff truncated equal the Hausdorff distance if rho equal plus l'infini. We begin preliminarily by the definition of the subsmooth set. One. Mention the definition of EQ uniform new subsmooth. Now we give some results that will be useful in the rest of this work. This proposition which gives us the upper semi-continuity of the subdifferential of the distant function. Let's turn to mannerisms. In this section, we are going to prove the mannerisms of this work. We give the hypothesis F, C1, C2, and IC3. As the previous hypothesis, we obtained the existence of a solution for the problem D. Of the theorem, we apply the catching up algorithm. We go through the following step. Step 1. Of approximation sequence using the Bull compact S of say. We prove that inclusion 6 is well defined. And we have the following inclusion 7 and inequality 9. The construction of sequence U and Vn. Define U and Vn by 9 and 10. Then we have the derivative U and Vn by 11 and 12. We define gamma by 13 and 14. It's easy to say that the limit 15 is equal to 0. Meaning at 12, 14, we have the inclusion 16. From 9 and 12, the derivative of Vn bounded by lambda. We conclude that Vn is equicontinuous with radio. We applied the Scolari-Ardella theorem to prove the conversion of sequence of Vn to some absolutely continuous mapping V. Prove that Un is a solution of a problem row. We apply Masolem. Conclusion: this work we studied the existence of solution for a class of unbounded second-order differential inclusion governed by non-convex time and state-dependent sweeping process with the class of uniformly subsmooth set. The fact that the Hausdorff distance of two unbounded sets may equal the infinity makes it difficult for the unbounded moving set to satisfy the classical Lipschitz continuity assumption. By an implicit discretization scheme, the existence result has been carefully. The standard assumption has been replaced by a truncated one. It is obvious that this kind of assumption is more visible than the classical one of the unbounded moving set. In addition to the unbounded perturbation, we just need the element of minimal norm satisfy linear growth condition. Finally, we give some references. And thank you.
Well, thank you for your presentation. I think this was last presentation or someone
Sir,
is
Hello, sir.
Yes, please go ahead.
Hello.
Hello, sir.
Yes.
Earlier one candidate has
Yes.
whose name is P.E. Satyanarayana, KVS.
Oh, yes.
He has some technical problem. Already
okay.
he put a note. So kindly, Satyanarayana, are you there? KVS Satyanarayana garu.
Yes, sir.
Okay, are you ready for presentation?
Sir, through mobile, sir.
Okay, whatever it is, the platform, sir, are you ready to give the presentation?
Yes, sir.
Okay, proceed.
Okay, sir.
Your time limit is only 5 minutes. Just
Okay,
try
sir,
to finish the main results and important conditions and examples. Okay, within 5 minutes due to time constraints. Starts your time now.
Thank you.
Hello.
Okay, sir. 1 minute.
Thank you.
Share my document.
Hello, sir. Hello.
Madam.
If I can present my work today. Do you hear me?
Hello. Hello.
My neighbor.
Sir.
Satyanarayana garu.
Sir.
So what is your platform? Phone, mobile or
Yes, sir.
laptop?
Mobile, sir.
So it is not possible to give your presentation through mobile, I think. So please please consult the technical assistance.
Another participant is also calling Bela Thrash. Maybe you can heard about her, Bela Thrash.
Her name is not in this list, sir. Name is not reflected in the list, sir.
Okay.
Sir, actually, name is not in the list. We will consider in the afternoon.
Yes, sir.
Yes, there is 2 more session, paper presentation session. I think it.
They will send. They will give a presentation in the evening. Javed
Yeah,
Ali is also
because
waiting.
we are already running late, and
Sir,
Professor
please,
Javed Ali is also already waiting for his invited talk.
Sir, please on your video one time, please.
Yes, please. So Dr. Javed Ali is already waiting for a long time. We are going late, so I think anyone who left for their presentation, please accommodate in the evening session.
Hello, Thakur sir.
Hello, Javed.
Or now?
Hello, ma'am.
Hello.
Professor Chu, how are you?
I'm fine.
Hi, Professor Chu, how are you?
Your mic is muted, Professor Chu.
How are you?
Good.
Nice to meet you here.
Again, sir.
Thank you. Same here, sir.
Yeah.
Professor Thakur.
Thank you, Professor Babu, for giving me opportunity to be part of your conference.
Thank you very much for your time you spent on this international conference, and you are chairman for this paper presentations too. For that one also, I thank you very much. And Professor Cho, namaste sir. Professor Cho.
How are you?
Fine, sir. How are you, sir? How is your father, sir?
Now a little recover from serious problems.
Oh, very good.
A little okay.
Okay.
That's good.
Okay. I'm very happy, sir, that today you are also participating. Thank you very much, sir. And today's evening we have some valedictory functions, sir, at about 7:30 p.m. 7 p.m. at about 7 p.m., sir. Please attend,
7
sir.
p.m.
Please. And I also welcome.
In Korea, 9 o'clock half.
In Korea, it is
Korea
about
time, 9 o'clock half.
Yes.
9 o'clock half.
Yes. In Korea, time will be 9:30. Yes.
Yeah. I will be here at that time. I will be here at that time, 9 o'clock half.
Okay.
Yeah.
And Professor Thakur, please attend that in
Yes.
function, sir. And Javed Ali, sir, you too, please attend that valedictory function. It will be at about 7 p.m., 7 to 7:30 p.m.
Okay, sir.
Yes. Sure.
Let us come for the today's lecture by Javed Ali. He is associate professor of Aligarh Muslim Department of Mathematics, Aligarh Muslim University, and I welcome Professor Javed Ali for his invited talk. Existence of solution of infinite system of Helfer fractional BVP in tempered sequence spaces, and its chair is Professor Anita Tomar. Please, I welcome Professor Anita Tomar also.
you, Professor Thakur. And good afternoon, everyone. Am I audible?
Yes,
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 yes.
madam.
Yes, you are
First
audible, ma'am.
introduce Professor Javed Ali.
Okay. Okay. Good afternoon. So it's my honor to welcome Dr. Javed Ali from Aligarh Muslim University. He has done his postdoctorate from NBHM PDF from IIT Kanpur from 2008 to 2010. He has received many scholarships and he has done many projects also. He has total 11 and a half years of teaching experience. And total academic plus research experience is more than 36 years. He has visited many countries to present his work and attending invited talk to do some work in collaboration. He has visited USA, Spain, Portugal, Japan, South Korea, Taiwan, Poland, Vietnam, Brazil, Nepal, Lebanon, KSA, Oman, Tunisia. The list is very long. He is very active researcher. And I know him personally since 2010. He has 1005 citations in Google Scholar and 348 citations in Scopus. He has also received UGC Startup Research Project of 6 rupees.
Ma'am, your voice is not audible, I think.
Besides this, he has PG Merit Scholarship, UGC University
సూర్యనారాయణ గారు మీరు స్టాప్ చేయండి షేరింగ్. ప్లీజ్ స్టాప్ యువర్ షేరింగ్ సూర్యనారాయణ గారు. అయితం పి సత్యనారాయణ గారు ప్లీజ్ స్టాప్ యువర్ షేరింగ్.
Hello, am I audible?
Yes,
Yes,
Dr.
yes,
Javed, you
yes.
are audible.
It is audible.
So can I start?
Yes, you start your talk.
Please. Share a
Good
screen,
afternoon,
please.
all of you. First of all, I would like to thank you, the local organizing committee of this conference, for giving me the opportunity to share my recent work. And I especially Professor GBR Babu Saab, and I also wish basically his life.
Please share your presentation. Please share your presentation.
Yeah, yes, I am going. And I also wish the basically happy and healthy life after your retirement, and hope you will continue your all academic activities as in past you have done. So today now I'm going to discuss this. So I think my screen of my presentation is visible, all of you?
Yes, it is visible. Thank
Okay. So in today talk, I'm going to discuss the basically two existence result for the infinite system of Hilbert fractional boundary value problems in the tempered sequence space. So for this, of course, we will use the well-known technique from the fixed point results. So outline of my talk is just first of all in this first section, introduction and technical background. I will recall some fixed point results and then Hilbert fractional derivative and differential equation and measure of non-compactness and measure of non-compactness in the tempered sequence spaces. Then in section 2 and 3, I will state the basically some results, existence result for the solution of the Hilbert fractional differential equation. Then I will have a basically two numerical example in the support of the results, and then we have reference. So in this conference, in 1.5 day, of course, a lot of people heard about basically fixed point results and fixed point. So of course, this conference was started with the keynote talk of the Professor Y.J. Cho, one of the expert and well-known researcher in this area. And then Professor Imdad, Professor B.S. Thakur also delivered the nice talk on iterations. Professor D.R. Sahu, Professor Anita ma'am, of course, and ma'am is also doing very good. And some more, Professor Murthy Saab and Basile Berende and Professor Pansab. So generally people talk about the basically fixed point theorem, its existence problem, or some applications, interesting applications, and how to approximate the solutions of nonlinear problems, etc. So so that's why I will not go into too much detail of the fixed point theory, but just I recall the some these historical comments on the basically fixed point approach. So we know that basically, of course, several results in the direction like either it's a basically Banach contraction principle or Brau's fixed point theorem there. But original idea of this fixed point approach was the basically in the work of the great French mathematician Henri Poincaré. So he was the one of the basically founder of fixed point approach, and basically he used this approach in the application of the several problems, physical problems, including especially mathematical analysis and classical mechanics. So basically Poincaré was the I can say perhaps was the basically first mathematician who used the fixed point approach in the application part. Fixed point theory is one of the important subject. Even today, this is a very fast growing subject, and I think it's due to have nice applications in the basically mathematics, within mathematics and outside mathematics even. So we know basically in outside mathematics, like in computer science, fractals, image recovery problem, image compression problems, and in economics and game theory, a lot of things is basically outside the mathematics. So that's why we can say that it's basically fixed point theory is a basically bridge between the pure and applied mathematics. So that's why it's a basically important subject which played a central role in the basically problems of function analysis and topology. So that's why this is a basically bridge between the pure and applied, because we know a lot of nice results to show the existence of problems of differential equation. Okay. And we know that what they mean by the fixed point theory, and of course we know what they mean by the fixed point results. So as we know that all the maps does not have the basically fixed point. So fixed point results, one can say that these are the results if we put some condition over the given map or on the space or on both, so that we can have the guarantee of a fixed point of the given mapping. So a topological space is said to have the fixed point property if every continuous, in particular non-expensive, people say non-expensive. So if every continuous self map of X admits at least one fixed point. Unfortunately, this fixed point property is basically a topological property. So this is very nice thing with this property. From the classical results, this is a very important result, that is the Banach fixed point theorem, and Banach itself proved this result in 1922. So almost it is 100 years. So for this theorem. Okay. So basically he considered the Lipschitz map whose constant is less than 1. Then he said that every self contraction of a complete metric space has a basically unique fixed point. So in general, we can say it has a basically three consequences. First of all, it existence of a fixed point, and fixed point is unique. And if we consider the sequence of Picard iterates, then that sequence also converges to the basically fixed point. So means by this theorem we can also approximate the or estimate the fixed point of the contraction map. After this theorem, there are a lot of generalization of Banach fixed point theorem. Either it's basically for discontinuous map, especially Cannon and Chatterjee map, and later on a lot of generalization. So Professor Cho, Imdad, and other people, Professor Babu, also basically done a lot of things in this directions as well. So in Banach fixed point theorem, and of course, nice generalization for the multi-valued map. So that's why very useful in the fractal, how to develop the basically fractals, generate the fractals and differential inclusions like that one. But if we take Lipschitz constant, that is say alpha equals to 1, then Lipschitz map become known as the non-expansive map. So as we know that for the non-expansive mapping, if we consider, for example, translation and so many others map, they don't have the basically fixed point. So question is again same, under what a set of condition we can have the guarantee of a fixed point of a non-expansive mapping. So in 1965, three famous mathematicians, one is the Browder, another is Kirk and Gohde, they basically solve the same problem, means fixed point of the non-expansive mapping, but under different set of conditions. Okay, so Browder proved this theorem and the uniformly convex Banach space. So this theorem states like this: if we have a non-expansive map which is defined on a closed bounded convex subset of a uniformly convex Banach space, then it has a basically at least one fixed point. So from means for here we have the only guarantee of a fixed point. We cannot talk about basically means uniqueness and other thing. On the other hand, basically Kirk proved studied the same problem, but basically he studied the problem in the reflexive Banach spaces using the normal structure. So of course, both the problem has own importance. This broader fixed point theorem is highly applicable in the study of existence of solution of differential equation. And Kirk fixed point theorem is a nice thing. Means with the basically geometry of Banach space and other issues in the function analysis. Okay, but if I consider basically my class of continuous map, so for the continuous map, first theorem was given by systematic basically that is first theorem was given by this Brouwer, and that is known as the Brouwer fixed point theorem. So basically, Brouwer considered the continuous map, which is defined on a closed unit ball in Rn, Euclidean Banach space, or you can say finite dimensional Banach space. Then T has a basically fixed point in C. So this is a basically most celebrated fixed point theorem. Also, of course, this is a basically part of algebra because in general we divide or we characterize the fixed point theory in the three major basically categories, like metric fixed point theory, algebraic fixed point theory, and discrete. So this Brouwer fixed point theorem is belongs to the algebraic fixed point theory. So proof of this one is of course not so trivial, and using this theorem, if we remember the Professor John of course Nash, he basically utilized this theorem to study the basically Nash equilibria in the economics, and of course for that research he got a Nobel Prize. Okay. And if I consider this Rn just one dimensional, simply R, then it's a very nice theorem in the real analysis. So generally all the students of undergraduate level, they have gone through or they basically know that theorem in the real analysis case. This Brown fixed point theorem is for the finite dimensional Banach spaces, but infinite dimensional spaces, Banach spaces are more important because due to their application. So especially like sequence spaces and space of the continuous functions and polynomial and etc. So that's why a fixed point results in the infinite dimensional for the continuous mapping is also basically equally interesting. So as you might remember, Kakutani basically produced basically one example in L2, and he defined a continuous map and then show that that continuous map defined on a closed unit ball in L2 need not have a fixed point. So what we can say directly one cannot extend Brouwer fixed point theorem for the infinite dimensional Banach space or arbitrary Banach spaces. So in 1935, J. Sauder extend this theorem, Brouwer fixed point theorem, from finite dimensional Banach space to arbitrary Banach space. So basically, my set or ball was closed and of course convex. It was bounded. So basically, he considered the here compact convex subset of a Banach space. So if we have a continuous self map which is defined on a compact convex subset of a Banach space, then it has a basically at least one fixed point. So this is the, you can say, infinite version or infinite dimensional version of the Brouwer fixed point theorem. And of course, this theorem is also has a lot of application, especially in the differential equations. Means to study the existence or solution of system of differential equation or simply differential equation. So here a condition of the compactness is a little bit tight. Means this is basically heavy conditions. So of course there are a lot of generalization like Takno prove this theorem or extend this theorem for the locally convex spaces and some others means results are available in the literature. So basically this compactness of the subset is a basically tight condition or heavy condition. So later basically Darboux basically proved fixed point theorem that is known as the, I will of course recall that theorem in the next slide. So basically he just weakened this condition of compactness. So basically you use the idea of the measure of non-compactness and prove some fixed point theorem. Okay. So now I come to the basically fractional differential integral equations. So in the last some year, this area is very active and very productive. A lot of nice problems studied in this direction. And so one of the important derivative in this direction are the basically Riemann-Liouville and Capito derivatives. So a fractional derivative contains both Riemann-Liouville and Capito fractional derivative that is basically introduced by the Hilfer, and that is known as the generalized Riemann-Liouville fractional derivative. So it's a basically combination or generalization of the both the derivative. So for such kind of the work in the last some years, we have nice papers and nice results in the direction. So references are given here. Okay. So by using the theory of measure of non-compactness and Darboux fixed point theorem, Rabbani and Hazarika study the solvability of the system of fractional differential equation in tempered sequence space. So I'm going to define what I mean by tempered sequence space. Then Golami studied the existence of solution of infinite system Hilfer fractional boundary value problems in C0 space, means space of the sequences, which is a convergent sequence converges to 0, and LP space. P is greater than equals to 1. Okay, so motivated by these two papers and their results, just we study the Hilfer fractional differential equation with boundary conditions in the tempered sequence spaces. And for this, we will utilize we will basically utilize the idea of measure of non-compactness and Meyer-Killer condensing operator. So and the fixed point theorem related to this. So I'm going to define. So first of all, what is this differential equation? So this equation d a plus gamma eta yi plus git of y equals to 0. This is basically called Hilbert fractional differential equation with boundary condition yi a equals to yi b equals to 0, where t in open interval I running over the capital N set of integer positive integer natural number. So where this gamma parameter in the semi-open interval 0 to 2 and eta in closed interval 0 1. So this capital D a plus gamma n is called basically known as the Hilbert fractional derivative of order gamma and type eta. And these are the basically function git of y equals to cit plus fi of t y1 y2 yn. And so so these are the basically continuous function defined over the closed interval. This one. So this is basically my system, infinite system of the Hilbert fractional differential boundary value problem. Now we define a Riemann-Lebesgue fractional integral of order gamma of Lebesgue measurable function by this I a plus b minus gamma of this W2. So we define by this expression. Okay, next we define right side Riemann Lebesgue fractional differential derivative of order, which are absolutely continuous function W for the absolutely continuous function. So this is notation, of course, for the just generalized and d gamma. So by this expression, and similarly, just we can define the Hilbert derivative fractional derivative of order gamma and type eta of function this W2, which is given by this equation 1.2. So this is basically definition of these are the definition from the literature. Okay. So here we have some observations. So when if we take eta equals to 0, then definition 3 implies the Riemann-Lebesgue fractional derivative, and eta equals to 1, this implies left or maybe right side capital derivative. So just we can have in this way, my derivative will be in this way when t is greater than a and t is basically less than b. And so this was basically my 1.1 is basically my problem. So for this problem, we have a green function which is defined. So for this problem 1.3, so let w in the L of a b be given function, then the solution of this differential equation system of Hilbert fractional differential equation with boundary condition given by this integral equation. So of course this is a standard idea. Once we have the basically differential equation, one can convert it into the integral equation, and so solution of this integral is basically same as the solution of given differential equation, where this is the basically my green function of this integral equation. So h of tr is given by this expression 1.5. Okay, so this is lemma here. So if for all mr in the basically this square maybe rectangular square, so maximum of mod of h mr, just it's a basically definition given by this expression. Okay, so this is the basically maximum of the this green function. Suppose x is a real Banach space and r is a non-negative real number set, b be a subset of x, so we denote b bar and convex of b, that is closure and closed convex hull of b respectively. So moreover, let us denote by the family of the non-empty bounded subsets of x, mx, and nx is the subfamily considering all non-empty relatively compact subsets of x. So for this family, one we can define a map known as the nu is defined from the mx to r plus is said to be the measure of non-compactness MNC if satisfying these conditions. So the family, a kernel of nu is basically collection of the all those points for which nu of b equals to 0. So this is basically a subset of x. B1 is a subset of b, then this, of course, measure of non-compactness here, nu of V1 is less than equals to nu of B, and nu of B closure is same as nu of B, and nu of convex closure of B is same as the nu of closure, and then nu of this is a something for the convex combination here. So this is x B1 plus 1 minus S B2 is less than equals to S nu of B1 plus 1 minus S nu. And if Bn is a sequence of closed sets in Mx such that Bnx plus, so this is basically decreasing sequence of closed sets, and limit of nu n of Bn is 0, then this intersection of all Bn is non-empty. Okay. So another important regular measure of non-compactness is so-called the Hausdorff measure. So of course, Kuratowski measure even, and another one is the Hausdorff measure. And of course, we have some more concept of the measure of non-compactness in the literature, and some weak notions also. So here it is defined Hausdorff measure means measure of non-compactness just by for a given set. In FIMA of the all positive epsilon, where W has a finite epsilon net in X. So this is the basically Darboux fixed point theorem. So it says that let C be a non-empty closed bounded convex subset. From where I can. Okay. Subset of a Banach space X, and G be a continuous mapping defined on a, of course, self map defined on a C, such that there exists a constant M in M less than 1, of course non-negative, with the property nu of GC is less than equals to M of GC, then G has a fixed point in the set C. So next we have a basically theorem for the condensing operator, U condensing operator. So let V1 and V2 to be arbitrary measure of non-compactness defined on the set X1 and X2 respectively, and let L is a operator be an operator from X1 to X2, then L is called mu1 mu2 condensing operator if it is continuous and u2 of LC is strictly less than by mu1 of C for every bounded non-compact subset C of X1. And if we take X1 equals to X2 and nu1 equals to nu2, then L is called the V condensing operator. So this is basically my definition of Meyer-Keeler condensing operator. So X is a Banach space, and nu be an arbitrary measure of non-compactness on X, and C be non-empty closed bounded convex subset of X. Then an operator from C to C is a Meyer-Keeler condensing operator if for any positive epsilon there exists a delta such that mu of W is greater than equals to epsilon, but strictly less than by epsilon plus delta. This implies that mu of L W is strictly less than by epsilon for bounded subset W of C. So this is basically regarding, we know the very famous Meyer-Keeler contraction operator. So corresponding to that, when we define Meyer-Keeler condensing operator using this measure of non-compactness. Okay, this is a very important theorem, and then it says that if we have a Banach space and nu be an arbitrary measure of non-compactness on X, and C be non-empty bounded closed convex subset of X, and if L is a basically operator self operator on C is continuous and Meyer-Keeler condensing operator, then L has a fixed point. And set of all fixed point of L in C is also compact. So this is basically about the topological structure of the fixed point set as well. So we will use this result to prove our main theorem. Now next one is the basically about the tempered sequence spaces. So idea of tempered sequence space initially introduced by Banas and Krasnensky. And so what is this idea? If we have a basically real sequence, fixed real sequence alpha, such that alpha is positive and the sequence is non-decreasing, then one can define a one tempered sequence corresponding to C0. So it's supposed denoted by V. Y is a collection of these sequences such that alpha I also converges to 0. And of course, this form a vector space over the field of real complex. and this space V is denoted by the C0 alpha. So this is basically my tempered, and of course it is also a Banach space, as this is a normed space, so we can define a norm of Y. Of course, C0 alpha means over this space C0 alpha just by supremum of alpha I, because alpha is positive, so no issue. So alpha I mod of yi. So this is similar to the basically norm of C0, because in case of C0, just we take supremum of the mod of yi. Okay, so this is the basically my one tempered sequence space, that is C0 alpha. Means if we multiply by basically some positive, of course, but fixed real sequence, positive terms are positive and non-decreasing, then still it is converged to 0. Then this is called the basically tempered sequence space, and of course this is C0. For the LP, Rabbani and Hazarika introduced basically or defined in this way, that is denoted by LP alpha. So it's a collection of the sequences such that this series is basically summable. Which series? Alpha IP and mod yi whole power p, where p is greater than or equals to p. So it is again basically, if I take my alpha is constant, that is 1 1 1, then it's basically we have the simply originally LP spaces. And for this space, they just discuss the some measure of non-compactness, and of course it is again a vector space, so that's why one can define a norm, and so norm on this space of an element, norm of y on this space LP alpha, is just in the same fashion. So summation of alpha IP mod yi whole power p, and then whole power 1 upon p. And of course this is also a Banach space with respect to this norm. So here just we discuss our problem in these two spaces. Anyway, now in the Banach space C0 alpha, the Hausdorff measure of non-compactness can be formulated as like this. So a Hausdorff measure of non-compactness in this space with respect to this space C0 alpha, and of course this is the basically bounded subset from the C alpha, that is B alpha. It is basically limit of supremum where y running from the basically capital B alpha, it's a supremum of the alpha k mod of yk, where k greater than or equals to 1. And of course here B alpha is a subset of MCL. So this is basically all. So, where yt is a basically secant, it's basically from the just C0 alpha for t in the closed interval 0. Similarly, on the space LP alpha, one can define the Hausdorff measure of non-compactness in this way. It's a limit n tends to infinity, supremum of just summation of this norm, that is alpha k p and yk whole power p, and then whole power p. So these are the basically, one can easily prove that these are the basically Hausdorff measure of non-compactness on the C0 alpha and LP alpha. So just we can have the proof in the sum now. So now this is the basically my first result, that is the existence criteria or existence result for the basically my infinite system of the Hilbert fractional boundary value problem in the tempered sequence space LP alpha. So we have the basically these three assumptions. So if we have these three assumptions, then I can state basically and with two more assumption is here. So this is basically my result of this section. Under the assumption M1 to M3, then my basically infinite system of Hilbert fractional differential equation with boundary conditions 1.1 has at least one solution yt, of course, is a sequence, whenever this estimate is strictly less than 1. Of course, where 1 upon p, p and q are conjugate, there 1 upon p plus 1 upon q equals to 1, such that yt in the LP alpha. Moreover, this yt is the basically kernel of this measure of Hausdorff measure of non-compact. So idea is again proof. A step of the proof is almost, first of all, corresponding means for the given differential equation we write it is the integral equation. Then we define a operator, integral operator, and then we prove, of course, using this theorem, theorem 8. So we will prove that means given operator is basically continuous and operator is Merkelt condensing operator. Then we can say that it is basically has a fixed point, and that fixed point is the solution of that L, which is the basically solution of the integral operator. So proof is of course it has some steps, so that's why, and it is a little bit lengthy, so I'm not going to discuss the proof here. Okay, next one. Okay, this is the basically another existence result in the tempered sequence space C0 alpha. So here we have the different set of conditions. Assumptions are different here. Just N1. So we have the functions Gi, which is defined closed interval, Cartesian product R infinity to R, and this function P from defined in this way, P by T equals to T, G1 T, G2 in this way. Okay, all functions are equicontinuous at every point of the sequence space C0 alpha, and the sequence alpha I CIT is converging uniformly on closed interval 0, 1 to a 0 function defined on the closed interval AB, and of course where Ci is non-negative real valued continuous function. This okay, and we have this condition that is a bound of this function fi of t1. So mod value of fit of y1, y2, y3 so on is less than equals to dit plus hit supremum of yk. Dit is the same as the condition as referred in the condition 2 here, and this hit is a non-negative real value continuous function defined on the closed interval a to b, and hit is basically eq bounded on the closed interval. So this is sequence equivalent. So with these three assumptions and with these two more assumptions, then we can state our existence result in the tempered sequence space C0 alpha. So under the hypothesis N1 to N2 and these more assumptions, infinite system 1.1 has at least one solution, y equals to y2 in the C0 alpha. And of course, just we have this estimate means bound. Just to show the operator is a condensing operator, so that's why we need this condition. So these are symbols. So again, proof is systematic, but of course we have to do in some steps. 3-4 steps is here. So these are basically two main results of this talk. Now we have some numerical examples. So of course we have also done some numerical simulation using the MATLAB, but as time is short here, so I couldn't include all the basically those numerical simulations here, but just I stated these two numericals. So this is example 11 or 1.1 we can say, which is in the basically support of basically first theorem, that is the existence criteria in the LP spaces. So this is basically my infinite system of Hilbert fractional boundary value problem defined by 4.1, where CIT equals to square root of t cos of it over I square, and this family of function fi t y1 y2 is defined by this series e y z t over k square 1 plus I into yk over 1 plus k minus I whole power 4 yk power 4, and I is running over 1 to a of course positive integer, and where my capital Y is greater than 1 and which equals to gamma, which is less than equals to 2 because this order, eta is 0.5 and Z equals to capital Y plus eta 2 minus Y. So here EYZ is basically my two parametric meta left function, which is basically a generalization of the exponential function in the complex. And A equals to 0, B equals to 1 means my closed interval 0, 1. So this is basically a meta left function is defined by this series t to power k over gamma yk plus z, y greater than 1 means positive and z in C. So if we consider this system, and we verified, of course, in our paper, it satisfies all the basically condition of the theorem 9 point, of course, main theorem as well as the our main result means existence result in the LP. So that's why it satisfies all the basically, and it has a basically solution. Same if I consider this next example, which is in the support of theorem 10, that is the existence criteria in the C0 alpha space. So my differential equation is exact same, but these functions are different. So CIT equals to t minus a, b minus t, and with a Lagrange function EYZ of minus IT over 1 plus I to the power 4. And this family of function is defined by just this summation k equals to I to infinity sine t over 1 plus I whole power 4 into yk. In the we can define in this way. And all the other parameters are similar to previous example, like a equals to 0, b equals to 1, and gamma and eta. So these are the similar to this, and then so that it has a basically solution because it satisfies all the basically condition of basically my theorem 10. Okay, so these are the basically two supportive examples in regarding our band results. Numerical simulation also we have done, but they are not the part of this talk now. Okay, so these are the references in this direction, and this is basically my joint work with my PhD student in Imamul Haq and Professor Mursali, my department. So I'm new in this area, and I'm trying to learning and trying to do some good work in this direction. Of course, for applications of fixed point results. So these are basically my references. Thank you very much for your kind attention and your. Hello. Hello.
Sir.
Hello, Professor Anita,
Thank
ma'am.
you, Professor Jade Ali,
my
sir,
side,
for his
talk is
lecture.
over.
Thank you, sir. Sir, any questions from participants, please?
Hello,
Sir, Professor Anta Tomar, madam.
Hello, Professor Anta Tomar, madam. Please ask about the questions.
Hello, Anita, ma'am. Are you there? I think she left the meeting.
Okay, okay. Any questions, please? Please, yourself you can ask, Professor Ali, Javed Ali.
Yes, sir.
You can ask directly. If there are any questions, please ask me. You ask.
Okay, if so, questions and suggestions and queries are welcome. So maybe you can write me, and my email ID is given on the front line. So if you have any question and suggestion,
My
please
dear
ask me.
participants,
Otherwise,
any
later on
questions,
you can
please?
contact me.
My dear participants, if you have any questions, please raise your hand through internet. Sir, no questions are there. Thank you very much for giving a lecture. And Tomar, madam, I think there is a technical problem from there. Morning also we are facing a little bit technical problem. I think that's the reason she is not presenting here. Madam, Anita madam. Okay, Javed Ali ji.
Thank you,
Thank
Professor.
you very much.
Okay, I will tell. Thank you, Professor Javed Ali, for sparing your valuable time to deliver your lecture in this international conference. I am very happy to see you here, and thank you very much.
Thank you, sir. Thank you very much. I am also very delighted to have with you and meet you and wish you a very healthy life after your retirement. I think you are going to retire maybe this month.
Maybe maybe an honorary professor. I may be in the department as honorary professor.
Okay, so it will be good for us. So we will keep in touch with you again, sir. Okay, thank you.
Let us
Very
be
much. It's
in
very
touch
nice.
with you. Very good, very good. Thank you very much for your wishes, and thank you very much. Fine, thank you.
Hello, madam. Anita Tomar, madam.
Professor Anita Tomar, madam, are you available there? Anita Tomar,
Thank you, sir. Now I request Dr. G. Nanarji Rao Garu to deliver his lecture on pseudo-complemented almost lattices. I also request Professor Sheikh Kalisha Wali, sir, Department of Mathematics, JNTU Vijayanagaram, to chair this session. Welcome, Kalisha Wali, sir.
Thank you, madam. Can you hear me?
Yes, sir. You are audible, sir.
Okay.
Thank you, sir.
My name is Sheikh Kalisha Wali, Professor of Mathematics at JNTU University College of Engineering, Vijayanagaram, Andhra Pradesh, India. I'm an alumnus of this great Andhra University, where the conference is going on. So, with due respect on my teachers, our respected teachers from Andhra University, highly intellectual people from all parts of the globe, invited speakers, research scholars, students, a good afternoon and hearty welcome to this session. I deem it as a great privilege to be a part of this international conference, organizing in connection with the superannuation of my teacher, Professor GVR Babu Garu, who is the registrar of the university, a good teacher, excellent researcher, man with values, and moreover a good human being. Before introducing the speaker of today's session, Dr. Nanaji Rao, I wish to thank the organizers for giving me this opportunity to chair the session. Now my present duty is to introduce Dr. G. Nanaji Rao to the audience. He is my friend. We are having 25 years of association. We are co-scholars and we are having friendship from 1996. Dr. G. Nanaji Rao, Galla Nanaji Rao, is serving Andhra University Maths Department as Associate Professor and heading the department. He received his MSc and PhD degrees from Andhra University. He received PhD in 2001. He is a Senior Research Fellow CSIR SRF from 2002 to 2003. Though he started his teaching to the PG students at Andhra University from 1996, he actually took up teaching profession in the year 2004. He started his career as a lecturer at VS Lakshmi Women's Degree and PG College. Later, he moved on to Andhra University in 2006. He joined as assistant professor in 2006. He elevated to associate professor in the year 2016, and he is waiting for the orders of the professor. Presently, he is head of the Department of Mathematics. His research areas of interest are lattice theory, in particular, almost distributive lattices. To his credit, he published 33 international journal papers. He presented papers in international and national conferences 14. He attended nearly 20 conferences. He visited China, Hong Kong to present his papers in the international conferences in the year 2007 and 2016 respectively. He produced a good amount of valuable research in collaboration with his teachers, Professor M. Swami Garu and Professor G.C. Rao Garu. He guided 9 PhD students. He is guiding 4 PhD students now, PhD students. He guided 8 MPhil students. Presently, 2 students are doing their MPhil under his guidance. He delivered invited talks 9. He chaired the sections 3. He acted as a resource person for different conferences 3. He completed one major research project funded by UGC, and he is a reviewer of the most prestigious journals, Mathematical Reviews, Southeast Asian Mathematical Bulletin, Asian European Journal of Mathematics. He taught almost all the courses related to PG programs. He wrote a number of textbooks. He discharged many administrative responsibilities, and he is also a member of many committees. With this brief introduction, I invite Dr. Nanaji Rao to deliver his talk on pseudo-complemented lattice, pseudo-complemented almost lattices. Now, I request Nanaji Rao to deliver his talk. Over to Dr. Nanaji Rao.
Is audible? Hello?
Yeah, it is audible.
Hello?
Yeah, it is audible.
Okay, thank you, Professor. Okay. Thank you, Professor Valli, for your nice introduction about me. First of all, I thank the organizers for giving this opportunity to present my talk entitled Pseudo-Complementation on almost lattices on the eve of our department senior professor, Professor GVR Babu Garu. all of you know very well that Professor G.V.R. Babu Garu is well known to everybody, and also is very very expert in fixed point theory, and he produced many PhD students and also MPhil students, both India and abroad. So I take this opportunity to present my talk. The pseudo complementation on almost lattices. So the concept of pseudo complementation star on almost lattice with 0 is introduced in this lecture and proved some basic properties of the pseudo complementation. So also proved that the pseudo complementary star on L is equationally definable. So this is actually one equationally definable class of algebras. It is well known that they form a variety. So that this is one important observation for this class of algebras, and a one-to-one correspondence between set of all pseudo complementations on an AL with 0 and set of all maximal elements of L is obtained in this lecture. It is also proved that set of all star elements, they form a Boolean algebra which is independent of the isomorphism of the pseudo complementation star on L. So it is it was Garrett Birkhoff's work in mid-30s that started the general development of lattice theory. Lattice theory. In a brilliant series of his papers, he demonstrated the importance of lattice theory and showed that it proves a unified framework, unrelated developments in many mathematical disciplines. Glivenko, Menger, Newman, Bohr, and Grazer, P.R. Halmos, Smith, Saz, M.H. Stone, Delworth, and many others have developed enough of this field for making it attractive to the mathematicians and for its further progress. The traditional approach of lattice theory proceeds from partial ordered sets to general lattices, semi-modular lattices, modular lattices, and finally to distributive lattices. So in one of my paper, myself and one of my student, Abtamu, is an Ethiopian, introduced the concept of almost lattices as a common abstraction of most of the existing lattice theoretic generalization of Boolean algebra. Here proved several equivalent conditions that enable to become a lattice. Further, introduced the concept of zero element in AL and observed that an AL can have at most one zero element, and it will be the least element of the poset. Also, they gave several examples of an AL with 0 which are not lattices and prove some basic properties of AL with 0. They established necessary and sufficient conditions for an AL with 0 to become lattice. Also, they introduced the concept of simple AL and gave a set of identities for an AL with 0 to become simple AL. So in this lecture, we introduced the pseudo complementation on an AL with 0 as like in lattice and proved that it is equationally definable and observed that there can be more than one pseudo complementation on an AL. It is well known that in case of lattice, if pseudo complementation exists, then it is unique. But in the case of AL, there can be several pseudo complementations. And in our lecture, we give example for that. An AL with 0 can have more than one pseudo complementation, and prove that the pseudo complementations on an AL and the set of all maximal elements, there is a one-to-one correspondence, and prove that the L star means all star elements form a Boolean algebra which is independent up to isomorphism of the pseudo complementation. So all of you know very well that these are the very fundamental definitions which are available. Poset definition and lattice definition. Lattice means it is an algebra of type 2 with two binary operations, join and meet, satisfying commutative, associative and absorption laws. Such algebra is called a lattice. And in any lattice, we have idempotent laws. That means x join x is equal to x and x meet x is equal to x. Okay. So this actually this concept was introduced by me and my teacher, Professor G.C. Rao. An algebra L join meet 0 of type 2 to 0 is called an AL with 0, almost lattice with AL means almost lattice if it satisfies these 8 conditions. So meet is associative. This is A join B meet C is equal to B join A meet C. A meet B meet C is equal to A meet B meet C. And A join B join C is equal to A join B join C. And these three absorption laws, and this is the zero element condition. So whenever any algebra satisfies these 8 conditions, such algebra is called an almost lattice. And we have gave many examples of an AL which is not a lattice. So this is one of the very important example that if you can define A meet B is equal to A and A join B is equal to B in an AL, then it is with respect to this, we define a partial ordering, define A less than or equal to B if and only if A is equal to A meet B and equivalently A join B is equal to B. This is a partial order relation. With respect to that partial order relation, we have the following lemma. So in a lattice, we have idempotence laws are hold. Similarly, in AL also there are idempotence laws. And if meet is one element, then the join is the other element. And meet is commutative when A and B are comparable. And A less than or equal to A join B and A meet B less than or equal to B. And these are some special absorption laws. And A meet B is equal to B if and only if A join B is equal to B. And join is also commutative when A and B are comparable. And any one of these conditions implies an AL will become a lattice. We proved in the next results. So an L is set to be directed above. For any AB belongs to L, there is a C such that A comma B less than or equal to C. So then such AL is called directed above. So then this is equivalent to an AL to become a lattice. That means L is directed above, meet is commutative, join is commutative, L is a lattice. So these 4 conditions are equivalent. And also there is another set of conditions for an AL to become a lattice. So A join B is equal to B join A, that means join is commutative. B less than or equal to A join B, L is directed above. A join B is the LUB of A and B in a poset. And A less than or equal to B join A for all AB belongs to L. B join A is the LUB of A and B in a poset, and L is a lattice. This is one set of conditions that an AL to become a lattice. And this is another set of conditions that an AL to become a lattice. So meet is commutative. A meet B less than or equal to A for all AB. A meet B is the GLB. B meet A less than or equal to B for all AB belongs to L. B meet A is the GLB and L is the lattice. So here we define a maximal element in an AL. An element A belongs to L is said to be maximal if A less than or equal to X implies A is equal to X. And these are the set of conditions that an element to become a maximal means M join X is equal to M for all X and M meet X is equal to X for all X. Then we say that M is maximal. So let L be a non-empty set defined for any xy belongs to L. X join Y is equal to X, which is equal to Y meet X. Then clearly L is an AL, and this is called a discrete AL, and this is very important example in the theory of ALs. Next one, the pseudo complementation. In this section, we introduce the concept of pseudo complementation on almost AL with 0 and prove some basic properties of an AL with pseudo complementation and prove that an AL with pseudo complementation is equationally definable. So this is the definition. Let L be an AL with 0, then a unary operation A going to A star on L is called a pseudo complementation. If for any AB belongs to L, it satisfies these three conditions. A meet B is equal to 0 implies A star meet B is equal to B, and A meet A star is equal to 0. A join B whole star is equal to A star meet B star. So a unary operation satisfies these three conditions. Such operation is called a pseudo complementation on L. We first observe that these three conditions are independent. You know, independent means one fails, the other two conditions are satisfied. So similarly, the other remaining conditions. First, we give an example of an AL which satisfies P1 and P2 but does not satisfy P3. For this, let X be a discrete AL. Already I gave a definition with 0 and with at least two elements, say 1 and 2 other than 0. Then X cube join meet 0 is an AL with 0 where join and meet are defined coordinate wise. Now for any X belongs to X cube, we write mod X for the number of non-zero entries in X. Define star on X cube as follows. For any X belongs to X cube, define X star is equal to X1 star, X2 star, X3 star, where for I is equal to 1, 2, 3, where xi star is equal to 0 if xi is not equal to 0, and 1 if xi is equal to 0 and mod x is equal to 1, and 2 if xi is equal to 0 and mod x is greater than 1, and 0 star is equal to 2, 2, 2. Then 0 star is equal to, and 0 star is equal to 2. Then x cube join meet 0 is an AL with 0, 0, 0 as a 0 element, which satisfies P1 and P2 but fails to satisfy P3. For if you take A is equal to 1, 0, 0 and B is equal to 0, 1, 0, then A star is equal to 0, 1, 1 and B star is equal to 1, 0, 1. And A join B is equal to 1, 1, 0. So that A join B whole star is equal to 0, 0, 2. And A star meet B star is equal to 0, 0, 1. Therefore, A join B whole star is not equal to A star meet B star. That means it fails to third condition. So this is one example. And the next one is an example of which satisfies P2 and P3 but does not satisfy P1. So for this, let L be an AL with at least two elements. Define A star is equal to 0 for all A belongs to L. Then L satisfies P2 and P3 but fails to satisfy P1. For if you choose a non-zero element, then 0 meet B is equal to 0, but 0 star meet B is equal to 0 meet B, which is equal to 0, which is not equal to B. So that means it fails to P1. So the next example is an example satisfying P1 and P3 but not P2. For this, let L be a bounded lattice with bounds 0 not equal to 1. Then for any A belongs to L, define A star is equal to 1 for all A belongs to L. Then L satisfies P1 and P3 but fails to satisfy P2. For you take 1 belongs to L and 1 meet 1 star. which is equal to 1 meet 1, which is equal to 1, which is not equal to 0. So therefore, these three conditions are independent. And such operation star is called a pseudo complementation on an AL. So these are certain examples of a pseudo complemented ALs which are not lattices. So this is one example of an AL which is not a lattice. So like this define x star is equal to 0. If x is not equal to 0 and 0 star is equal to b, then this is an AL with 0 and x going to x star is a pseudo complementation on L. Note that this is not a lattice. This is one example. In the case of distributive lattice with 0, it is well known that the element A star satisfying the properties P1 and P2 is unique if it exists, and that P3 is a consequence of P1 and P2, and hence there can be at most one pseudo complementation. So in case of distributive lattice, if the pseudo complementation exists, then it is at most one pseudo complementation. However, in an AL with 0, there can be several pseudo complementations. For consider this example. Already you know discrete AL definition. Let L be a discrete AL with 0. Then for any x not equal to 0 in L, in X, define for any A belongs to X, A star is equal to 0 if A is not equal to 0 and X if A is equal to 0. Then star is a pseudo complementation on X. Here, with each x not equal to 0 in X, we obtain a pseudo complementation. So this is an example of a pseudo. It have more than one pseudo complementation. So more generally, this is a more general example. Let A be a non-empty set with at least two elements, and let B be any set. Choose P comma P naught belongs to A power B. A power B means all mappings from B to A, such that P of T is not equal to P naught T for all T belongs to B. Define for any AB belongs to A power B and T belongs to B. A join B of T is equal to A of T if AT is not equal to P naught T, and B of T if A of T is equal to P naught T. And A meet B of T is equal to B of T if AT is not equal to P naught T, and P naught T if AT is equal to P naught T. And A power P of T is equal to P naught T if A of T is not equal to P naught T, and Pt if A of T is equal to P naught. Then this A power B join meet P naught is an AL in which A going to A power P is a pseudo complementation. So this is the more general example of an AL with more than one pseudo complementation. In the following, we observe some basic properties of the pseudo complementation star on an AL. So let L be an AL with 0 and star, a pseudo complementation on L. Then for any AB belongs to L, we have the following. 0 star is a maximal element. If A is maximal, then A star is 0, and 0 double star is 0. A star meet A is equal to 0. A double star meet A is equal to A, and A star is equal to A triple star. And A star is equal to 0 if and only A double star is maximal, and A star is less than or equal to 0 star. A star meet B star is equal to B star meet A star, and A join B whole star, which is same as B join A whole star, and A less than or equal to B implies B star is less than or equal to A star. It is actually in Boolean algebra, we know that A less than or equal to B implies B complement is less than or equal to A complement is there, and vice versa, because double complement is there. A double complement is A itself. So here A less than or equal to B implies B star is less than or equal to A star, and A star is less than or equal to A meet B whole star, and B star is less than or equal to A meet B whole star. And A join B whole star is less than or equal to A star, and A join B whole star is less than or equal to B star. A star is less than or equal to B star if and only if B double star is less than or equal to A double star. And A is equal to 0 if and only if A double star is equal to 0. So these are some important tools to prove the next results, that is star is equationally definable. Let L be an AL with 0 and star a pseudo complementation on L. then for any AB belongs to L, the following are equivalent. A meet B is equal to 0, A double star meet B is equal to 0, A double star meet B double star is equal to 0, A meet B double star is equal to 0. And also A meet B whole double star is equal to A double star meet B double star, and A meet B whole star is equal to B meet A whole star. First we observe that if L is an AL with 0, does not satisfy the distributive law, X join Y meet Z is equal to X meet Z join Y meet Z for all X, Y, Z in L, then star is a Euler operational which satisfies the following conditions. A meet A star is equal to 0, A double star join A is equal to A double star, A join B whole star is equal to A star meet B star, and A meet B whole double star is equal to A double star meet B double star, and 0 star meet A is equal to A. Does not imply star is a pseudo complementational L. For consider this example, so you take L is equal to 0 ABCD and define binary operation join and meet like this. Then and also define a star on L by 0 star is equal to D and D star is equal to 0 and A star is equal to B star is equal to C star is equal to 0. Then star satisfies the conditions 1 to 5 above, but star is not a pseudo complementational L. Since A meet B is equal to 0, but A star meet B is not equal to B. However, if an L satisfies the distributive law, X join Y meet Z is equal to X meet Z join Y meet Z for all XY, then we prove that the pseudo complement star and L is equationally defined. So this is actually the theorem that L be an AL with 0 which satisfies this distributive law, then a Euler operation star and L, A going to A star and L is a pseudo complementation if and only if it satisfies these following 5 conditions. So this is one set of conditions in which star is equationally definable, and we gave another set of conditions in which star is equationally definable. Let L be an L with 0, then a Euler operation star A going to A star and L is a pseudo complementational L if and only if it satisfies the following conditions. A star meet B is equal to A meet B whole star meet B, and 0 star meet A is equal to A, and 0 double star is equal to 0, and A join B whole star is equal to A star meet B star. So this theorem and this previous theorem gives a set of conditions that the pseudo complementation star on an AL is equationally definable, and hence we can treat these class of pseudo complemented ALs, they form a variety. So the next section, this set of all star elements, that means L star is equal to all A stars is that A belongs to L is a Boolean algebra. In section 3, it is remarked that an AL with 0 can have more than one pseudo complementation. Already examples were given. So in this section, we prove that if L is an AL with pseudo complementation star, then each maximal element of M in L, we obtain a pseudo complementation star M. In fact, we prove that this correspondence between the set of all maximal elements in L and set of all pseudo complementation star on L is 1-to-1. So the use of this theorem is to find the number of maximal elements and the number of pseudo complementations. So and prove that the Boolean algebra L star is independent up to pseudo complementation star. So this is actually the theorem that L be an AL with 0 and star be a pseudo complementation on L. For any A star B star belongs to L star, define A star is less than or equal to B star if and only A star meet B star is equal to A star. Then L star comma less than or equal to is a Boolean algebra in which A double star meet B double star whole star is the least upper bound of A star, least upper bound, and A star meet B star is the greatest lower bound of the elements A star and B star in L. So this is one important theorem, very important, not one, it's a very important theorem to define. We will next we'll plan to define a stone lattice. So for this, for that, this is very, very useful. So this is the corollary. Let L be a pseudo complementation L with pseudo complementation star. Then the map L going to L star defined by f of A is equal to A double star is an epimorphism. And next we shall prove that if L is an AL with pseudo complementation star, then a one-to-one correspondence between set of all maximal elements in L and the set of all pseudo complementation on L. For this, first we need the following lemma. Already we have observed that an AL can have more than one pseudo complementation, and already examples were given to this effect. So let L be an AL with 0 and star and perpendicular be two pseudo complementations on L. Then for any AB belongs to L, we have the following. A star meet A perpendicular is equal to A perpendicular, and A star join A perpendicular is equal to A star. A star perpendicular is equal to A double perpendicular, and A star is equal to B star if and only if A perpendicular is equal to B perpendicular. A star is equal to 0 if and only if A perpendicular is equal to 0 if and only if A meet B is equal to 0 implies B is equal to 0. And fifth condition, A perpendicular is equal to A star meets 0 perpendicular. So using this lemma, we have proved that a one-to-one correspondence between set of all maximal elements and set of all pseudo complementations. So this is actually the theorem. Let L be an AL with 0 and star be a pseudo complementation on L, and let M be the set of all maximal elements in L, and let PCL means the set of all pseudo complementation. Already we know that an AL can have more than one pseudo complementation. So PCL means the set of all pseudo complementations on L. For any small m belongs to capital M, define star m from L to L by A power star m is equal to A star meet m. A power star m is equal to A star meet m for all A belongs to L. Then the unary operation m going to star m is a bisection of m onto PCL. Because to each maximal element m, you define a unary operation. Because we need a pseudo complementation, that means we need a unary operation, star m. So a star m from L to L by A power star m is equal to A star meet m for all A belongs to L. Then m going to star m is a bisection from m on to PCL. So this is a, a very, very useful theorem to find the number of maximal elements. Finally, we prove that the Boolean algebra L star, already we have proved that if star is a pseudo complementation, then L star is a Boolean algebra. But already we know that if star and perpendicular are two pseudo complementations, corresponding to star we get one Boolean algebra L star, and corresponding to perpendicular we get L perpendicular is another Boolean algebra. But these two are unique up to isomorphism. So that is actually the last theorem in our lecture. Let L be an AL with 0 and star and perpendicular be two pseudo complementations on L. Then the Boolean algebras L star and the L perpendicular are isomorphic. So this is the last theorem in our lecture. So using this.
Hello, Vali. Please, time.
Sir, anyhow, he told last theorem, na sir.
Okay.
That he told this is the last theorem.
Last theorem. So using this this lemma, so next we improve research to define a stone lattice. For that, this lemma is very, very useful. So anyhow, this is the last theorem. So these two Boolean algebras are independent. So these are some of the references that we are used in our paper. So work of Liebfrink, Rabenboim, Venkatraman, and Blythe, TP Speed, Cornish. So thank you.
If anybody is having queries, please, from the audience side. I think nobody is having queries. A nice presentation, a valuable and informative lecture. Definitely, this is very helpful to the young researchers who wish to pursue their research in lattice theory, in particular pseudo-complemented almost lattices. Thank you very much, Professor Nanaji Rao.
Thank you, Professor Wali, for to share a session to my talk.
Thank you, Dr. G. Nanaji Rao, for.
Thank you, Masher. Thank you very much.
And thank you, Professor Wali, for chairing this session.
Thank you very much, sir. Thank you for giving me
Very
this
nice,
opportunity, sir.
Very nice. Thank you very much.
Thank you.
Thank you,
Thank you
one
very
and all.
much.
Thank you.
Thanks a lot, sir.
Now I request Dr. P. Anuradha Kameswari Madam to deliver his lecture on analogous to some arithmetical functions in ZPX. Now I request Professor P.P. Murthy to chair the session. Sorry, sir. Now I request Professor K.K.M. Sharma, sir, Department of Mathematics, Andhra University, to chair this session. Now it is over to you, sir. Over to Professor K.K.M. Sharma, sir.
Good afternoon. I take this as a privilege to introduce Dr. P. Anuradha Kameswari, Associate Professor, Department of Mathematics, Andhra University. Dr. Anuradha Kameswari did her MSc, MPhil, and PhD from University of Hyderabad. Her research interests are algebraic number theory, and cryptography. Dr. Anuradha Kameswari has work experience of 18 years in teaching and administrative experience 6 years as assistant principal at Department of Mathematics, LB College, and Warden, Andhra University Ladies Hostel for 2 consecutive years. She taught almost all subjects from for MSc program. She completed one major research project during the period 2015-18. She has 35 publications, both national and international, which are Elsevier, Scopus, Web of Science with impact factors. She attended 15 conferences, seminars, workshops, and 3 more in talks presented. And in workshops, she attended as a resource person for 13 workshops. And Madam Anuradha Kameswari delivered 9 invited lectures. She authored 1 book, which is published by Book Publishers International with ISBN number. Also, she wrote study material to PG students of Andhra University School of Distance Education. She guided 9 PhDs and 2 PhD students are in progress. She guided 5 MPhils, and then she is editorial member board for the journal Pure and Applied Mathematics, and she is a reviewer of ASEAN Research Journal of Mathematics and International Journal of Computers and Technology. She is has professional memberships also. She is life member in Andhra Pradesh Society for Mathematical Sciences, life member for Cryptography Research Society of India, life member of Professor S. Meenakshi Sundaram Memorial Society, life member of Indian Mathematical Society, member of International Association of Cryptography Research. Now I request Dr. Anuradha Kameswari to deliver her lecture. Thank you. Over to Madam Anuradha Kameswari.
Sir, am I audible, sir?
Yes, madam.
Is my screen shared?
Please share the screen, madam. Yes, yes, madam. Your screen is share. Coming.
Thank you very much, sir, for elaborate introduction of my myself. I am very happy to share this platform where all these stalwarts of research area nonlinear functional analysis delivered their lectures. I thank Professor Ravindranath Babu Garu for giving me this opportunity. I work in the area of number theory and cryptography, not very much related to nonlinear functional analysis. Little related, as the modular theory may be considered as something some way non-linear. In this present talk, I introduce to some fundamental developments for a possible research in some generalization of the Riemann zeta function with polynomials. So, with that purpose, I am presenting this talk. The motivation of for this is in the construction of cryptosystems with polynomials in ZNX, where this is a modular ring for n greater than an integer greater than 0. The quotient ring of the polynomial ring in ZNX with an ideal generated by a polynomial fx, where fx is a polynomial. In this, basically in this residue ring, the group of units is mostly considered for the message space in the construction of cryptosystems. In this context, all the computations, there is a need to compute the order of the unit group. If n is equal to p, this computation is simple. When n is equal to a prime number, this computation is simple, and fx is an irreducible polynomial. This quotient is immediately becomes a field, and the group of units is one number less, and which will be nothing but n power k minus 1. So computation of the group order in residue is simple when n is a prime number, and fx is a irreducible. Now in the joint work with my student, the units in the
Excuse me, madam. Madam? Madam, excuse me, madam. Anuradha Kameswari, madam. Madam, మీ phone లో మీ రెండిట్లో జాయిన్ అయ్యారు మేడం. రీసౌండ్ వస్తుంది, ప్లీజ్.
ఇప్పుడమ్మా?
It's okay, madam. Thank you, madam.
Okay, thank you. So, in a joint work with my student, we worked on counting these units in this particular ring when fx is not necessarily reducible. Okay, and what we notice when n is not a prime number and fx is not irreducible, counting units in this particular residue ring is not so simple. So we need to find out the possibilities of counting these units. So in the same joint work, it is proved that an analog denoted as p and fx to the arithmetical function Euler-Tauschent, we can count the units in the residue ring when n is a prime number and fx is not necessarily necessarily irreducible. So the notion that is used as an analog to this Euler function may be used in this count is what is identified in this work. The formula for since n is prime, we denote it as ppfx, the analog, which is going to be an analog for your Euler function. The formula for ppfx is obtained by first developing an analog mu p to the arithmetical function, Mobius function mu. So in this talk, the study is extended to not only the developing the analogs to arithmetical functions like Mobius function and Euler function. I also extended the study to Revelance function and divisor function in ZPX for a prime P, and some related properties are also discussed. This study is useful from the perspective of developing a generalization to Riemann zeta function with polynomials. So the analog is to establish the analog, the base structure that is used is this. Let P be a prime number, then we define the set of all one primitive polynomials in ZP over ZP denoted as P1 ZPX, given as set of all polynomials Fx, where Fx is this, with all its coefficients are coming from ZP, and the GCD of all the non-zero coefficients is actually 1. The GCD in ZP will be a unit, but we don't unit, it may vary. The point here is in ZP you may have the over ZP the content may be a unit which is varying. Now the condition we are taking here is it must be exactly equal to 1, not a unit. So that is the set of all one primitive polynomials set is considered for all these analogs. So a real valued function mu p on P1 ZPX is defined as follows. Mu p fx is 1 if the degree of this polynomial is 0. If degree of fx is greater than 0 and f is a product of irreducible polynomials, then mu p of fx is defined to be equal to -1 to the power of k, where k is the number of the irreducible factors and all the powers are equal to 1. And it is defined to be 0 otherwise. If you have a square factor, then it is defined to be equal to 0. This is exactly the Mobius function on the set of all positive integers. So it is a generalization to this. Now this satisfies this the defined analog Mobius function has a summation equal to this, satisfies this particular property. The summation over all the factors of this polynomial is 1 whenever your degree of fx is 0, and the summation takes the value 0 if the degree of fx is greater than 0. And in the proof, you can see that if degree of fx is 0, then fx is a constant, and since we are taking up that it is a one primitive polynomial, the c must be equal to 1. So you have the result valid for degree of fx equal to 0, it takes up the value 1. And now if degree greater than 0, now to prove this we need to set up the set D, which consists of all the summation is over all the divisors of fx. Now D is the set of all divisors of fx in ZPX. D is defined to be the disjoint union of two sets D1 and D2. The D1 consists of all divisors with no square irreducible factors, and D2 consists of square irreducible factors. So when we consider the summation over D, this can be identified as a summation over a disjoint union, summation over a D1 and D2. So over D2 it is going to be equal to 0, and over D1 this turns out to be this, and which can be considered to be equal to the factors are now D1 factors are this, which is the summation like this, which can be expressed as this way, and this turns out to be the 1 minus 1 raised to r and 0. So you have this equal to 0 if your degree of fx is greater than 0. So that's one property established for Mobius function as regarding the summation, which will be used to develop a product formula for the Euler-Tauschenk analog. So, and this Mobius analog mu p also has a multiplicative property. That is, whenever the polynomials are co-prime, then mu p of the product will be the product of mu p ax and mu p bx. This follows right from the definition. From the very definition, this statement can be, this proof can be obtained. And we move on to the development of the analog for the Euler function. And the Euler function P on Pnx is defined as this way. It is equal to, this stands for the number of the polynomials gx in Zpx, where the degree of gx is less than degree of the polynomial fx here, and the polynomial fx and gx are co-prime. With the number of such gx, your Pbx is defined to be equal to this number when the degree of fx is greater than 0. And if degree of fx is equal to 0, this number is defined to be equal to 1. So this is the function that is going to be analog to your Euler quotient over integers, over numbers. So now this Euler quotient can be also represented by this summation like this, with the observation that any element gx in the residue ring, Zpx over fx, this residue ring can be considered as gx in Zpx with degree gx less than degree of fx. So now if we denote this set of all elements in this residue ring by Rf, the Euler function, what we have defined above, can be considered as counting these numbers with gx varying over this set, which is nothing but your Rn. So you are counting this whenever your gx and fx are open. Whatever you have defined here is same as this summation. So this as a representation for the Euler function you have defined there. So now, using that, we are trying to give another summation formula for this Euler function. So, if degree of fx is greater than or equal to 1, Pb of fx will be equal to this summation. So, this again uses the formulas we have established. So, if degree of fx is equal to x, you have gx with the property in your residue ring are going to be like this. It is gx in your Rf, and Rf has how many elements? There are p to the power of s elements, and we are trying to, you have already seen that Ppx has this expression, and this expression, and you are removing now this coprimality, and you are saying that this is same as this summation. You can observe this, and this is what you have proved in your first theorem using your Mobius function that is expressed here. And finally, the summation is considered with these three arguments. And finally, this is the summation formula for the Euler function. So we have already defined the Euler function, and we have seen two types of representations for the same. So we are trying to understand this Euler function more and more. And now we are going to give another product formula which will be quite useful in the count we are talking about. So this is the product formula for the Euler function. And here the product runs over all the irreducible factors of fx. So this is the formula to be established. And if degree of fx is equal to 0, you have fx equal to constant, and by definition Pc is equal to 1. And on the RHS here, this product is empty, which will be considered as 1, and you have p power 0, which is 1 again. So you have these things valid for degree equal to 0. You consider your degree of x greater than 0, and fx is such a irreducible product, then you are identifying what this product is. So this turns out to be your PPFX. Okay. So I leave out the discussion here for verification. So this gives us a product formula for Euler function, which is quite useful in the count of the units in the residue ring we are talking about. So this is what we are trying to say. So if this is the example where fx is irreducible, and this is the field. This is a field with 3 square elements, and this is irreducible polynomial. So this is the field with 3, and there are the units are basically 3 square minus 1, 8 invertible elements. So, and now you see this is what you have. That is, you are claiming that these are nothing but invertible units. Is what your claim is that your PPH gives the invertible elements, the units. So here this from this idea you are saying that PPX is 8, and you have given a product formula. Now you can verify by a product formula also you have the same value 8. So this is the advantage of this count, and this seems to be simple because your polynomial here is an irreducible polynomial. This is not so simple when your fx is not irreducible. So that's what that's the so this is what the group of order of units in this is 8 is what we are saying. So this number you are talking about when your polynomial is not irreducible, that is reducible. You have the polynomial written as this way, and then the number of here invertible elements in this field Zx quotiented by x square plus 8. The count is not so simple, but you can obtain it from this formula Ppfx, which is equal to 100. So this particular quotient residue ring has so many units in it. So this is about and this Euler function also has a multiplicative property, which also again now follows from the multiplicative property. You can product formula you can obtain this. Now we introduce another arithmetical analog, that is the divisor function dp on this. Let fx be a polynomial from here. Then for fx a product of with a decomposition like this, we define dpfx to be the number of divisors of fx. That is, dpfx is nothing but number of divisors gx overall 1. It is dx, not a gx. Overall 1. So this the first thing we are trying to prove here is this is the divisor. It should not be gx. This is divisor dx. Okay. The multiplicative property of divisor function dp on this is this. This divisor function also has a multiplicative property, which is not quite clear from the definition. This needs to be proved, and the proof is given here, and this is what it is. Why? So the divisors are like this, and these are the multiplicative property, that is ax and bx considered are co-prime. This is what you have considered. These are considered as co-prime. Then each divisor can be expressed as tx into rx, where now tx is a divisor of ax and rx is a divisor of bx. They are disjoint. The divisors set is disjoint. So this can be separated as a product of sums like this. And finally, we have this multiplicative property for divisor analog. This divisor function analog. And because of this we have dp fx given by this particular product formula whenever your fx is a irreducible decomposition like this. So that's the next proof we are carrying. If dpfx is equal to this, because of the multiplicative property you have, it is dp this product, And incidentally, we need to find out the formula for dp g power a, gx to the power of a. And you know, the divisors for this are 1, gx, gx square, gx are all the divisors. So that implies this has so many divisors, a plus 1. Therefore, by multiplicative property of dp, since each of them have so many divisors, this substituting in the product, the dp of fx is just this product. So this is what fx is equal to when you take this polynomial. This is an irreducible polynomial. The divisors are just 2. It's an irreducible polynomial and it is verified by your formula. And when the polynomial is reducible, it has 4 irreducible, 4 divisors. The number of factors for this particular polynomial is this. Also, it can be verified, and since it's a small polynomial, you can verify the number, which is equal to 4. And now we have another arithmetical function analog, that is Lively's function. Lively's function lambda p. Now this is again defined on this same ring, same set of primitive polynomials, and we define it to be equal to 1 if the degree of fx equal to 0. It goes hand in hand with the Mobius function mu p. And in fact, the study of this function helps to understand more about the Mobius function up. And if degree of fx is greater than 0, for f being the irreducible decomposition like this, then lambda p fx can be defined as -1 raised to a1 a2, a1 plus a2 plus a3 plus ak. And by the very definition, you can understand that this lambda function is multiplicative as well, and it has little more freedom by the means that it is completely multiplicative. Completely multiplicative, like you don't need the condition of AB being the coprime, that is you have dp of AB ax bx is dp ax into dp bx. This is the analog for the lambda p, and these are the analogs that are developed, and their further properties can be some more properties like a product on these. We can define certain product on these analogs, extend the decay product of arithmetical functions on these analog, and even study about the group structure of all the multiplicative mathematical functions. All such theories can be extended and give a scope for moving to generalizing the Riemann zeta function as well. The formula for PPA counts the units in the with another foremost interest for us is it counts this particular formula PPA counts the units in the residue ring. It gets the order of the multiplicative group. The group plays a vital role in our cryptosystem construction for fx primitive polynomial and not necessarily in ZPX. Such things are also used in the NTRU cryptosystem constructions, where you can replace the x power n minus 1 polynomial by a reducible polynomial. First irreducible, and then you can even reduce by reducible polynomial, primitive polynomial. Then you can generalize such cryptosystems. The product formula the product formula for PPFX is obtained applying the Mobius function mu p. So we needed the generalization to obtain this PPFX. We needed the generalization of Mobius and then generalization of Euler function. The product formula is developed for and the PPFX and DPFX are applied in cryptography with polynomials in the residue ring. And extending this study of developing analogs to other arithmetical functions and the related properties are useful in understanding a generalized Riemann zeta function with polynomials in ZPX. So this is what I have, and these are the references. Thank you, sir. Thank you for giving me this opportunity.
Thank you, madam, for your inspirational talk on analogous to some arithmetical functions in ZPX. Congratulations. Thank you, madam. Thank you for sparing your valuable time to present an invited talk on the next conference on recent advances in functional nonlinear functional. Thank you once again.
Thank you, sir. Thank you.
Hello, sir. Hello, sir. Hello. Hello. Hello, sir.
Good
Hello,
afternoon, all.
sir.
Thank you, sir. Professor KKM Sharma garu to chair the session, and thank you, madam. Commissioner garu delivered the talk. Now, I
Sir.
request the participants to present the paper presentations. There are two parallel sessions. One is from actual time is 3:45 to 5:30, which is shared by Professor C.S. Srinivasarao garu, and another session 5:30 to 7 p.m. Already that is preponed to 4 p.m. That is chaired by Dr. M.A.R. Kameswari. Those who are in the presentation from 5:30 to 7 p.m. are requested to join in Google Meet link, and the rest of the candidates 3:45 to 5:30 are continue in WebEx link only. Now, I request Professor C.S. Srinivasarao garu to chair this session, and simultaneously I request Professor Dr. M.A.R. Kameswar garu chair the session in Google Meet link.
Excuse me, sir. Excuse me, sir. Excuse me, sir.
Yes?
Please,
Yes, sir.
the IPNU, I am Saudi Hassan, among the participants in the conference. I received the acceptance notice, but unfortunately, my name is not in the table. I will write my information again. Please add me to the table and join yours on Sunday, sir. Please accept this request with the utmost respect and appreciation. Thank you, sir.
Thank you, Hari Krishnan garu. Now, may I request?
Sir, you can present the paper. Actually, what is which session you are, sir? Hassan, sir?
Hassan. Hello? Hello? Sir, Hassan, sir? Are you there to present your paper, sir? Please respond, sir. Please respond.
Yes, sir.
So what are you, sir? Hello.
Yes. Yes, sir.
Please message, sir. We will.
Please put a message.
Please put a message in group, WhatsApp, any one group.
Can I start the?
Sir, Srinivasarao, sir, please start the session.
Thank you, Hari Krishnan garu. Now I request the first candidate, Amir H. Dar. Please present your paper. Sir, are you there? Amir H. Dargar, are you there? Hello.
I am here, sir.
Okay. Are you ready to give your paper presentation?
Yes, sir.
Sir, kindly note the point. Your time is only 5 minutes. Due to time constraints, kindly
yes, sir.
Focus on the main results and examples, if any.
Yes, sir.
Thank you. Okay.
Thank you.
Start your paper presentation, sir. Time starts now. Please start the presentation. Your screen is visible. Please start the presentation. Hassan sir, your screen is visible. Please start the presentation now.
Yes, sir. Existence and uniqueness. Yes, sir. It's clear, sir. Sir. Existence and uniqueness.
Do you have any problem, sir?
Yes, sir.
What is your problem? Your screen is sharing. Your screen is visible.
Yes, sir. It's clear, sir.
As clear, clear.
Yes, thank you, sir.
Okay, right.
And the third chapter entitled Generalized Stability, and the last chapter entitled some reference for this work. In this work, we consider a one-dimensional photoelastic system with a delay theorem and nonlinear damping theorem. First, we show that the existence and uniqueness of the solution by the semi-group technique, more precisely by Euclidean theorem. Also, we prove the general stability estimates using some preparates of convex function and Lapenoff functionals. The second chapter entitled Basic Concepts gives some necessary preliminary notion, some definitions, theorem, and result to approach the other chapters. In the third chapter, study the existence and uniqueness of this system, solution 1. The last chapter entitled General Stability of this photoelastic system with a delay theorem and nonlinear damping theorem. In this chapter, we recall some definitions concerning symbol of space and certain results of inequalities in the sum space. We will first of all give a reminder of some definitions concerning Sobolev space. We start with the Dubek space is given by the following relations. And the Sobolev space is given by the following relations. And now we give inequality, Young's inequality, given by the following relations. The inequality is written in the following form. Theorem of Euclid. A linear operator A is the infinitesimal generator of semi groups if and only if A is closed operator and domain of A is dense on X. On X, it's is given the following relations. We suppose that for this work, we suppose that alpha and f satisfy the following hypotheses, H1 and H2, existence and uniqueness. In this section, we give existence and uniqueness results for the system 1 using the theory of semi-group. We consider the following problems. We introduce the following new variables. It's easy to verify that Z satisfy the following relations. Therefore, the system 1 is equivalent to the following systems. So if we denote A given by where derivates E for T equal V and T equal C, then system 1 can be rewritten as follows, where A is the linear operator defined by and JA is given by. We consider the following space, and H is the energy space given by. A qubit with inner product is given by the following relations. The domain of I is given by. Clearly, domain of A is dense in H. Now we can give the following existence result. Now we prove that I is a monotone maximal operator. And the inner product between A, E, less than the following relations are as a result is monotone. The second conditions, next we prove that the operator identity plus A is surjective for any K belong to H. We prove that there exists a unique A belong domain of A such that. So according to Lamar-Phillips lemma, we obtain the existence and uniqueness of the solution of the system 1. Generalized stability. The purpose of this section is to establish the result of the general stability concerning the system 1. The energy functions associated with the system 1 is given by idea of the proof multiplying 1 and 1 2 by additivity respectively. Second idea integrating over 0 1. We use the fact that using integration by parts and the boundary conditions, we write the result of net in the form. Let E be a solution of 1, then the functional is given by satisfy the following inequality. And F2 is given by and satisfies the following inequality. And F3 satisfy the following inequality. And F4 satisfy the following inequality. Now we define the Lapenoff functional given by where n and ny, n12 and 13 and 1 are positive constants. Let it be a solution of 1 then there exists two positive constants such that the Lapenoff functional for satisfy the following inequality, and the second inequality is given by 6. Theorem. Suppose is H1 and H2 old, then there exists positive constant such that the solution of 1 satisfies the following inequality. Idea of the proof multiplying 6 by alpha t using the fact that end up being the Young's general inequality. And now we present some reference for this work. And finally,
sir, please, only 1 minute
thank
time
you.
is there. Hello.
Finally,
Assistant,
thank you.
Only 1 minute time is there. Only 1 minute. Hello.
Yes, sir. Hello, sir.
Try to finish within 5 minutes, sir. Already time is over. 4 minutes, 30 seconds over. Only.
Excuse me.
Okay.
Excuse me, sir. Excuse me, sir. Yes, sir.
Okay, sir. Okay. Thank
Yes,
you, sir.
sir.
Thank you. Thank you for your.
Thank you very much, sir. But my name is Saudi Hassan. I am a participant of this conference, but my name is not exist of the table, sir, for the attestation participation, sir. Are you send the my information for email, sir? I am sent the my information of the mail conference, sir.
Thank you, sir. Time is over. Time is over. Thank you. Thanks for your
Thank you
presentation.
Thank you very much, sir. The attestation of participation, sir, is.
Okay, sir. Okay. Thank you, sir. Thank you for your presentation. Already time is over.
Yes, sir. Thank you very much.
Okay, right. Next participant, I request B. Nageswar Rao. Nageswar, are you there?
Yes, sir. Yes, sir.
Okay. So, Nageswar Rao, please note the point.
Sir.
Time is only 5 minutes. Due to
Sir.
time constraints, you should focus on main results and important conditions and examples if you have any.
Yes, sir. Yes, sir.
Okay. Time constraint. Time starts now.
Okay, sir. Okay. Thank you, sir. Good evening, sir. Okay. Sir, my screen is visible, sir.
Yeah, visible. Your screen
Sir,
is
good
visible.
evening, sir. Good evening, respected professors. Sir, good evening, sir. Good evening, sir. Good evening, respected professors. Sir, good evening, sir. 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 Good I would like to introduce myself to you. This is Dr. B. Nageswar Rao, working as Associate Professor in Mathematics, Department of Science and Humanities in Lendi Institute of Engineering and Technology, Vizianagaram District, Andhra Pradesh, India. Today, title of my paper is Translate Operators on Wave Groups. Abstract. Here, in this paper, we are introduced translate operators on vague sets. Here, these translate operators on vague sets and vague groups, vague normal groups, etc. Here, these three important keywords are there. In this translate operators, vague increasing translate operator and vague decreasing translator operators. Translator operators also are the three keywords. Introduction about my research. Here, basically, indexed set. Indexed set, everybody knows, IA of x or characteristic function chi of x is equal to 1 if x belongs to A, 0 x doesn't belongs to A. If by observing this definition, indexed set or characteristic function, it will be gives only two values, 0 and 1. It is not given complete information between 0 and 1. This defect is identified in 1965 by the famous mathematician Jade Wheel, and one of the reasons for introduce fuzzy set. According to the famous mathematician Jade Wheel, the fuzzy set is a mapping mu A from x to closed interval 0, 1. Here elements of fuzzy sets are degrees of membership function. By using fuzzy sets, a lot of applications are available. Applications of fuzzy sets, for example, fuzzy sets are used in cloud computing, data science, artificial intelligence, engineering graphics, robotics, etc. in computer science engineering. Also, fuzzy sets are used to signals and systems, image processing in communication engineering department. Also, these fuzzy sets are used to electrical circuits and circuit analysis in electrical and electronics engineering. Also, fuzzy sets used in thermodynamics and mechanical engineering. Also used in construction field for civil engineering. So that's why I'm here, which is the very important fuzzy sets compared to abstract algebra. Fuzzy set is very essential and useful for all the real life applications also. Everybody knows in every home using washing machine, that is the entire washing machine run by fuzzy sets only. Because of suppose membership mu of x is equal to 1, it can off on mu of x is equal to 0, that membership, that washing machine off. Between 0 and 1, the entire washing machine can be run by membership function. That is nothing but fuzzy set. This is the basic applications of fuzzy sets. And now coming to the vague set. Vague set is a pair TIFA, both TIFA are also fuzzy sets, which satisfy the condition 0 less than or equals to TAX plus FAX less than or equal to 1 for all x in x. This inequality is very important. Here, vague set is a pair TIFA, both TA and FA are fuzzy sets, which must and should satisfy this condition, then only the pair is vague set. Even particularly, TA is called membership function or truthcity function. FA is called non-membership function or falsity function. So, vague set is generalization of fuzzy set. How to write? The pair TA, FA, TA is nothing but 1 minus FA, FA. Also, TA, 1 minus TA. So, the pair vague set TA is equal to TA, FA is generalization of fuzzy set. Next one is applications of fuzzy vague set. Basically, vague set is generalization of fuzzy set. According to Gau and Buhir, actually vague set introduced Gau and Buhir. According to Gau and Buhir,
Sir Nageswara garu, please go to the main results.
Sir. Here, in my research paper, I would like to introduce these translate operators and apply these introduce translate operators and apply these operators on vague sets. So here T alpha plus A is called vague increasing translate operator. T alpha plus A nothing but TA T alpha plus F, FA T alpha plus X. Where TA T alpha plus X is equal to minimum of TAX plus alpha comma 1, FA T alpha plus X is equal to maximum of FAX minus alpha comma 0. Here T alpha plus A is nothing but vague increasing translate operators, and T alpha minus A nothing but vague decreasing translate operators. These operators, why I am applying translate operators? Actually, vague set is very useful. According to Gau and Buhir, TA represents profit function, FA represents loss function. By using Gauguin-Bouguer, the view of Gauguin-Bouguer, if loss can decrease, profit automatically increases. That is the basic application of wake set. But why I am applying translate operators on wake set? These operators apply on wake sets, which is more accuracy. Compared to wake set, translate operators on wake set is more accuracy. So here, that's why I'm applying translate operators on wake sets, wake groups, etc. This is the first result. T alpha plus A, T alpha minus A are wake translate operators on wake sets of X, where if A is wake set of X, then translate operators also wake set of X.
Garu,
Sir, sir.
your paper presentation, already time is over.
Sir, sir, small example. 1 minute, sir, 1 minute. This is a example of translate operator. After applying translate operators, the wake set also translate operators. This can be represented by a increasing translate operator. This is a decreasing translate operators. So this is another example. This is a very important property like result. Here, wake increasing translator operator at alpha particularly is equal to 0, nothing but wake decreasing translator operator. Both are equal to wake set. Here, wake increasing translator operator, particularly alpha is equal to 1 gives 1 complement. This is wake value, unit wake value. And wake decreasing translator operators at alpha is equal to 1 gives 0 wake value. Next, this is in basic set theory also extended after applying translate operators on wake set. For any wake set A of X, alpha in 0, 1, here increasing translate operator on complement of wake set gives decreasing translate operator whole complement. Similarly, wake decreasing translate operators on complement of wake set gives wake increasing translate operators whole complement. Next one, this is the very, very important result in my paper. In general, for any alpha in 0, 1, then the translate operators do not commute each other. But in my research, I identified this condition that X be a non-empty. The above example gives the strengthness of this failing property, do not commute each other. But in our research, identify this condition that X be a non-empty set and A be a wake set of X. Then after consider the condition alpha like 1 minus minimum of 1 minus P comma Q, where P is equal like this.
Next
Then
participant is B.
the above result is happening. Okay, sir. Okay.
Thank you, sir.
Thank you very much, sir, for giving this opportunity.
The next participant is Vishala, madam. Madam, please share your screen.
Yes, sir.
Okay. The title is, the time 5 minutes, madam. Your title is Radiation Absorption and Aligned Magnetic Field Effects on MH Fluid Fast Inclined Various Plate in. Okay, madam.
5 minutes.
So good evening, everyone. I am Dr. Vishali, working as Assistant Professor in the Department of Basic Sciences and Humanities from School of Engineering and Technology, Sri Padmavati Mahila Vishwavidyalaya. Today, I am presenting you radiation absorption and aligned magnetic field effects on MHD dissipative fluid past an inclined vertical porous plate in porous medium. So the abstract is, in the presence of the aligned magnetic field, chemical reaction and radiation absorption, the research centered on the analysis free convective flow of a viscous, incompressible and electrically conducting fluid via an inclined plate through a porous medium. The free stream velocity could obey exponentially increasing small disruption law. Analytically, two-term harmonic and non-harmonic functions overcome non-dimensional governing equations. Distributions of velocity, temperature, and concentration are explored by using the graphs for different parameter values entering into the problem. The skin friction coefficient, heat transfer rate, and mass transfer rate are derived. This research is very useful in the steel industry monitoring molten iron flow, nuclear plant liquid metal cooling, and in meteorology. Introduction. The introduction of this research paper is the phenomenon of free convection and mass movement flow of the conducting fluid past an inclined heat surface under the effect of a magnetic field has drawn attention in its application to geophysics, astrophysics, and many engineering problems such as cooling of nuclear reactors, aerodynamic boundary layer regulation, and cooling towers. Mass transfer is one of the commonly observed phenomena of both chemical and biological sciences. As the fluid is at rest, the mass transfer occurs. Mass is transmitted solely through molecular diffusion arising from gradients of concentration. Convective heat and mass transfer mechanism are identical in design with the limited concentration of group in fluid and higher mass transfer speeds. Already several studies have also been carried out of simultaneous heat and mass transfer, assuming different physical conditions. In specific, here chemical engineering methods, the chemical reaction between a foreign mass and the fluid in which the plate lies happens. These processes exist in various industrial applications, including polymer manufacturing, ceramics or glassware processing, and food processing. The physical and statistical formulation is as shown here. The governing equations for this investigation are focused on mass, linear momentum, energy, and concentration, species equilibrium. So the four equations are given here. The mass equation, linear equation, energy, and concentration equations are here. Next, the appropriate boundary conditions for the corresponding fields are, these are the boundary conditions. Next, the non-dimensional numbers are shown here. Using these non-dimensional numbers, the equations, that is, these equations transform to these forms, and the boundary conditions are also transformed to equation 10. The following are the solutions obtained by using the boundary conditions. The velocity equation, temperature, concentration distributions are shown here, and the skin friction, the surface non-dimensional skin friction is defined as tau is equal to dou u by dou y at y is equal to 0, and that is equal to dou u naught by dou y at y is equal to 0 plus EC, where that is the accurate number, dou u1 by dou y into at y is equal to 0, and that gives this equation. The Nusselt number and the Sherwood number are also represented here. Next, I'll discuss about the results. Here I've showed the velocity profiles. The velocity profile, this is figure 1, shows the velocity profile for different values of the inclined angle. The inclined angle impact on the velocity profile is clearly shown here. It is observed that the velocity reduces to the increasing values of alpha. And figure 2 demonstrates the effects of aligned magnetic field on velocity. The velocity declines as the aligned magnetic field parameter
Madam
increases.
Vishali garu, only 43 seconds are there.
Yes, sir. I'll finish it off.
Kindly finish as soon as possible.
Yes, sir. Figure 3 shows the magnetic field influence. The existence of transverse magnetic field renders the fluid flow resistive, and this force is called as Lorentz force, which slows down the fluid flow. Here, this shows the temperature profiles. The figure 4 shows the variation of velocity profile in the presence of permeability. This figure 4. Parameter K0, as the permeability parameter increases, velocity decreases. Next, figure 5 shows the temperature profiles. Figure 5 demonstrates the influence of heat.
Madam, sorry to say, time is over. Thank you very much for your presentation.
Okay, sir. And
the next participant is?
Okay, thank you, sir. These are the conclusions and references.
The next participant, Deepshika.
Yes, sir.
Are you there?
Yes, sir. Yes, sir.
Are you ready to give your presentation?
Yes, sir. Is my PPT visible, sir?
Yeah, visible, madam. Just please note some point. So time is only 5 minutes. Due to time constraints, you should focus on main result and examples if you any.
Okay, sir.
So within 5 minutes, you should try to finish your talk.
Okay, sir. Good evening, everyone. Myself, Deepshika.
Thank you, Vishal Madam garu.
Today, I'm going to present on the topic on some results of discrete frames of translates. So first, I would like to thank the organizer of this conference for giving me the opportunity to present here. So first, I'm going to start with the definition of frame. So a sequence of vectors in a Hilbert space H is called a frame if there exists positive constant A and B such that for any vector f in H, this inequality holds. So this concept was introduced by Duffin and Schaeffer in 1952. So here the constant A, it is called a lower frame bound, while the constant B is called an upper frame bound, and these frame bounds are not unique. There may exist infinitely many frame bounds. Now we have some operator associated with the frame F. So first is the pre-frame operator, which is also known as synthesis operator. It is from the space of all square summable sequences onto H. So it takes the sequence Cn onto this series. Next is the adjoint of the pre-frame operator, which is called the analysis operator. It is from H onto the space of all square summable sequences. It takes the vector vector F onto this sequence. Now the composition of these two operators, analysis and the synthesis operator, is called the frame operator, which is from H onto H. It is defined like this. This is a very important operator because this is linear, bounded, invertible, as well as self-adjoint. And the speciality of this operator is that it gives us the reconstruction formula. So we can express any element of the Hilbert space in the form of this series. So this is the series involving the frame elements. Now we have the definition of dual frames. So if Fk is a frame, then the frame Gk is called a dual frame if for any F in H, the F can be represented in this series. So we can see this Gk is a dual frame and Fk is a frame. So both Gk and Fk are frames here. And for every frame Fk, there exists at least one dual. As you can see in this slide here, this is the choice of one Gk. So this has one special name. It is called a canonical dual frame. So it is always possible to find out at least one dual for any frame. And the dual frames are not unique. There may exist infinitely many dual frame for a corresponding frame. Now, the concept of a discrete Gabor system was introduced by Pfaender in the unitary space Cn, where in the discrete Gabor system, the translation and modulation operator are used. And in this paper, we are going to study the frames which are generated by using the translation operator. So before this, we need some notations. So this is the element of unitary space Cn. And this is the translation operator, the translation by k. So tk of x will be this. And the discrete Fourier transform of an element x in Cn will be this. So the x cap m will be this element. Now we have the definition of discrete frames of translates. So Tk phi, where phi is an element of Cn, this is called a discrete frames of translates if there exists positive constant A0 and B0 satisfying this inequality. So here this phi is called a generator function because it is generating the entire family of translates. Now we want to see the condition. So we proved some condition under which any phi can be a discrete frames of translate. So this is the sufficient condition. So if phi belongs to Cn and if its Fourier transform satisfy this condition, that is this quantity is strictly positive, then Tk phi will be a discrete frames of translate. We have the bounds also. This A will be a lower frame bound and this n times norm of phi square will be the upper frame bound. So this is the necessary condition. If Tk phi is a discrete frames of translate, then its Fourier transform must satisfy this condition. Now this result says that the canonical dual of a discrete frames of translate is also a frame of translate. So you can see this is the canonical dual. So here the structure preserved under duals also. Now we characterize the generator function for discrete frames of translate in C2.
Deepika madam.
Yes, sir.
You have only 43 seconds time is there.
Okay, sir.
So kindly finish as early as possible.
Okay. So any phi in C2 will be a discrete frames of translate if the first component, the square of the first component not equals to the square of the second component. So this was the characterization for generator function in C2. So this is an open problem, or one can think about this problem. They can think about to characterize the generator function in Cn, where n is any natural number. So these are the references. Thank you.
Thank you, madam, for a good presentation.
Thank you, sir.
Now, I request the next participant, K. Ravi Babu Garu,
Yes,
Department
sir.
of Mathematics, Dr. V.S. Krishna Government Degree College. Are you there, sir?
Yes, sir. Yes, sir.
Sir.
Yes, sir.
Very good afternoon.
Oh, good evening, sir.
So you have only 5 minutes time, sir.
Okay, sir. Okay.
Due to time constraints, you should
My
focus on main result and examples, if any.
okay,
So
sir.
you should try to finish your presentation within 5 minutes, sir.
Okay, sir. Is my PPT visible, sir?
Yeah, visible.
Okay. Good evening, all of you. My name is Dr. K. Ravi Babu, lecturer in mathematics, Dr. V.S. Krishna, Government Degree College, Visakhapatnam. My presentation paper is Generalized Permitting Derivations on Almost Distributive Lattice. Here, in 1957, Professor Posner introduced the concept of derivations in rings and prime rings. Later on, several researchers developed the concept of derivations in BCA algebras and MV algebras. In 1975, Professor Saaz introduced the concept of derivation in lattices. In 1981, Professor U.M. Swamy and G.C. Rao introduced the more significant generalizations of Boolean algebra called almost distributed lattice, which is neither complemented nor distributive. In 2007, my Guru G.C. Rao and myself introduced the concepts of derivation, symmetric biderivation, permitting triderivations in almost distributive lattices. This is the definition of an almost distributed lattice. An algebra L join meet of type 2, 2 is called an almost distributed lattice if satisfies the following 5 axioms. In this paper, L stands for an ideal L join meet unless otherwise specified. Now, ideal with 0 and discrete ideal, just let us see definition of ideal with 0. An element 0 belongs to is called 0 element of L if 0 meet x is equal to 0 for all x belongs to L. And this is the definition of a discrete ideal. Now, the derivation of definition of a derivation on ideals. A function d from L to L is called a derivation on L if d of x meet y is equal to dx meet y join x meet dy for all x comma y belongs to L. For example, the identity map on L is a derivation on L. This is called the identity derivation on L. If L has 0, another definition, if L has 0, define a function d on L by dx is equal to 0 for all x belongs to L, then d is a derivation on L and it is called a zero derivation on L. This is another example of a derivation. If you define d from L to L by dx and fix an element a belongs to L, dA of x is equal to a meet x for all x belongs to L, then dA is a derivation on L. In a discrete radial, L is equal to 0 AB, if we define a function d on L by d0 is equal to 0, dA is equal to b, dB is equal to a, then d is not a derivation on L. Now coming to permitting triderivation, before going to that, we need two definitions. Permitting map. A map D from L cross L cross L to L is said to be a permitting map if D of xyz is equal to D of xzy is equal to D of yzx is equal to D of yxz is equal to D of zxy is equal to D of zyx for all x comma y comma z belongs to L. A mapping small d from L to L defined by dx is equal to capital D of xxx for all x belongs to L. It is called the trace of D. Now, permitting triderivation definition, a permitting map D from L cross L cross L cross L to L is called a permitting triderivation on L if D of x meet W comma Y comma Z is equal to W meet D of XYZ join X meet D of WYZ for all x comma Y comma Z comma W belongs to L. Observe that the permitting triderivation D on L also satisfies these two equations also. Now coming to generalized permitting D derivation on L, let D be the trace of a permitting triderivation D on L. A mapping F from L to L is called a generalized permitting D derivation on L if f of x meet y is equal to fx meet y join x meet dy for all x comma y belongs to L. Example, let small d be the trace of a permitting triderivation D on L, then the identity map on L is a generalized permitting D derivation on L. Another example, Let L be an ideal with 0 and 0 not equal to A belongs to L. Let small d be the trace of the permitting triderivation D on L defined by capital D of xyz is equal to x meet y meet z meet A for all xyz belongs to L. Then if we define f from L to L by fx is equal to A meet x for all x belongs to L, then f is a generalized permitting D derivation on L. If we define f as fx is equal to x meet A for all x belongs to L, then f is neither a derivation nor a generalized permitting D derivation on L. If we define fx as 0 for all x belongs to L, then f is a derivation but not a generalized permitting D derivation on L. Here the theorems depends on generalized permitting D derivation on L. Let small d be the trace of a permitting triderivation D on L and f be the generalized permitting D derivation.
Raibabu garu, you have only 45 seconds is there.
Okay,
time.
sir. Then
So
the
kindly
following holds fx meet dx is equal to dx for all x belongs to L and fx less than or equal to x for all x belongs to L and fx and fy meet f of x meet y is equal to f of x meet y. Another theorem, this is the let small m be the maximum element in L and small d be the trace of a permitting triderivation on L and f with generalized permitting D derivation on L, then the following 5 conditions are holds. And another theorem, let D be the trace of a permitting triderivation D on L and f with a generalized permitting D derivation on L, then the following 4 conditions are holds. Another way define a set fix f of L is equal to x belongs to L such that fx is equal to x. Now we conclude this paper with the following theorem. Let D be the trace of a permitting triderivation capital D on L and f be a generalized permitting D derivation on L. If f is a joint preserving mapping on L, then fix of L is an ideal of L. These are the main theorems.
Raibabu garu,
permitting D derivations.
sorry to
Thank
Raibabu
you, sir.
garu. Hello.
Thank you, sir. Thank you.
Very good, good. Nice presentation.
Thank you, sir.
Okay, sir. Raibabu garu, I am Professor C.H. Srinivas Rao.
Oh, nice meeting, sir.
Sir, Mrs. Evan College has been transferred to here only, Narsipattam, then Narsipattam transferred to here. Okay.
I know, sir. I know, sir. I know very well about you, sir.
Thank you, sir. Very nice presentation. Okay.
Thank you, sir. Thank you.
Sir, due to time constraints, sir, that is the
Yes, sir.
reason
Yes, sir.
to
That's right.
allocate only 5 minutes to each and every candidate.
Yes, sir.
Even then, your presentation is very good.
Thank you, sir.
Okay, thank you. The next participant, I am calling the next participant. Yes, sir, Sridevi, are you there?
Yes, sir.
Thank you, Raghav Garu. Thank you, Raghav Garu.
Thank you. Thank you.
Sir, visible my
Yes, sir, Sridevi, are you there?
Yes, sir. My voice is audible, sir. Can you hear my voice, sir?
Dear Sridevi Garu.
Yes, sir.
You have only 5 minutes time.
Okay.
Within 5 minutes, you should finish your presentation.
Okay, sir.
So you should focus on main results.
Okay, sir.
And examples, if any.
Visible my PPT,
finish
sir?
within 5 minutes.
Sir, can you see my PPT?
No. It's not visible. You please present your PPT, please. Share your presentation on screen.
Sir, I share. I see my PC.
Yeah. It's coming, but slowly due to some technical problem, I think.
Okay, sir. Now, sir?
No, it's not visible now.
Sir, now?
Okay.
Okay, sir. Good evening, one and all. Gathering here. I am Dr. S. Sridevi, Queen's College of Arts and Science.
Please share your screen, madam. Okay.
I'm going to present my paper, Study and Cooperative Non-Cooperative Game Theory Techniques, Game Theory Security for Wireless Sensor Networks.
Madam, your paper presentation is not visible on the screen. Please. Sridevi Garu.
Yes, sir.
It's now. Okay. Proceed, madam. Continue.
Okay.
Hello.
Now I'm going to present my
yes, continue.
topics.
Let you continue.
Okay. cooperative, non-cooperative game theory techniques in
So
wireless
please
sensor
raise your
networks.
voice, madam.
Study and cooperative, non-cooperative game theory techniques in wireless sensor networks. Objective of my paper: designing an efficient protocol to maximize the security of sensor node during the transmission and reception, thereby maximizing network lifetime wireless sensor networks using cooperative, non-cooperative game theory techniques. Maximizing security of each and every node in the network during the transmission and reception data, thereby maximizing network lifetime with respect to energy constraints using cooperative, non-cooperative game theory techniques. Operation research is a scientific approach to problem solving for executive decision making. Game theory is a main mathematical models formulated to study the situation, conflict, and cooperation and non-cooperation. It is divided in the set of game theories, set of players, set of actions, set of preference. This is a rules of game theory.
Madam, please share the screen.
Two category: mixed strategy and pure.
Madam, your
Mixed
screen
strategy.
is not visible.
Madam, still your screen is not visible on the screen, madam. Please.
Now, sir. Sir.
Not visible now.
Shall I share my PPT, sir? Can you share my PPT?
Please
Share
make
you.
it clear, madam.
Sir, shall I share my PPT? Can you share my PPT?
Not possible, madam. Not possible.
Okay. What I do, sir?
Please share the conclusion even.
Okay. Game theory divided two categories. Pure
So,
strategy. Yes.
madam, continue, madam.
Thanks, sir. The game theory divided classified two categories: static game, dynamic game. Static game exists only one steps, which means that player move their strategies simultaneously without any knowledge what other player is going to play. Dynamic game, player move their strategy predetermined order, meaning that move one player is continued and by move the another previous player. Non-cooperative game theory, the captain take the decision, allow the implement that places. Cooperative game theories, all players take the decision, implement them. Received security signal strength. We start by introducing the permutation which have been used throughout the results in this research scheme. This hypothesis has been divided into 5 major categories. The nodes should be first placed coordinate behavioral economics. The nodes then position in the non-cooperative game theory philosophy techniques. Third one, create cluster head using negation game philosophy, the collaborative and non-collaborative game theory classes. The node are therefore the forced to submit the game theory classes before it can be used to determine amount of security. Such incorporate connection point in sleep mode using repeated game theory. In each these instances hardly look at the lifetime networks. Wireless sensor networks. Wireless sensor networks relying cooperation among the group of nodes. Lack of energy nodes show certain behavioral patterns and must be rational enough. Wireless sensor networks made up
Madam,
the
Madam
thousands
Sridevi garu, you have only 1 minute time is there left.
Okay, sir.
Only 1 minute time is there.
Central situation via Wi-Fi. The sensor
So
network
try to
is
finish within 1 minute.
Okay, sir. Composed of detector, fields, edge devices, sinks, and tags supervisor. Taxonomy of game theory divided using the cooperative, non-cooperative, repeated game theory, Burgenian game theory, Bayesian game theory. The typical game theory approaches terminological used the wireless sensor networks. Game with wireless sensor network relation between motivation, scope of present work. The green color shaded restricted area in which this research in my undertaken. Stimulation tool, network stimulated decrease event stimulator for modeling wired and wireless network scenarios. Network simulator constructed by combining advantage of two languages C++ and Actual. The C++ and Actual mirror implementation with one-to-one correspondence. Conclusion of my paper: the security of each and every node is maximized by using cooperative non-cooperative game theory. It aims to present some problem of wireless sensor networks addressed with the help of game theory models. This is also aimed to achieve security shielding sensor nodes to switch between security conserved models of an operation and security routing algorithm. Clustering and destiny control to information fusion are also achieved. Future work: the existing of work can be applicable only for static network. In future can be extended by dynamic network scenario. These are my
Okay, madam,
references.
time is over.
Thank you to all.
Thank you very much. Time is over. Okay,
Okay,
very nice presentation. Next participant, I request MK Gupta. MK Gupta, are you there for paper presentation? Hello. 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 MK Gupta, Department of Mathematics, Gurugas Das Viswanajalam, Central University. Are you there? Next participant, MER Kameswari.
Sir, already presented yesterday morning.
Okay, thank you. Next, the next participant, I request R. Venkata Arvindaraju. Are you there? Hello. Hello. Venkata Arvindaraju. 9. Hello. Venkata Arvindaraj garu, please be ready. Time starts. Are you there? Hello. I request the next participant, CH Prabhakar Rao. I request CH Prabhakar Rao for paper presentation. Now I request the next participant, Sujata Kumari Srileka. Sujata Kumari. Srikala. Madam, hello. Sujata Kumari. Lera. Next participant, Sumati Malik.
Sushmita Malik. Yes, I am here.
Susmita Malik. Are you there?
Yes, yes, sir.
Okay, madam. Only 5 minutes time. Within the 5 minutes, just you should finish your talk.
Okay, okay.
You should focus on main results and examples, if any. Maximum, you should finish within 5 minutes.
Okay, okay.
Starts now.
The paper is visible, sir?
Yeah. No, not visible. Your please share your screen. Not visible, madam. Hello.
Hello.
Your paper is not visible on the screen, madam. Please.
Okay, okay.
Susmita Malik garu.
Yes, there is, sir.
Still, it's not visible on the screen.
Okay. 1 minute, sir.
Okay. Time duration is only 5 minutes.
Okay, sir. Now?
No.
Now is it visible, sir?
Just slightly, just you rotate it. You rotate.
I have to rotate it.
Half of the title is visible.
It's like landscape mode, madam.
Make it clear, madam.
Need to. It's not in the proper direction.
Yeah.
Now?
Not visible, madam.
We can see just your screen, yeah.
Yeah.
Can you make it as a portrait mode, portrait? Can make it to the right
Please
side.
rotate it, madam.
You rotate
It's
it to
not
the
in the
right
proper
side.
direction.
Rotate to the right side. Ma'am, in the down of the emblem, there is a rotate symbol, ma'am. If you click that, it will change.
Okay, 1 minute, sir.
Yeah, now it's okay.
Right now it's okay, madam. Please continue.
Okay. Okay, I am Shushmita Mullik, research scholar in the Department of Mathematics, Vishwabharati. My work is inter-ideal in regular and interregular semigroup. These are the outlines.
Madam, continue.
Yes. So, skipping the first introduction part, I want to say what is the interior ideal. The concept of interior ideal in semigroup has been introduced by A. Lajos, and this has significant contribution in the study of interior ideals in semigroup. A subsemigroup I of a semigroup S is called an interior ideal of S if SI is subset of I. Now we can easily check that every ideal is an interior ideal of a semigroup. Next, a regular semigroup is a semigroup S in which every element is regular. That is, for each element A belongs to S, there exists an element X belongs to S such that A equals to AX. That is, A belongs to AS. S is said to be interregular if for each element A belongs to S, A belongs to S square S. This is called duo semigroup if every one-sided ideal of S is two-sided. Now, for any element A in a semigroup S, the smallest left ideal, right ideal of S containing the single element A is denoted by LA, RA, IA and defined by LA equals to
Madam
S union.
Susmita Garu, please press the rotate symbol. It will be comes in the proper direction. So your PPT is not visible clearly on the screen.
Ma'am, in the right side bottom, there is an emblem, right? Andhra University emblem. There you can see the rotation symbol. We are
Actually, I
getting
can't.
vice versa, ma'am. We are getting vice versa.
No problem, madam. Continue your talk.
Okay.
Already 3 minutes time is over, madam. So
Okay.
please continue your presentation, madam.
So yes, sir. So the interior ideal generated by a single element A is defined by A union S square union SS. Here we have an example. Here we have an example S with a binary operation which is defined by the cat table. Here we can easily check that BD and CD are the interior ideals of S, but none of them neither left ideal nor right ideal of S. That's not an ideal of S. The first question arises when the interior ideal and the ideals in a semigroup coincide. Here we have some results, and following this result, we can conclude that in a regular semigroup, the interior ideal and the ideal coincide, and as a corollary, in an interregular semigroup, an interior ideal and the ideal coincide. Next, we have some results which discuss the interplay between the classes of all interior ideals and other ideals. Next, we have introduced some definitions of different classes of interior ideals. That is, an interior ideal I of a semigroup S is semi-prime if for any interior ideal A of S, a square subset of A implies A subset of A. Whereas an interior ideal I of a semigroup S is called completely semi-prime if for any A belongs to S, a square belongs to I implies A belongs to I. And an interior ideal is called prime or strongly prime interior ideal if I1 at subset of I implies I1 subset of I or I2 subset of I.
Madam, I request you, madam, half-minute time is there. Please finish your
Okay.
presentation.
Here we have an example. In this example, we can see that A, AB, AC, and ABC, these are the interior ideals. Here, ABC is a strongly prime interior ideal, but the A is not strongly prime interior ideal by the definition. Here are some results. At last, we have introduced the minimality of interior ideals what is minimal interideal? An interideal I of a semigroup A is said to
Thank
be
you,
minimal.
madam. Time is over. Thank you very much for your paper presentation. Thanks a lot. Next, I request the next participant, Halim Yahoi. Are you there for paper presentation?
I am here, sir. Hello.
Okay. So,
I am here, sir.
time constants, only 5 minutes time is there. Within the 5 minutes, you should finish your presentation.
Okay, sir.
Let's start now. Please share your screen.
Are you see?
Not visible, madam.
It visible?
Not visible now.
We are getting black screen, ma'am. Once close the presentation and again open it. We can see your screen, but we can't see your presentation.
Is there any technical problem?
Yes, sir. Now, are you see?
Take the help from the technical assistant, if any.
Ma'am, we can see your screen, but we can't. Just open your talk, ma'am. Now open the talk. Now open the presentation.
Ah, right. Okay.
Yes, yes, yes.
Continue, madam. Continue. Hello.
Hello, sir.
Continue,
It's
madam.
not my screen, this.
It's clear.
This? Can you see?
Yes.
Yes, yes.
Semi-linear integral differential? This, sir. Sir. Hello, sir.
Yes, ma'am. We can see your presentation. You
والله
can change
الحمد
the
لله
slide.
او عيط له ما عبيوش دوك نازل نعيط.
Are you see my presentation, sir?
Yes, yes, ma'am. Yes, yes. You can change the slide.
Good morning, everyone. Thank you for accepting me your conference. My name is Ahlam Yahyawi and from University of Rumsila, Algeria. We begin by giving outline of my work, motivation. This work is devoted to study the existence of solution of some non-standard integral differential problems of non-local type. We use the method of perturbation to establish such existence results. We have more particularly in mind an isotropic singular perturbation. Adding perturbation terms involve a small parameter epsilon, where the epsilon only acts on some of the direction of domain variables. The techniques developed in several recent works for different type of equation, elliptic, parabolic, and hyperbolic. We set our problem omega equal omega 1 times omega 2, and we have x applied the component of x into x1 and x2 with the weight function h over h defined satisfy this condition, and we consider the following a weighted anisotropic Sobolev space without the gradient respect to x1. And due to the presence of non-local terms, we have we consider this space of non-local term L of U, and our problems is like that. To either have non-local terms, have a non-local non-standard equation with non-linear function g, have a non-local terms given by a partial integral of hu. And we test the first equation in this problem by h by the function test function hv rather than v to have this wake formulation. And we can see that we lose the differential in the direction x1. For this, we approximate these problems by give another problems, and we add the differential in the direction x1 multiplied by perturbation terms epsilon square. And of course, we test in the equation by HV to have this wake formulation, and we study the wake solution in this WH W omega H space, and we add the gradient respect to x1 is without weight. And of course, our our main results.
Madam, only 1 minute time is there.
Okay, sir. And we have this lemma to give this lemma give us the convergent of the non-local term L of U, and we give some condition about the nonlinear functional J, and we define this functional capital G, and we give this function associated J epsilon as we investigate the existence solution as critical point of this functional J. And we need to compute the derivative of G is given by this theorem, and we can see that the derivative of G is similar to the wake formulation of the perturbed problems. And our existence result, we give the condition about J by these forms, and we need to get the solution is minimize this functional G is the solution of SP epsilon of the perturbed problems in wake sense. And this the proof of
Madam, please conclude, madam. Time is over.
Okay, this is an example, and pass to the limit. Let epsilon go to the 0 to have this result, and this proof, and that's some reference. And thank you for your. Thank you.
Thank you very
sir.
much. Thank you very much, madam, for your paper presentation.
You're welcome. Thank you.
Thanks a lot. I request the next participant, Slee and Jarjahi Tahar. Are you there for paper presentation? Good evening. Are you there, Slee and Jarjahi Tahar? Hello. Good evening. Hello. Hello. The respected Jarjahi Tahar and Slee. Next, I invite the next participant, Sabha Bhai Bichi. Sabha Bhai Bichi. Are you there, please? I invite the next participant. Hello. Hello. Please respond. Hello. Dear Arvindraj garu, please stop your share. Please stop your. Arvindraj garu. Mute share. Arvindraj mute. ఒక్కసారి సభ బై పిచ్చి అని ఆమె లేరు కదా. నెక్స్ట్ నవ్వి బందార్జా దొరై ఎఫీనా.
بغلا هذيك قدام.
సభ. Hello. Continue, sir. Continue your presentation, please. Hello.
Ma'am, please start your presentation. Ma'am.
Hello.
Hello, sir. Can you start now?
Yes, start, madam. Please present your presentation.
Hello.
Okay, madam, responded. Please continue, madam. Continue your presentation, please. Good evening, madam. Please respond.
Okay.
Just start your presentation. Madam, your voice is not audible. Hello. Kindly make it clear, madam. Your voice is not audible. Yes, okay. Madam, visible, madam. Your title is hello. ఎవరు సభాని ఇది నౌక బౌండ్ జరిందా బౌండ్ జరిందా బొజ్జరిందా నౌహ బొజ్జరిందా దొరై ఎఫీనా I invite the participant Dorai Afina Yoro Mustafa. Are you there for paper presentation?
Hello. Hello.
Hello.
Hello. I am here.
Okay, madam. Okay, please continue your presentation.
Yes, I am going to share my presentation with you.
Yeah. Please share your screen, madam.
Yes.
Continue, madam. Continue, visible.
My name, good morning, hello. My name, good evening, my name is Bujrida Nuha from Pure and Applied Mathematics Laboratory in the University of Jijel in Algeria. I am here today to talk about existence results of sweeping process with non-convex Fourier perturbations supervised by Professors Afanduria and Yaro Mustafa Fatah. This work that I will be showing is organized as follows. We start first with the general introduction and we go next to the notations and preliminaries. Then we finish with the purpose of this work, which is proving the existence of a solution. Let's begin with the general introduction.
Madam, small announcement. Madam, small announcement. You have only 5 minutes time limit. So within the 5 minutes, you should focus on main results and examples, if any. Please try to finish within the 5 minutes your talk.
Yes, sir.
Okay. Continue, madam. Continue.
The general class of differential inclusion, known as the following sweeping process, have been introduced and thoroughly studied in the period of 70s by Morrow, plays an important role in elastoplasticity and dynamics. That differential inclusion can be expressed in this form, where CT is a closed convex set moving in an absolutely continuous way in an infinite dimensional Hilbert space H, and C denotes the usual normal cone. In 2, the authors prove an existence results in Hilbert spaces with regular set value mapping C of the perpetual sweeping process problem defined as follows. 2, where F is an upper semi-continuous set value mapping with convex compact values. In the present work, we extend the results in 6 in many directions. The main purpose of this proof to existence of solutions for the problem as PPF, where we have this equality with B strictly positive is a moving time dependent closed convex values of Rn, and F defined as follows is a multifunction with multi-closed non-convex values and the Lipschitz with respect to the Roe-Hausdorff distance with minimal non-satisfied linear ground condition. Through this work, in the second section, we will be recalling all the needed concepts. Then in the third section, we prove the existence of solution for the considered problem. Let's see now the notations and preliminaries. We denote by. And we show some resources which being used. Let's continue with finding and proving the existence of a solution. We consider the following assumptions. H1, H2, H3, and H4. Now we pass to the main theorem of this section. Suppose that H1, H2, H3, and H4 are satisfied. Then for every U0 belong to CB0, the problem as PPF has an absolutely continuous solution U. Satisfy this inequality with the given value of gamma. In the proof, the following discretization lies at the heart of many proofs for the sweeping process. For every n greater than or equal to 0, we consider partition of the interval 0t by the points, and we denote it by gt by the limit of minimal norm as follows. So we can find the estimate 5. To prove this theorem, we go through the following steps. In step 1, construction of the sequence. For k is equal to 0 and since ct has ct1 and has closed convex values, we get these estimations, and by 4 we have the inclusion 6 using h1 and the following proposition, and by 5 we get the inequality 7. So the points x0 and x1 and xkn have been constructed, and we can find this inclusion by using the characterization of the normal cone in terms of the projection operation. We find this inclusion and 8. Then it follows from the Gronway lemma, the following Gronway lemma. We get the inequality 9. Then by relations 9 and 8, we obtain the inequality 10. Step 2, construction of approximate solution. We define un as in 10 and its derivative as follows. Relation 10 and 11 imply the inequality 12. So by construction, we have this estimation. we define then the function delta n and theta as shown in the inequalities 15 and 16. Then we have this estimate. In step 3, the convergence of sequences by using the theorem of Ascoli-Arzelà, we conclude that UN is relatively compact in the Banach space of all continuous mappings. Since this equality, we concluded from the consequence of Ascoli-Arzelà theorem that there exists subsequences UN converges to an absolutely continuous mapping U, and the derivative of UN converges weakly to the derivative of U in the space L. Then we have these equalities. So it comes from theorem, the following theorem. And by H4, we have the sequence Hn is a Cauchy sequences in the Banach space of all continuous mappings. Hence, the sequence Hn converges uniformly to some function H with this inequality. Step 4. We shall know that U is a solution of SPPF. By H1 and 30 and 18 and this limits equal to 0 and the closeness of CB, we get that UT is belong to CBT. On the other hand, we have 21. By 21 and 90 and the properties of the normal cone, we get this inclusion. So finally, in application of the measure theorem to this sum, we obtain this inclusion, and further by using H4 and by the closeness of FTUT, we obtain HT belong to FTUT. The proof of theorem is complete. Conclusion, we conclude that the problem SPPF has an absolutely continuous solution with proposed basic assumptions. Assumption
Madam, you have only 1 minute time is there. You have only 1 minute time.
I'm
Please
going to
finish your
finish.
presentation within 1 minute.
Basic assumption H rho, Lipschitz property of the moving set CT and the perturbation FTU, but we leave its convexity. In our proof, we use discretization techniques based on the Catenat products algorithm. Those are some references which I used. Thank you for your attention.
Okay, thank you, madam, for nice presentation.
You're welcome.
Next, I invite the next participant.
Hello, sir. Can you start now, please?
Madam, yes. Permit. Okay, madam, are you ready for presentation? Shabab Babichi. Madam, are you ready for presentation?
Yes, I'm here.
Okay, continue, madam. Continue. Just you have only 5 minutes time. Within the 5 minutes, please, you should finish your presentation. Please note this point, madam. Madam, continue. Madam, please present your paper, madam. Please. It's visible.
It's okay.
Okay. Madam, please start your presentation, madam.
Hello, good day. I'm Can you start?
Continue, madam. Start your presentation now. You have only 5 minutes time, madam. Within the 5 minutes,
Sabah
you should
Baybes,
finish your presentation.
PhD student. Today I present my work entitled Blow Up for a Complete Nonlinear Wave Equation with the Fractional Damping and the Source Term. The work plane consists with the by introduction, preliminary, and the blow up of solution. In introduction, in recent years, fractional calculus has been increasingly applied in different fields of science, physical phenomena related to electromagnetic propagation of energy, thermal stresses, are successfully described by fractional differential equation. We start by introduction. In recent years, fractional calculus has been increasingly applied in different fields of science, physical phenomena related to electromagnetic propagation of energy, thermal stresses are successfully described by fractional differential equation. Fractional calculus allows for the investigation of the non-local response of mechanical systems. This is the main advantage when compared to the classical calculus. In the literature, a number of definitions of the fractional derivative have been introduced, namely the Hadamard, Erdős-Kóbor, Riemann-Liouville, Jade Wheel, Gromov-Letnikov, Jumari, and the capital representation. In this representation, we consider a coupled nonlinear wave equation with fractional damping and source term. We investigate the existence and the uniqueness properties of solution for the initial boundary value problem and prove and estimate the time of blow-up of each solution in Sobolev space by means of the conductivity theorem of H level. We consider the following system as follows: with the boundary condition and the initial data, where omega is a bounded domain with smooth boundary of first order omega in Rn, n equal 1, 2, 3. Let this equality with this is hypothesis, we can easily verify that this inequality as follows. There exist two positive constants C0 and C1 such that this inequality as follows. Now, the second, the well-poisonedness, we say the local existence and uniqueness of the solution of problem. We have an important theorem. Assume hypothesis A1 hold, then for any initial data, this initial U0 in this domain, and U1 V1 in space L2 the omega, the problem admits a unique local weak solution. For eta is positive, we define the fractional derivative in the sense of capitals as follow this equality. We define the full energy of the system as follow. Yes, the derivative of energy is defined as follow. Integrating from 0 to t, we obtain this equality as follow. In blow-up of solution, we have an important theorem. Suppose that UV is the solution of the system 1, 4, then for any t positive, there exists t equal inferior that t and sufficiently large initial data for which UV blow-up of t. To prove, let HT defined as follows, where D and L are positive constants to be determined later. Obviously, the derivative of H equal this equality. Let H, where D and E are positive constants, to be determined later. Yes, considering the functional Ct is equal, where epsilon positive and sigma verify this inequality. Yes, is the complete the proof. Let us define the extension operator to be whole domain as follow: L omega 2 and L k alpha 2 is defined as follow. The next choose B so that verify this inequality. Finally, I have some reference to related to my work. Thank you for your attention.
Thank you, madam, for nice presentation.
Thank you, sir.
Very good. Next, I invite the next participant, Lekhal Rachid. Lekhal Rachid, are you there for proper presentation?
Yes, I am here.
Okay, sir, only 5 minutes time is there. Just you should try to finish your presentation within the 5 minutes. Just for that, you should focus on main results and examples, if any. Please note this part.
Can you open share?
Please start the.
Can you open share, please?
Share your presentation now.
Can you see my presentation?
Yes, sir, we can see your presentation.
So, hello everybody. I welcome you all to this presentation, which is entitled "Some Results for Almost Only Star Manager." So, first we have a plan of our work, such that we have introduction, new selection principles, results and theories, conclusion. Introduction. In 1999, Cauchy used the star operator for a space A of space X and family P of a subset of X star AP equal union G such that A intersection G different of T set to define the star selection principles star Menger and star Rothberger and star Hurwitz AP. So the symbol as fine AB denoted the selection hypothesis that for each sequence Un of elements of A, there exists a sequence Vn such that for each n, Vn is a finite subset of Un and union star is an element of P. We define O denote the collection of all open covers of space X. So by open cover we have space X is said to be star Menger, respectively star Rothberger if it satisfies the selection hypothesis as fine OO respectively as 1 OO. And space X is said to be star Lindelof if for every open cover U of X there exists a countable subset V of U such that star union VU equal X. Now, selection principles. In this section, we introduce and selection principles in connection with the star operator, strongly star, and almost strongly star, and weakly strongly star. Definition: strongly star Lindelof. Space X is said to be strongly star Lindelof if for every open cover U of X there exists a countable subset Fn of X such that union star Fn U equal X, and space X is strongly star major if for every sequence Un of open covers of X there exists a finite Fn of X xn in X such that union star Fn Un equal X. Strongly star Rydberger. For every open sequence of open covers of X, there exists Xn such that union star Xn Un equal X. Now we introduce and given new selection principles. Almost strongly star Lindelof. Space X is said to be almost strongly star Lindelof if for every open cover U of X there exists a countable subset Fn of X such that closure star Fn U equal X. Definition 2: almost strongly star major, respectively weakly strongly star major. So for every sequence Un of open cover of X, there exists a finite Fn of X such that union closure star equal X, respectively closure union star Fn Un equal X. And definition 3: almost strongly star Rydberger, respectively weakly strongly star Rydberger. So for every sequence Un of open cover of X, there exists Xn such that union closure star Xn Un equal X, respectively closure union star Xn Un equal X. Results and theory. So in this section we give some propositions and theorems by using the new definition above. Lemma. Every almost strongly star major space X is almost strongly star Lindelof. So by definition above, we have this relation between definition. Strongly star Rydberger is almost strongly star Rydberger, and almost strongly star Rydberger is weakly strongly star Rydberger. And we have strongly star Rydberger is strongly star major, and strongly star major is Lindelof, because every finite is countable. And we have strongly star major is almost strongly star major, and similar with weakly. Theorem: a continuous image of almost strongly star major space is almost strongly star major, and similar we have a continuous image of weakly strongly star major space is weakly strongly star major. And we have a continuous image of almost strongly star Lindelof, respectively. Almost strongly star Rydberger space is almost strongly star Lindelof, respectively. Almost strongly star Rydberger. And we have similar with weakly. Theorem: for a paracompact space X, the following are equivalent. X is almost star major space, X is almost strongly star major space, X is almost major space. We have almost major is almost strongly star major, and almost star major is almost star major. And in paracompact we have almost star major is almost major. Then we have equivalent. Similar with weakly, so we have weakly star major and weakly strongly star major and weakly major are equivalent in paracompacts. Similar with case Rydberger. Definition: We say that topological space X is d-paracompact if every dense family of a subset of X has a locally finite refinement. So we know that every almost strongly star measure is a weakly strongly star measure. Then by definition is paracompact. We have in paracompact union closure V equal closure union V. Then in this case we have weakly strongly star measure and we almost strongly star measure are equivalent in case the paracompact. Conclusion: the main theory of selection mainly describes overlap properties and local properties in topological spaces, especially function spaces. His first source come from the theory of measurement and the theory of basis in metric spaces. In mathematics, the main theory of selection describes mainly the properties of combination overlays of topological spaces. And we have some reference used in this paper. Thank you for your listening and attention.
Thank you very much for your nice presentation. Hello.
Thank you.
Now I invite the next participant, Samia Galia and Darai Afine.
Yes.
Are you
Yes,
there for
I am
paper
here.
presentation?
Yes, I am here.
Yeah. Just your time is only 5 minutes. So kindly finish your presentation within the 5 minutes. For that, you focus on only main results and references and examples, if any. Please continue.
Dear professors, I present to you this work entitled An Optimal Control Problem, prepared by me and Dr. Afan Doria. Table of contents, notations and preliminaries, iterative differential equation, iterative differential inclusion, an optimal control problem. We begin by introduction. Iterative differential equations are a special kind of state-dependent differential delay equations, have distinctive characteristics. There are many pioneering research papers that have developed the study of iterative differential inclusion. Other in paper 1 apply the contraction principle of the existence of the unique monotone solution for the iterative differential equation. The no-autonomous equation, the problem P, was investigated by Ande in paper 2 and Brandt in paper 3. Motivated by the above discussions, the main purpose of this paper considered the sufficient conditions for stating the existence of the solution of the problem P. Moreover, we assume a new problem which is perturbed for a first-order iterative differential inclusion governed by a maximal monotone operator, the problem PA. Then we present a positive example for an optimal control problem associated with problem PA. Notations and preliminaries. We give the definition and some properties of the maximal monotone operator. For example, do you see the approximation in proposition 1, 1? In our study, we need the fixed point theorem and Ronwell lemma. Iterative differential equation. We begin by the following existence result of the problem P. Theorem assume that F is characteristic mapping. 2. There is a non-negative function M such that the following inequality are satisfied.
then the problem P has an absolutely continuous solution. Proof. Step 1. Consider the integral operator T defined by TH equal EH, where the EH is the solution of the problem 1. By applying the Axela-Ascoli theorem and properties of integrable functions, we proved that T verified the conditions of Schauder's fixed point theorem. Step 2. We used the Scorza-Dragoni theorem and step 1 to prove that the problem P has a solution if F is a Carat-Eudori mapping. Iterative differential inclusion. Theorem. Let F be a Carat-Eudori-Lipschitz mapping and A be a maximal monotone operator. Suppose that the assumption H1, H2 are satisfied. So the differential inclusion P A has a unique solution. For the proof of our theorem, we need the following results. Theorem. Let F be a Carat-Eudori mapping and A be a maximal monotone operator. Suppose that H1, H3 are satisfied. So the problem P has a solution. Proof. By using the approximation, we write the problem P A in the form of an iterative differential equation. So, by theorem 2.1, we conclude the existence of solution of this equation. On the other hand, by using proposition 1.1, Lübeck theorem, and theorem 1.5.2 in paper 3, we prove thus the existence of solution of problem PA. Now we give the proof of theorem A1, existence of a solution. We define a new problem satisfies the hypothesis of a theorem T1, and we prove that U is the solution of the problem PA if and only if U is the solution of the problem PF. Uniqueness of solution. Let U1, U2, two solutions of the problem PA by monotony of the operator A and Gronwell-Lehmann, we got U1 equals U2. An optimal control problem. We begin by some notations and definitions. For example, Donaro topology, the set of original controls, the set of relaxed controls. For the proof of next theorem, we need the following lemma. Now we present our main result in this section. Theorem. Let A be a Carat-Eudori integrand satisfying the following assumption. Let's consider the control problems P L and P R, where U Ni and U C is the unique solution associated with Ni and C of the problem P L and D R. Then we have length P L equal mean P R. Finally, we give some references. Thank you for your attention.
Thanks for nice presentation. I invite the next participant. Thank you. Next presentation, Samia Sohali Feroz. Sohali Feroz, are you there for a proper presentation? Hello? Feroz. Feroz, are you there? I invite the next participant, WB Amar Wahua. WB Amar Wahua, are you there? WB Amar Ohua, are you there for paper presentation?
Yes, sir.
Yeah. Please continue. Share your presentation on the screen. Hello.
Is it clear?
Yeah. Respected participant, just only 5 minutes time. You
Yes,
should
sir.
finish your presentation within the 5 minutes. Continue. Continue.
Hello, I would like to thank you for accepting my work to be a part in your conference. I will present my work to you under the title Existence Result for a Kirchhoff type wave equation with variable exponent nonlinearity. This work consists an introduction, main result, and some references. We start by introduction. We consider the following boundary value problem 1-1, where omega is a bounded domain in Rn with small boundary and m of s equal a plus bs with the positive parameter a b. The p Laplacian operator given by this following: R and m are given measurable function on omega, satisfying this following. The equation 1 can be viewed as a generalization of model 1-2 introduced by Kirchhoff, Masoudi and all considered the problem 1-3. They studied the existence and no existence of solution with variable exponents. Masoudi also and Talamah proved the blow-up infinite time of solution 1 for problem 1-4. We have now a main result. We define the potential energy functional and Néhary's functional respectively by the following 1, 5, 1, 6. We consider A equal B equal 1, and this does not change the general result. Let's start by this theorem. Under the assumption of lemma 1, the local solution of problem 1-1 is global. For the existence of local solution of problem 1-1, we can refer the reader 5. And for this result, we need the following lemmas. The first lemma, assume that the assumption of R and M and R hold, the Néhary's functional is strictly positive, and beta 1 plus beta 2 less than 1, where beta 1, beta 2 given by this following. The second lemma, under the assumption of R and M, we have the equation 1-7, and this following. The following proof is proved the lemma 2 when we give the energy is less than or equal the initial energy. Now we have the proof of the theorem. We use the lemma 1 in the last term of ET. We get the inequality when this 110. So that we have 111, and by lemma 2 we get 112. This implies that the local solution is global in the time. And we have some references when we used in my work. And thank you for your attention.
Congratulations. Very nice presentation.
Thank you, sir.
Invite Uma Dikshit. Uma Dikshit, are you there?
Yes, sir.
Are you
Good
ready for
evening.
paper presentation?
I'm there, sir. I'm there.
Okay. Please continue. Just only 5 minutes time is limit. So you should finish within 5 minutes.
Yes, sir. Sir, is my screen visible?
Yes, visible.
Okay, sir. So I'm Dr. Uma Dikshit from University Postgraduate College, Usmania University, Telangana, India. My research topic is number theory. In that I have taken up this identity using primitive function module. We generally know what a multiplicative function is and what a completely multiplicative function is. In this particular paper, we will talk about completely primitive functions modules. And earlier identities are given, this Jordan-Toshan function identities by other authors is given in a different way. I have used this primitive function module and given the identity in a different way. So we already know that the multiplicative function is nothing but f of m in f of mn equals to f of m f of n whenever the GCD of mn is 1. And completely multiplicative function will be the same thing for all mn, not necessarily for this GCD to be 1. Now our importance is about the primitive function module. This is the Jordan function which I have mentioned here. I will be required the Mobius function also in one of my lemmas. And I also require this gamma function, gamma r, which is product of distinct prime factors with gamma 1 as 1. And we proceed further. The primitive function module, we are defining it in this way. First of all, we should have an arithmetic function. Then the arithmetic function, we are clubbing it with this particular gamma function which we have defined. So f of nr will be f of gamma nr comma r for all gamma nr equals to this one. And completely, the way we define the arithmetic and completely arithmetic, we are defining primitive and completely primitive function module also. So we have given the definitions. Then we are taking two arithmetic functions and defining two functions, f of nr and f of dr. The earlier author, Cohen, has proved this particular lemma, that whenever it is completely primitive module r, then we have f of nr equals to this value. This is already proved actually before. And we further are proving this regarding the same thing for capital F of r. I have here these two functions. Okay, this is already proved by an earlier author. We also prove it for f of dr over here. So this is also a lemma, so which I will be leaving and going to my main result. So for completely f of h of r be completely multiplication function, we are defining f of r like this. Then I definitely require another lemma where I have to prove f of r equals to not equals to 0, because if you see my main result, I have this Jordan-Toshan function where I have a denominator, I have f of r. So naturally, first I need to prove that this is not equals to 0. So we have proved that also in one of our lemmas. Now coming to the main result, we have the Jordan-Toshan function is completely primitive module. That is my the title of this paper also. With that, I'm proving that Jordan-Toshan function is completely primitive module R. So we are denoting Jordan-Toshan function over here, and we get these values because we have already defined f of nr and h of nr earlier. So using them and knowing that they are completely multiplicative functions, we write their values. As you can see here, we just have it over here only. Here, h of r by gamma r and f of gamma r. Using these earlier lemmas, we have proved these values, and we have this h of r because they are multiplicative functions. I can write it as h of r by h of gamma r. So just adjusting these terms, that h of gamma nr will come down, h of gamma r will go up, and these values getting cancelled, we get this particular value, h of gamma r by gamma nr and f of gamma r by gamma nr. We are denoting it by some value. I mean, instead of having this value, both of them are same because, so we are just writing it as hm by fm, where m is denoting this gamma r by gamma nr. So we got this value, and this is the main definition of proving completely primitive module over here. So this is the final part where I'm after getting its value in a different form in terms of gamma, then I'm proving that it is primitive module. So G of nr, I should prove this one. As you can see here, I'm just going back and here. An arithmetic function, completely primitive function value, if we can show f of nr is f n dash r. So we are showing the Jordan-Toshan function is completely primitive module r over here. So that was my result. I mean, the earlier authors did not use, we have these results with multiplicative functions. So defining a function gamma r. I have just proved it that it is completely
Madam, your time limit is over.
Yes, sir.
So
These
kindly
are the
finish.
references. Thank you so much.
Please conclude.
Thank you, sir. I have concluded.
Thank you, madam. Thank you very much for your nice presentation.
Thank you, sir. Thank you.
I invite the next participant, T. Surendra. Please, Surendra, are you there for paper presentation? Surendra garu, are you there? Are you ready for paper presentation? Hello. Lera? Okay. Oh, sir. I recall R. Venkat Aravindraju. Hello. I invite Venkat Aravindraju. Are you there for presentation? Okay. Thank you to all. Close the session. Now I'm going.
Sir,
yeah.
Sir, if I can submit my presentation now, because I was not able.
Okay. Continue.
Yeah.
Continue.
Uh,
Sir, only 5 minutes time limit. Sir, please note the point. Only 5 minutes time limit. Within the 5 minutes,
sir.
You should conclude, sir. Please.
Yeah.
Please continue, sir.
Yeah. Is everything okay? Yeah. Hello.
Continue.
Yeah. Sir, if I can make my presentation. By the phone.
You continue, sir. No need.
Because
You continue. Please see with your presentation.
Just now there is a problem.
Yes, sir.
So, hello everybody. Let me introduce myself. I'm Saleh of Gijel, Algeria. By a short introduction, let K be an algebraically closed for an ultrametric absolute. We denote by a okay algebra of entire function. And M of the field of meromorphic function in K. In this work, we investigate the growth of transcendental meromorphic solution of some ultrametric Q difference equations. So we consider the following ultrametric functional equations of Schroeder type, where these coefficients are rational functions, and the PQ relatively prime polynomials in F over the field of rational functions satisfies these conditions. Our method is by ultrametric Nonlinear theory. Preliminary and the notation. The absolute value is said to be non-Archimedean if it is satisfies all conditions of absolute, and in addition, triangle inequality. Proposition 1, the following statements are equivalent. So a function f, a meromorphic function, respectively, an entire function is said to be transcendental if it's not rational functions, respectively not a polynomial. Moreover, an ultrametric transcendental meromorphic solution can admit infinitely many zero or infinitely many poles. And we define the maximum models of F for every R greater to 0. Let F be a meromorphic function in K. Using the notation, these notations, we define the compensation function of F by and the Kantian function of 0 as follows, and the Kantian function of poles as follows. Finally, we define the characteristic function of f as follows. The function TF is called the Nabelina function. And this is some properties of TRF. The proposition let f be a homomorphic function on K, then we have f transcendental if and only if this limit equal infinity. F be f a rational function if and only if TRF equal big O log R. Finally, we define the order of growth of a homomorphic function f in K. In a particular case, if f is an entire function, we define rho equal. We studied the equation 1, but the coefficients are constant and q less or less 1. Then we obtain the following result. If f a meromorphic function of solution of equation 1, then f is a rational function which has no poles alpha equal 0 equal 0. This results if the entire solution of equation 1 is a polynomial. In the first part of this section, we are interested in the case of non-constant coefficient in the equation. Then we have the following results: theorem 1 and theorem 2. All transcendental meromorphic solution of equation 4, which have at most finite number of poles, satisfies, and all transcendental meromorphic solution of equation 4, which have an finitely of poles, satisfies. So in the next, we study the ultrametric meromorphic solution of the following equation. With the coefficient are rational functions. Then we have the following theorem. If f is a transcendental meromorphic solution of equation 5, which has at most a finite number of poles, then we have a rho of f greater or equal this fraction. And here are some references. Thank you for your attention.
Thank you very much for your valuable presentation.
Thank you.
Congratulations. Thank you.
Thank you, sir.
A small announcement to all the participants who are here. Just within 5 minutes, the valedictory function is going in this room. Please, all of us, please stay here only. Hello, sir. Congratulations for your presentation. It's very useful and valuable for the young research scholars. Thank you very much for your presentation. I request all the participants to stay here only. Within 5 minutes, the valedictory function is going on in this room only. Thank you to one and all. chief guest of today's function, Professor Krishnamohan sir already came. Please, the program will start within 5 minutes. Please try to stay here only. Thank you to one and all. I request all the participants, please be prepared for the valedictory function.
Good evening. A warm welcome to each one of you to this valedictory function of International Conference on Recent Advances on Nonlinear Function Analysis and its Applications. This is a happy moment for the department celebrating the success of the conference. On this occasion of closing ceremony of the conference, I invite the dignitaries of the dais and on virtual mode to this occasion. Firstly, I invite our President of the function, Head of the Department, Dr. G. Nanaji Rao, to please come on to the dais and occupy his chair. Please honor Sir with a bouquet. I have great pleasure to invite our chief guest, Professor V. Krishnamohan Garu, to please come on to the dais. I invite Sir to please come on to the dais. Now I invite Registrar Andhra University, Chairman of the conference, Professor G. Ravindranath Babu Garu, to please come on to the dais. I hand over the proceedings to the President of the function. I request the President to preside over the function.
So good evening, everyone. It's my great pleasure and honor to welcome you all to this valedictory function of the International Conference on Recent Advances in Nonlinear Functional Analysis and its Applications 2022 on the occasion of the superannuation of Professor G.V.R. Babu Garu. The chief guest of Professor M. Krishnamohan, Sir, Officer on Special Duty, Andhra University, Professor G.V.R. Babu, Chairman of the conference, Professor P.D. and Srinivasu, Co-Chairman of the conference, and myself, the Director, and Dr. P. Anuradha Kameswari, Organizing Secretary of the conference, faculty members of the department, Professor S. Ravikumar, Professor C.H. Srinivas, Professor Captain Ramakrishna, Honorary Professor of, and my teacher, Professor K.K.M. Sharma, retired professors of the Department of Mathematics, heads and faculty members from other departments, keynote speakers, invited speakers, delegates from India and abroad, faculty members of the affiliated colleges, supporting staff, research scholars, student friends, and press and electronic media. This international conference on recent advances in nonlinear functional analysis and its applications 2022 is a two-day event from 29/1/2022 to 30/1/2022. This conference was formally inaugurated yesterday by lighting of the lamp in the presence of the chief guest, Professor P.V.G. Prasad Reddy Garu, our beloved Vice Chancellor, Andhra University, in the presence of guest of honor, Professor K. Samta Madam, Rector, Andhra University, Professor Y.J. Cho, Department of Mathematics Education, Jiosang National University, Korea, Professor Muhammad Imdad, Department of Mathematics, Aligarh Muslim University, Aligarh, India, Professor K.P.R. Sastri Garu, Department of Mathematics, Andhra University, Professor U.M. Swami, Department of Mathematics, Andhra University, and all the guests present here now and participated in virtual mode. The welcome addresses was given by Professor K. Srinivas Rao, President of the inaugural function, Principal, JVD College of Science and Technology. He emphasized the importance of conduct of conference and how effectively researchers can be made use of this. Professor G.V.R. Babu Garu, Registrar, Andhra University, delivered the history of the Andhra University. Professor K. Samtha Madam, Rector, Andhra University, gave her message regarding the importance of the conference to present young research students. So, Professor Y.J. Cho, Korea, emphasized the importance of international conference. Professor K.P.R. Sastri Garu delivered his speech on how to our Professor G.V.R. Babu Garu changed the research from differential equations to fixed point theory. Professor Muhammad Imdad explained about the research importance. Professor U.M. Swami visited the conference and great success, and also visited the Professor G.V.R. Babu Garu. Chief guest, Professor P.V.G. Prasad Reddy Garu, gave his message in depth regarding the future of the present generation in terms of education. Many of the students were inspired by his speech. Myself gave a brief history of the Department of Mathematics. Professor P.A. Kameswari explained about the conference. Vote of thanks was proposed by Dr. M.E.R. Kameswari a PhD student of GVR Babu Garu. Present, she is working in Getam University. Yesterday, there were 2 keynote addresses given by Professor Y.J. Cho from Korea and Professor Vasil Berend, Romania. So 5 invited talks were by eminent mathematicians from across the globe and from our country, followed by paper presentations, which went up to 10:30 p.m. Today, the second day, 9 invited talks by eminent mathematicians from across the globe and from our country, followed by paper presentation, took place till now. This is the second international conference organized in this department. The first was organized by me in 2014 in physical mode for 3 days on the eve of the retirement of my teacher, Professor G.C. Rao. It is my pleasure to place on record that this international conference on recent advances in nonlinear functional analysis and its applications 2022 is a grand success with 2 keynote addresses, 14 invited talks, more than 100 papers presentations, and more than 1,531 participants. So with these opening remarks, I request the organizing secretary to give a brief summary of the conference.
Respected chief guest of today's function, Professor V. Krishnamohan Garu, Chairman of the President of today's function, Dr. G. Nanaji Rao, Chairman of the conference, Registrar of Andhra University, Professor G. Ravindranath Bab Garu, I am happy to present this report on the schedule of the conference proceedings. The International Conference of Recent Advances in Nonlinear Function Analysis and its Applications is organized by Department of Mathematics, Andhra University. The conference brought together many eminent professors and emerging researchers in the area of nonlinear function analysis. It served as a platform covering several topics in 4 technical sessions in 2 days. In the first technical session, we had in the first technical session, on the first day, we had 2 keynote addresses and 5 invited talks. And in the next 2 technical sessions on the second day, we had 8 invited talks, in which we had 4 international speakers: Professor Y.J. Cho from South Korea, Vasile Berindre from Romania, Professor J. Dirick, and Professor F.A. Macrae. And we had 14 invited speakers from India. We had received about 108 papers for paper presentations, which is carried out altogether in 6 sessions, in 3 sessions on 29th and 3 sessions on 38th today. There were about 1,513 participants altogether registered for the conference. All the participants of the conference have joined this conference virtually using WebEx and YouTube links. I'm happy to say that this virtual conference undoubtedly served as a great platform to share and generate research in nonlinear functional analysis and related topics. So we have received 108, and out of which 108 were presented in all the 6 sessions. 101 paper were all presented in the, yes, out of 108. We have received 108 papers for presentation, and out of which 108 were presented in the 6 sessions. I thank the organizers for giving me this opportunity.
Thank you, Dr. Anuradha Kamasuri, for your brief introduction. Summary regarding the conference. The next conference summary report by Chairman Professor G.V.R. Babu garu.
Good evening to all of you. Respected President of this validatory function, Dr. G. Nanaji Rao, Head of the Department of Mathematics, and Director of the Recent Advances in Nonlinear Functional Analysis and its Applications International Conference 2022. Good evening. Dear respected Professor V. Krishnamohan Garu, Chief Guest of this function, good evening. Respected my colleagues, Professor P.D. and Srinivasu, Chairman of this department, Professor K. Ramakrishna, Professor C.H. Srinivasa Rao, Professor S. Ravikumar, Professor K.K.M. Sharma, research scholars, and Professor Dr. M.V.R. Kameswari, and research scholars and supporting staff, good evening. Respected Professor Y.J. Cho from Korea, Professor R.P. Pant, Professor B.S. Chaudhary, Professor D.R. Sahu, Professor B.S. Thakur, and other invited speakers and keynote speakers, very good evening. Dear all delegates, good evening to you all. First, I wish to give a brief note how we organized this conference, the idea how it is arised in our minds. I wish to give a brief note on it. In the month of October 2021, Professor N. Ramakrishna approached me and floated an idea of organizing a conference on the eve of my superannuation. Up to that time, I didn't have any idea. It is a seed of this conference. It is a seed in my mind about this conference. Then I discussed the same in the department, and when I approached our Honorable Vice Chancellor along with our head, our Honorable Vice Chancellor was kind enough to allow us to organize this conference. He has given green signal to us to conduct a conference. Then I initiated consulting all the invited speakers, keynote speakers. Then they responded positively. With the help of organizing committee and committee members, we could reach this state. We reached this state. Now, about the conference, on day 1, 29th January 2022, the academic session started with the keynote address of Professor Y.J. Cho, Gyeongsang National University, Korea, on some inertial projection methods for solving some nonlinear problems. Professor Y.J. Cho discussed some properties of the metric projection and some kinds of the projection methods for nonlinear problems and their convergence. Introduced inertial extra gradient algorithms and proved their convergence theorems in Hilbert spaces. Also posed a single projection method for finding a solution of the bi-level pseudo-monotone variational inequality problem in real Hilbert spaces. Numerical examples are also discussed. The second keynote address is delivered by Professor Vasile Berin de Romania on the existence of fixed points of various enriching contractive type mappings. These enriching contractive mappings are newly introduced one, and the existence of fixed points, it is a new technique and it is interesting one also. We also did some work in this field. Also, discussed new developments for Sirikritz-Russ contractions which are shown to form an unsaturated class of mappings. On behalf of this conference, I thank Professor Y.J. Cho and Professor Vasila Berinde for their valuable addresses and sparing their valuable time. Regarding invited talks, Professor M. Imdad discussed the concept of Suzuki type ZR contraction by unifying the definitions of Suzuki type Z contraction and ZR contraction, and provided examples to show that ZR contractions are more general than Z contraction, and proved the existence and uniqueness of fixed points of Suzuki type ZR contractions. In fixed point theory, the development of fixed point theory is dependent on the generalization of the existing conditions. If we prove a theorem with the generalized condition, it is a new theorem. So, and we have to show that it is a generalized condition also. We have to produce some examples. So, in that way, they showed that Suzuki type ZR contractions are more general than Z contractions. Further, discussed the existence and uniqueness of solutions of family of nonlinear matrix equations. Professor R.P. Pant, I thank Professor M. Imdad for delivering his invited talk. Professor R.P. Pant, Nainital, India, discussed fixed point theorems of Kannan and Chatterjee and the importance of these theorems. Discussed on the Karisti fixed point theorem, which characterizes metric completeness. Consequences of these theorems are also discussed. I thank Professor R.P. Pant for his lecture. Professor B.S. Chaudhary, Shivpur, India, discussed best proximity point problems to determine the distance between two sets, which is an extension of the fixed point problem applicable to the non-self mappings. I thank Professor B.S. Chaudhary for sparing his valuable time and for his giving lecture in this international conference. Dr. Professor D.R. Sahu, BHU, Banaras Hindu University, introduced the parallel normal S iteration technique and studied its convergence rates and solving such problems in infinite dimensional Hilbert spaces under practical assumptions. It has applications in signal and image processing problems. It is a very interesting topic, and he discussed it thoroughly in this conference, and I thank Dr. Professor D.R. Sahu for delivering his invited talk. Professor H.K. Nashine discusses some iterative algorithms to obtain positive definite solutions of nonlinear matrix equations and illustrated by suitable examples. I thank Professor H.K. Nashine for delivering his lecture. On day 1, 2 keynote addresses and 5 invited talks are completed. And on day 2, the first invited talk is delivered by Professor P.S. Avadhani, described various examples of fixed points that occur in day-to-day life. It is very interesting lecture, and I thank Professor P.S. Avadhani garu for delivering his lecture. Professor Anita Tomar explained fractal sets, Mandelbrot sets, and various fixed point iterations, and various diagrams are shown to Mandelbrot sets of Picard iteration, Mann, Ishikawa, and Noor iterations. It is a nice presentation, and I thank Professor Anita Tomar for delivering her invited talk. Dr. Jade Wheel, Dr. Yafia McRae, and Professor J.V. Vasundhara Devi delivered a 3-part joint invited talk which deals with basic theory of ordinary differential equations, qualitative theory of integral differential equations, followed by delay, stochastic, random, and impulsive and fudgy differential equations. And third one, it consists of the qualitative theory of set, fractal, matrix, and graph differential equations, and differential equations involving retardation and anticipation. Also, the variational Lapenoff method, a combination of the nonlinear variation of parameters formula and the Lapenoff method are discussed. I thank Professor Trissy, Professor McRae, and Professor J. Vasundhara Devi for delivering their interesting topic in differential equations in this conference. Professor T. Som from Banaras Hindu University discussed the generalizations of Banach contraction principle, also discussed the existence of common fixed points, coupled fixed point of phi contraction, multi-valued maps, fudgy mappings, etc. on related spaces, namely metric spaces, Banach space, probabilistic metric space, fuzzy metric space, 1CRE SB metric spaces. And these are generalizations in the sense that the contraction condition may be the same, but it is in different spaces. That in that way, these are the this lecture has gained importance, and I thank Professor T. Som for his lecture. Professor B.S. Thakur, Raipur, India, discussed various iteration algorithms and compared their convergence numerically. Empirical evidence related to the rate of convergence of these iterations is also discussed. And this talk is very important in application purpose in the wavelet analysis and signal and image processing problems. I thank Professor B.S. Thakur for delivering his lecture and spare his time to deliver his talk in this conference. Professor Javed Ali discussed the solution of the Hilfer fractional BVP in tempered sequence spaces C0 alpha and LP alpha. For this study, a fixed point theorem of Merkelder condensing operator. It is very interesting. Merkelder contractions are more general than the contraction maps, and it is condensing operator also. And with these conditions, a fixed point theorem is proved, and it has applications. He showed. And this talk is very interesting, and I thank Professor Javed Ali for his lecture in this conference. And now, Dr. G. Nanaji Rao, he delivered a lecture on pseudo-complemented almost lattices, and a one-to-one corresponds between the set of pseudo-complementation on an almost lattice L with 0 and the set of all maximal elements of L is discussed. And in my opinion, I hope that this can be used, the space can be used in order to get the existence of fixed points. It is an open problem, I think. So it is an interesting, and we can extend the results of existing results of metric fixed point theory to the pseudo complement almost lattices. So I thank Professor Dr. G. Nanaji Rao for his nice lecture. Even though he is busy with head of the department and several works, he delivered his lecture. He has shown interest to deliver a talk. That is, I congratulate him. Dr. P. Anuradha Kameswari studied the counting the counting the units in the residue of polynomial ring ZPX, the analog of Mobius function and Euler function in ZPX. The analogs to arithmetic functions like Mobius function, Euler function, Lively function, and divisor function are developed, and some related properties are discussed. I thank Dr. P. Anuradha Kameswari for delivering her talk in this conference. I think that the work of this talk is useful in computer applications, I hope, and it is useful to the society too. And so I thank all the invited speakers, and also I thank all the chairs of the sessions for sparing their valuable time in this international conference. Here I wish to say, by sharing the knowledge of all participants, all resource persons, invited speakers and chairpersons, they shared their knowledge to the participants, and all of you delegates it helps a lot to generate new problems in nonlinear functionals, particularly in fixed point theory and approximation of fixed points, and these talks may suggest direction to solve the problems. Now it is the time to form as a group to discuss research problems, and any unsolved or unsolvable or a problem, to solve a problem, you can discuss such problems with the resource persons. By doing this, you can save time and get the best solution of the problem. Now, in the organization of the conference, a lot of help I have taken from so many persons. I thank all the faculty members, research scholars, and all my students who obtained PhD and MPhil degrees under my guidance for the support and cooperation extended by serving in different committees for the success of this conference. I thank the university authorities for recommending renovation of this seminar hall, and I thank the engineers office staff and electricity office staff for completing the necessary works within short span of time. I thank the university, I thank Professor K. Ramasudha, Honorary Director, University Computer Center, and her team for providing all the facilities to organize the conference virtually in a befitting manner. I thank all that team, excellent service they have given. And I thank the Dean, sanitary and security staff for making the necessary arrangements in a beautification of the premises. And I also thank the institutions, academic institutions and banks, particularly Andhra Bank, State Bank, and Union Bank of India. I welcome Union Bank of India manager. He came here and I welcome him. And I thank all of them, and also some police institution, police officers, they also given support to conduct this conference, and I thank all of them wholeheartedly. I thank all of them. This Herculean task is possible only because of your full extent support and cooperation. Even though we conducted it successfully, if there are any lapses, kindly excuse us with a broad heart. Thanking you. Thank you, one and all.
So thank you very much, Marshall, for your elaborate speech regarding conference and each and every point you discussed it here. The next one, introduction of the chief guest by Anuradha Kamasuri.
Dignitaries on the dais, I am privileged to introduce our today's chief guest, Professor V. Krishna Mohan Garu. Professor V. Krishna Mohan Garu is a professor in the Department of Commerce and Management Studies, Andhra University, Visakhapatnam, having a total teaching experience of 31 years. He teaches marketing core and specialization papers to MBA MCOM students. He got his master's degree in both commerce and commerce MCOM and management MBA, and PhD in marketing and management from Andhra University. He did faculty development program of 1 year duration in marketing at IIM Ahmedabad in 1989-90. He has authored 6 books, contributed several lessons to MBA distance education course material at Andhra University. He got 67 research papers and research reports, as well as guided 45 research students, leading to the award of PhD. He has organized 6 national seminars, 3 workshops, and 20 training programs. He got 2 best research papers, 1 papers award, 1 each at national and international level. He got 2 best research paper awards at national level. He got the state best teacher award from the government of Andhra Pradesh for his excellence in teaching and research in 2011. He is serving as a member in several university boards of studies and many professional bodies. He nurtured MBA course at DCMS of Andhra University with a tie-up of leading retailing organizations in India. He served as Deputy Coordinator of Special Assistant Program SAP Phase 3 during the period 1994-2004. He was placement coordinator in DCMS during 2004 and 8. He served as a member of Central Purchase Committee of AU for 4 years. He served as Joint Director of MBA program offered by Andhra University during 2002-5. He served as visiting faculty to many reputed management schools. He was counselor for Andhra University, SV University, SK University, Indira Gandhi Open University, Andhra Pradesh B.R. Ambedkar Open University, Annamalai University, and Madurai Kamaraj University. He served in NCC Air Wing and qualified C certificate and represented All India Vayu Sainik camp held at Bangalore and pre-RDC campus of Visakhapatnam and Hyderabad. Professor V. Krishnamohan Garu served as Registrar of Dr. B.R. Ambedkar University, Srikakulam during 2009 and September 2009 to March 2016 for 6.5 years. He served as Registrar Andhra University for a full tenure of 3 years from 2019. Now he is extending his services to Andhra University as officer on special duty. Now I hand over to Professor V. Krishnamohan.
Thank you, Anuradha Madam. So now, address the Chief Guest, Professor Krishnamohan sir.
Great. Good evening to all of you. I'm so happy to be here on the occasion of valedictory function of International Conference on Recent Advances in Nonlinear Functional Analysis and its Applications, organized in the context of superannuation of Professor G.V. Ravindranath Babu. I'm so happy to be here. At the outset, with the opening remarks by President Dr. G. Nanaji Rao, Head Department of Mathematics, and also beautifully summarized at the conference scheduled by the organizing secretary Anuradha Kameshwari Garu, and the conference summary report in detail presented by Professor G.V.R. Babu, and also for the nice introduction. All pleasing words, although I asked her not to speak beyond a minute. And they invited resource persons, keynote speakers, faculty of the department, and delegates, dear students. Hopefully you are all beneficiaries. And for a long time known as PDN Srinivas, right? Sheila, remember we used to work together in ASET. And mathematics, in fact, is a scary subject to me. That is why I'm sitting so silently. I know nothing in mathematics. That is how I have taken commerce and management as my disciplines.